ऊपर पैनल છે ને ગ્રીન ડ્રોપ ડાઉન છે
હા શું કરું
નીચે લાવો ક્લિક કરો
So we'll start the workshop now. Hello and welcome everyone to the virtual workshop on fundamentals of fiber reinforced concrete and textile reinforced concrete testing and design. First of all, thank you dear participants and distinguished speakers for taking the time to join us today. In this workshop, we have talks delivered by academic and industrial experts from national and international organizations. In this workshop, you'll also have virtual training sections for specimen preparation, testing, and characterization of fiber reinforced concrete and textile reinforced concrete. So this is the schedule of today's workshop. Any questions from the participants can be posted on the chat box. So before the end of each section, that is 10 minutes before the end of each section, there will be a question and answer session. So all the questions which are posted in the chat box will be answered. Now, I would like to introduce the first speaker of the session. The speaker for the section is Professor Ravindra Gettu. He is the Dean for Industrial Consultancy and Sponsored Research, and he is the B.S. Raju Chair Professor in the Department of Civil Engineering, IIT Madras. He has expertise in advanced concrete system and focuses on sustainable construction technologies. I now invite Professor Ravindra Gettu to deliver his talk on Introduction to Fiber Reinforced Concrete and TRC. I pass on the mic to Professor Gettu.
Thank you, Steffi.
Yes.
It's great to be here, and I am very happy to see so many participants who are in this workshop on textile reinforced concrete and fiber reinforced concrete. So I will give a brief introduction on both these materials, and I'm sure that other speakers during the day will provide more details and go in depth. So I'll share my screen. I hope my screen is visible.
Not yet, sir.
How about now?
Yeah. Yes,
Okay.
we can see.
Okay. So I'm going to talk about fiber and textile reinforced concretes. Give just a broad overview, and then we can take some questions or wait for the others to make their presentation. So I would like to start with the discussion on sustainability in construction. There are these sustainable development goals that have been brought together by the United Nations. This was done in 2017. And this is divided or set in 3 rows. If you can see the top row, it is about aspects that relate to the individual human being, like poverty, hunger, health, education, equality, and sanitation. These are things that affect each and every one of us, and we have to improve, we have to provide what is needed for the world to be more sustainable. In the second row, we have aspects that are related to communities, groups of people living together, cities, and so on, like affordable energy, affordable and clean energy, economic growth and work, industry, innovation, infrastructure, reduction of inequalities, sustainable cities and communities, responsible consumption and production. So this is where a lot of our activities in construction come in addition to helping what is there in the first row, and certainly what is there in the last row, like climate change, life below and on land, below water and on land, peace and justice, strong institutions, partnerships for these goals. So what is very clear is that sustainability is much more than carbon footprint. It is not just talking about carbon footprint and environmental impact. Similarly, construction is more than just making the structure. It is not the usual reinforced concrete structure or the same structure that we keep doing. Things are changing. And what we find, if we look closely at the sustainable development goals, there are aspects that we can have an impact on. Obviously, innovation and infrastructure, industry. Today, you are going to hear about floors, slabs on grade, which are very important for warehouses, which is becoming very important again for our industry, especially in these times where so much of online ordering is done. We need large warehouses. We need the warehouses to be in good shape. We need more and more innovation. We need better infrastructure. Sustainable cities and communities. Sustainability, again, is more and more important because we have limited resources. We are seeing resource crunch right now in some aspects. So these are things which tell us that we should waste less and we should work on things that will last for a long time, and we should conserve our resources. This also is related to the Sustainable Development Goal number 12, responsible consumption and production. We have to reduce wastage. We have to increase durability. We have to make sure that what we are using is right and adequate and without wasting for any project. Climate action. Anything that pollutes, uses up too much resources is going to affect climate. So carbon dioxide emissions. We have heard a lot about concrete and cement being having very high carbon footprint. So this is something we have to work on. Similarly, life on land, because the resources, if we are just aggregates, we can imagine the amount of aggregates that are taken out of the ground when we have to make concrete. So all this is very important that we have to look at these sustainable development goals. So I've summarized some aspects that could be more relevant. And this we have here in this 3-pillar approach that has always been used for talking about sustainability. The environmental pillar, the bottom line of environmental actions includes global warming. And here we are talking about carbon footprint, using up the resources, using too much energy, and wasting water or using water. In the social aspects, it's very important that what we do has the right social impact. It helps society, not harm society. Housing for all, our aging infrastructure has to be addressed. We have to take care of pollution of our living space. Finally, the economy, the very important pillar for all emerging economies and everyone all over the world. We have limited real estate, so we have to build in a responsible manner. Maintenance costs are important. It's not just the original cost of a structure, but also maintenance costs. Transportation costs. These are also something that we have to keep in mind. So if we look at all that, 1 minute. Yeah, so we look at these aspects that are there in this blurb that I have at the right bottom. Efficient and economic construction is important. We have to look at low carbon emissions. Our structures have to be more durable. And if possible, we have to look more and more at reuse and recycling of materials and components towards a sustainability-based design. So let me show you what all aspects we should consider. I'm not going to touch about all these, but we should keep this in mind. When we look at the life cycle of concrete, the life cycle starts off with the cement. The production of the cement, which I've told you, is very carbon intensive. So we have to see how little of cement we can use, and how can we make this cement product last as long as possible. Then we have the concrete production where we use a lot of aggregates. See, sometimes 70–80% of the concrete are aggregates. And these aggregates are coming out of mountains and out of quarries, which we are destroying because we have to construct. So before we reach concrete also, already there is a lot of impact that has happened. During construction also there is impact. We need energy. There is a lot of wastage in all sorts of aspects. Wastage of material, wastage of time, wastage of money. So all this, if we can take care of, then most of the life cycle we'll have it in a responsible manner. The life is very important, durability. See, that is why you will find that all the speakers today will talk about cracking, will talk about durability, because it's very important. The structure is not just in the first phase, but also it has to last for a long time. Are we talking about 100 years? Are we talking about 50 years? And can we achieve it without major repair and maintenance? And finally, can we start thinking about design that will allow the reuse of material when the life ends of the structure? Then other than that, also we have to talk about electricity. Electricity, not only in the making of the material, construction, but also when we are living. When we are living and using a building, can we look at the electricity cost reduction, and finally water. So all this, if we can think of, we are looking at two materials which we believe are going to help in this aspect. Fiber reinforced concrete is a material where we have distributed fibers in the concrete, and this will increase the post-crack resistance. That is, the crack will not open. So this we believe is important because you can extend the life. You can make sure something is durable. You can make sure that something doesn't suddenly fail. So this is the importance of fiber reinforced concrete. Why we add the fibers? Particularly so that it can absorb energy during failure, so that there is no brittle failure. We want this crack bridging to delay and control crack propagation. So we get something like a pseudo-ductile behavior. It is not really a ductile material, but is behaving like a ductile material. That's why we call false ductile behavior. And we get high tensile strains, which otherwise we cannot. And this is required for extending the life, making it durable, making sure that cracks do not open. And we also get increased resistance to impact and fatigue cracking. Finally, also the fibers help in reducing the shrinkage cracks. Normally, the fibers are very small in volume, less than 1%. So they limit the cracking and failure. Fibers are not added to increase the strength. This is sometimes a misconception that I always like to insist, that fibers are not there to increase compressive strength or even tensile strength. And this is a mistake sometimes we make. And we find manufacturers or even researchers saying that fibers have been used and the strength has increased. No, it is not. It is to limit cracking, increase the ductility that we can see in failure, avoid brittle failure. So what are some major applications? I'll start off with steel fiber reinforced concrete because this is very common. And I'll give you some examples. This is, for example, the Rotang Pass, the tunnel that was recently inaugurated by the Prime Minister, and where there was shotcrete used with fiber reinforcement for the lining. So we have several tunnels like this in our country. We have a lot of slabs, slabs on grade. I talked to you about for warehouses, even outside in stockyards. We have pavements. We have slabs that are used for storage. In this particular case, each stack of containers gives an axle load for the stacker of 100 tons. So at a certain point, heavy loads have to be taken, in addition to the fatigue load, in addition to the traffic load. So these are elements where fibers have been used a lot. And this is an example of a factory floor. Again, almost with no joints so that robots can be used, automation can be used. with low amount of fibers. Here only 10 kg of fibers was used. So we can limit the fibers through proper design. We can go on to other type of elements. These are segments that we tested for metro tunnel. So a lot of metro construction is going on. There could be cracking. There could be limits on durability. So we wanted to see how fibers could be used in these tunnel segments. You can see some tests going on. And we found that we could have good distribution of fibers and enhance the ductility. We participated in a lot of road construction where asphalt roads are replaced or asphalt roads are topped with fiber reinforced concrete. And we have done this on our campus. And if you visit our campus, you'll be able to see a lot of concrete roads. And most of them will have fiber reinforced concrete. And there is an opportunity to put fly ash here. In this case, we put 30% fly ash. So these are good demonstration projects where we looked at different types of fiber reinforced concrete for roads. This is an interesting application that we could participate in. This is the ramp at Chennai Airport. And here, this is the luggage ramp that is going from the level that the planes are to below where the luggage is taken. And this had to be opened up very fast and had to have a high friction. So fiber reinforced concrete was used, M45 concrete, because of the early need to open this up. And we had some grooves give more friction. We reached a friction coefficient of 8 because the problem was the luggage trolleys were slipping and we had to increase this. So we went for a fiber reinforced concrete slab. We can have other applications in prefabrication. These are wall panels. This is a set of wall panels that have been used for a 68-kilometer long road. These are from Nagpur, where we have elements, precast elements that are used for the stormwater drains. Here, fiber reinforced concrete and self-compacting concrete were used with simple systems to put these together, a trench cut, and you can put these prefabricated elements. So prefabrication can take very good advantage of fiber reinforced concrete and other materials. Then we have all seen the beauty of the cladding in the Mumbai airport. Again, it's glass fiber reinforced concrete. Glass fiber reinforced concrete has also been used in screeds where we want to protect precast slabs. This is a case at IIT Madras where we have used glass fibers, 12 mm long glass fibers. So there are many things. Basically, what we are looking at is how to increase the toughening that the fibers will give to the concrete. We have to do testing. There will be a lot of talks about testing. These are examples of the square panel test, where we test a panel of shotcrete with a punching type load. And then we use what is called the Barton chart. So this is used across the world in defining what is the energy absorption capacity, depending on the type of rock and the thickness of the layer. We can see how much is required, what thickness is required, and what amount of fibers. And these are some examples where you get the load displacement from the test I showed you before. And there will be more explanation in the latter part of the workshop. And then we calculate the area under the curve and get the energy. This is then used to design. Now let's move on to textile reinforced concrete. This is an interesting concept which draws on what we did with Ferrocement, where you have a fine concrete matrix, non-metallic reinforcement to give us the textile reinforced concrete. Obviously, because it's non-metallic, we have better corrosion resistance, thin elements, better optimization, and therefore we can go for an optimum section, lower dead weight, better durability, and we have good shrinkage and crack resistance. And with all this, we can get our sustainable development goals. There have been examples here. We can see prefabricated elements, thin slabs like shells done with textile reinforced concrete. This is the facade. Later on, you'll hear from Dr. Mohit Raina, and this is a picture from one of his projects where you can have a facade looking so elegant. In IIT Madras also, we've started doing thin elements like this channel segment you see here. Repair, we can use textile reinforced concrete. This is an example from abroad, and this is an example from IIT Madras where we've repaired the column in one of our buildings. So a lot of possibilities there. And what does this textile incorporation do? Give us a behavior like this. Where we increase the number of layers of an adequate glass fiber, we get a behavior that is like strain hardening. So we can take advantage of this behavior to limit the cracks. The number of cracks decrease. And we can, with the adequate type of composite, this again, people will talk about it later on, you can get this bilinear behavior and design for it. And therefore, you can design an element which has few cracks or very thin cracks, so that it does not affect the serviceability or the durability. Now, talking about durability, we have to make sure that it is the right type of textile and right type of glass also. So here I have two glasses, two different types of glass textiles and different environment that you see here. This environment is simulating what happens inside the concrete, or there could be alkali attack. We find that if you have AR glass, alkali resistance glass, almost nothing happens over time. However, if you use E-glass without any particular protection, you see the strength is coming down. This is something that obviously we don't want. Why this happens is that the surface gets attacked like this. The surface of the textile becomes like this. So we have to be careful. We can have pitting type corrosion happening. Again, this people will talk about it in more detail. Now we can modify the matrix. So we find here that in the composite, you find that if the composite and the glass made out of proper glass is there, then you don't get much behavioral change in spite of the exposure. However, if it is E-glass, you have a drop. Now, what we can do is modify this, change the matrix to make the behavior better. So that is where we come in to see if we can change the glass, change the coating, and change the behavior so that we have proper design. We have to look at the fabric. We have to look at the matrix. Then we understand the mechanical behavior so that we get a stress strain response that can be used in design. And finally, we need to design the structure, and there'll be a talk later in the workshop which will discuss how to design both with fiber reinforced concrete and textile reinforced concrete. So I'll stop there, and if there are few minutes I think left, I can take some questions, or we can leave it for later. Thank you, Steffi.
Yeah, thank you, Professor. Thank you. It was a very informative lecture. So participant can post your question. So I have one question, sir. So by using fibers, can we completely eliminate joints in the floorings?
We can. There is this concept of jointless flooring. Well, you're completely eliminating always has a limit, no? So I think in the practice, some other speakers from the industry can answer. They go up to 25 meters. So after 25 meters, you need some sort of a joint because it's not practical to cast for infinitely, no? So there is the concept of jointless flooring where we design for almost no cracks or very, very thin cracks. This we have done something with our consultancy works. But I think people from industry will be able to give an example. I think the one that I showed of the BMW factory, I think that was a jointless floor. So we can do it. We can do it. In certain applications, certainly you can eliminate cracks completely, joints completely.
Okay, so thank you. And there are two more questions which you can.
Yeah, I think there is one on the PVA fiber. See, what I know about PVA, I have not directly used PVA, but I've heard that it's very expensive. So cost could be a limitation, but it has been used a lot in this was propagated a lot by Professor Victor Lee in the University of Michigan. And he used it a lot, and a lot of people use it in Japan, China. This is being used a lot. But I believe it is very expensive. There could be durability issues also. Yeah, but I have particularly not had experience. Comparison of carbon and steel fibers. See, carbon fibers are very thin. So that is one big difference in terms of mixing. If you have something that is very thin filaments, mixing in concrete becomes very difficult. Cost again of carbon fibers is higher. We have used pan fibers, which are like the precursor to the carbon fibers. Those can be useful in plastic shrinkage cracking. But as far as I know, it will not compare with steel fibers because steel fibers are easier to mix. We understand the durability better. So using carbon fibers in conventional fiber reinforced concrete is very difficult. Mixing will be difficult. The cost will be very high. Then somebody asked, what is the main advantage of TRC over ferrocement? Well, as the name implies, we don't have any steel reinforcement. That is the biggest advantage. Otherwise, conceptually, we can even think that TRC is nothing but ferrocement, but without the steel reinforcement. We are using another textile. So conceptually, it's not very different. So people who have been using ferrocement should make the switch very easily. It is not a new animal we are talking about. This is something that people have used a lot. The only thing is the big disadvantage was the corrosion. So instead of that, we are using something, we are trying to define something, derive something that will not have these durability issues. Then in FRC, there is an aspect ratio. Is TRC also geometry? Certainly. The type of textile is important. So we are looking at how to design the textile. The architecture of the textile is important. You cannot have the warp and weft very, very far away. Then it will not help. You cannot have it too close because the aggregates will not pass through. So it is very important, just like we look at aspect ratio in FRC and TRC, we have to look at the fiber architecture. Then there's a question on TRC is in precast and in situ. Yes, they have been used in both. They have been used in both, and I'm sure speakers will talk about it. I told you one example of where we use TRC for retrofitting. That was done at the site. And I also showed you examples of prefabrication. So both can be done. Now someone says hooked-end steel fibers. Well, there are many types of fibers. The most efficient seems to be the hooked-ended steel fibers. This was a patented technology. Then the patent expired and other people started using it. But in my opinion, either the hooked or the crimped, that is the wavy one, seem to work. But the hooked-ended always work very well. Now, somebody says, I'll see how long Steffi gives me and I'll stop. There are a lot of questions coming in.
There's one more minute, sir. So
okay, one more minute. I'll try to fit in as many as possible, but I'm sure that other speakers will do a good job. So they say fibers don't increase tensile strength, so why not use steel reinforcement along with fibers? Yes, we can use. There can be a combination also. There's nothing stopping us. Amount, what if the amount added is more than required? Nothing. It is just you're being on the side of safety. So if you add more fibers, more go wrong, that we don't have to mind. What are critical differences in FRC mix design with more detail? The main thing is workability. Main thing is workability. When you put the fibers in, you will lose slump, you will lose workability. So the mix has to be more workable. So generally, we will put about 10% more of paste or mortar. And what I usually say is if you're designing a concrete for a certain slump, you design for 3 centimeter extra slump. For TRC, again, it is very important to have proper workability because we need the mortar, we need the paste to penetrate into the textile. So that is very important. Okay, so I think
so
I've covered.
Stop. Yes,
okay, I've covered all the questions. Thank you, Steffi.
Thank you so much, sir.
Yeah, thanks for having me.
Yes. So the next presentation will be by Dr. Sunita K. Nair, who is currently a visiting faculty at IIT Palakkad. She completed her PhD from IIT Madras. Prior to her research career, she had over a decade of teaching experience at Amrita University, Coimbatore. Her research areas include characterization and modeling of special concretes using soft computing tools and techniques, and also fatigue-based design of concrete pavements. I now invite Dr. Sunita K. Nair to deliver her talk on design and characterization of FRC. The floor is yours, ma'am.
Good morning. Good morning.
Yeah,
Thank you, Steffi.
Yeah.
Very glad to see so many participants in this workshop. Thank you for coming. Let me just try sharing my screen. I hope everything is working fine. I hope.
Yeah, we can see a screen.
Right? Everything seems fine, right?
Yes,
Yeah,
yes,
go ahead.
yes.
So thank you for this opportunity. And what I will be presenting here is a combination of work that was done at IIT Madras during my research at IIT Madras, and after my PhD, some collaborative work that I have done with Professor Gitu and Dr. Steffi, and some current work that is being done at IIT Palakkad with my student Ajish. So just 1 minute. Yeah. So we have had a great introduction to the topic by Professor Gitu. So I don't need to actually introduce the topic, but still there will be a brief introduction and followed by discussion on the relevant characteristics of fiber reinforced concrete and how these characteristics are brought into the design philosophies of fiber reinforced concrete. And then there will be then I will demonstrate what is the influence of these material parameters on a design of fiber reinforced concrete. So, as most of you might be knowing, fiber reinforced concrete has a homogeneous distribution of randomly oriented short fibers in concrete. The fiber length could vary from a few millimeters to up to 60 millimeters, and the shape might vary. You can have cream fibers, hook-ended, straight fibers, and by design, we expect this orientation of the fiber to be random, but that does not mean that it is not possible to have preferential orientation. There are certain cases where we would like to have preferential orientation, and that can also be designed appropriately. But for the conventional fiber reinforced concrete, what we are expecting, as you can see here in the inset, you might be able to see the X-ray tomography of some of a chunk of concrete.
My system doesn't have
Sorry, sir. A chunk of concrete. Excuse me. And yeah, this is an X-ray tomography image of a chunk of concrete that has been.
Get that link. I got the link, but it was.
Just 1 minute.
Sorry, please mute your mic.
Meeting is not. Zoom. I don't have the Zoom app open. Not in that you can download that.
Just 1 minute.
They have Zoom and all they will do. They have.
Okay. So we have this X-ray tomography image, which represents the random orientation of the fibers. And what fibers does is that it will elongate more than the matrix under tension when introduced into the matrix. And 1 minute. So what are the different types of fibers that can be used in concrete? So there are many type material that is used commonly in fiber reinforced concrete. The conventional material include the metallic steel fibers, polypropylene fibers, polyester fiber, carbon, and the mineral fibers such as glass, sisal, and naturally occurring fibers such as jute and coconut. There are unconventional material fibers such as stainless steel, amorphous metallic fibers, acrylic fibers, mineral fibers such as basalt, and the next generation carbon fibers such as PAN. Now, how do you choose the appropriate fiber for an application is a topic of discussion by itself, and I will try to touch upon it at the later part of the discussion. Now, another question that we can try to answer is when we should think of adding fibers to look to see the various situations under which you must think of an option to add fibers would include a situation when you would like to increase the crack resistance. It might be for any reason. It could be for shrinkage resistance, or when we are expecting cracking due to the slender nature of your structural elements, when there is a requirement for having post-cracking flexural performance. That is, the design itself is governed by the post-cracking flexural performance of the concrete. Such a requirement occurs in applications such as pavements, flooring, tunnel lining, etc. And if there is a demand for higher ductility, this could be a supplementary reinforcement. The main reinforcement cannot be avoided in such cases, but in addition to have some additional ductile performance, we can add fibers in seismic design or regions where you expect higher ductility for your structure. When, as Professor Gettu had said, whenever we read where there is a requirement for increasing service life, by delaying the crack propagation due to the addition of fibers, we can increase the sustainability value for your structure. And if you would like to make a bendable concrete, that is highly deformable concrete, there is only one option to go for fibers, because that is the only method to increase the tensile strains at rupture. So with this in mind, let's think of what are the characteristics of fiber reinforced concrete that may be relevant to us. For the convention, if you look at the conventionally adopted dosage, this also indicates that the economically viable dosages of concrete, of fibers, is mostly less than 1% in volume fraction. And for these dosages, we generally obtain a strain softening behavior, or in other words, the pseudo-ductile behavior for concrete, and very limited increase in the first crack strength or the strength of concrete. So if you look at the behavior of concrete, it would possibly be showing a reduction in the load carrying capacity after the first crack. However, the behavior is not as brittle as the normal concrete. So due to the presence of this post-cracking capacity in the fiber reinforced concrete, there is an increased energy absorption. And that means there is some capacity which is a function of the toughness of the concrete, that is, which is imparting some toughness to the concrete. And as already discussed, since strength is not the primary, strength increase is not the primary effect we are expecting from fibers, it is essential to capture the post-cracking enhancement, post-cracking behavior, performance enhancement through characterization techniques. And this is only possible. That is what I am meaning is to capture the load deflection curve beyond the first crack. We need to do a displacement or a crack width control testing. And it is an essential component of the quality control for fiber reinforced concrete. This is something that we need to understand as a community which works on fiber reinforced concrete. Strength test would rarely demonstrate the actual benefit of adding fibers to concrete. So we need to do what is called the displacement control testing or the toughness characterization. And this characterization can be done under various configurations. It can be done under compression. It can be done under tension. The most commonly adopted configuration is, however, the there are many standards and codes that specify configurations suitable for flexural toughness testing. The prism testing, which is recommended in the IS code also, the Indian standard code, IS 17161, which was recently published. It recommends the 4-point bending configuration, which is on the unknown specimen. There are the European standards, which prefer the 3-point bending configuration, which is a north specimen. Then the modified 4-point testing, which is done, which is as per an ASTM code, ASTM 1399. And of course, we have the square panel and this round panel testing. Square panel is essentially for sprayed concrete, whereas the round panel is done as per the ASTM 1550. So there are many configurations, and the user might be confused as to which particular testing will be relevant for them. So for understanding this, you must also understand how the results look like. So if you can see this slide, these are results obtained from 4-point bending test on unknown specimens, done on M35 concrete with various dosages of hook-ended steel fibers. Now, the figure clearly demonstrates what is the enhancement that is attained by the concrete due to the addition of various dosages of fibers. Now, this is what is required to be captured when we are doing the characterization. If you look at other figures, other test results, what I have compared here is same dosages of various steel fibers. So we have hook-ended steel fibers with a length of 50 mm, 60 mm, and undulated green fibers and undulated flat fibers. So this is a comparison of same dosage, but different type of fibers. Again, this demonstrates that blindly following one dosage for any fiber invariably might not lead you to have the same performance as expected. You might have a better performance or a lower performance depending upon the nature of interaction that occurs between the fiber and the matrix. These other pictures that are shown below, on the left side, you see the flexural toughness the load deflection curve obtained using macro glass fibers and macro polypropylene fibers. The brown one, the maroon is polypropylene fiber, the yellow is glass fiber. So you can have a comparison between steel, non-metallic fibers, and on the right side bottom, you see the load deflection curves by on the same matrix, but by incorporating the unconventional amorphous metallic fibers. So the AMF fibers is starkly different from the other type of fibers, because if you see most of the other curves, you see very little change in the first crack strength or the flexural strength. However, when AMF fibers were added, there is a marked increase in the first crack strength. So what I would like to stress here is that depending upon the performance imparted by your fibers, you might get an increase in the flexural strength also. But by design, we are not expecting that we want to have an increase in strength by addition of fibers. What we want is probably a much better performance in the post-cracking area. And since the amorphous metallic fibers were giving very limited post-cracking strength, we attempted to do a hybrid mixture of steel and amorphous fibers, which gave results having a very synergistic performance. That is, if you take the individual steel fiber and amorphous fiber, the performance, when added up, it had a synergistic effect. This could also be attributed to the higher volume fraction. So what we understand here is, due to the post-cracking capacity, fibers impart rotation capacity to your structures or your structural element. And due to this, we have to utilize its potential, this rotation capacity, and bring it into the design technique. And in order to bring this post-cracking performance into design technique, it will not be sufficient to use elastic design techniques, because there we restrict ourselves to first crack strength. Therefore, definitely the design techniques used for fiber reinforced concrete should include inelastic analysis. The material capacity should be related to the post-cracking behavior and not to the first crack strength alone. And we can, these post-cracking strength characteristics could be used to model the stresses or moments that occur in your structural element. And the strength parameters that could be used, I will explain to it in a moment. Commonly used strength parameters are the equivalent flexural strength and residual flexure strength. Now, a little bit into how we actually bring in this post-cracking capacity into design. Let us look at one example where we have the inelastic design technique for slab on grade. This is similar to the TR34 Concrete Society guidelines for slab on grade, where we adopt the yield line analysis for ultimate load estimates, where it is assumed that under the load, wherever you're applying the load, the failure is not when the first crack appears, but we allow the yield lines to develop below at the bottom of the slab, and these radial cracks will extend and reach the circumferential cracking. And when the circumferential cracking extends to the top of the bottom and top of the slab, and the crack appears at the top, the failure condition has been attained. So the failure is only at the appearance of the crack at the top. That's the ultimate moment capacity can now be represented or modeled as the sum of the plastic moment capacity along the radial yield lines and the elastic moment capacity along the circumferential yield lines. That is how the ultimate moment capacity becomes the sum of plastic moment capacity and the elastic moment capacity. So this is one way of bringing in the post-cracking capacity of your concrete to the design equation, because the plastic along the yield lines, the capacity of the concrete will be represented by the post-cracking flexural strength. Then in such a situation, how do you model the elastic and plastic moment capacity? Since the elastic moment capacity is represented by the appearance of the crack at the top, it is modeled as the first crack strength. So you will be using the flexural strength FCK to model the elastic moment capacity. It is just the flexural formula. You can use the flexural formula to determine the FCK value and substitute it in the MN equation to obtain the elastic capacity. However, what about modeling the plastic moment capacity along the yield lines? For this, we need to use the post-cracking capacity, which is the equivalent flexure, which here is represented as the equivalent flexural strength obtained using the load deflection curve. The equivalent flexural strength of the concrete, of the fiber reinforced concrete, is obtained by taking the area under the load deflection curve, the total area under the load deflection curve, TEN, dividing it, this load deflection curve we will obtain from the 4-point bending test that we have already seen some examples and the configuration. And also this test will be demonstrated in the next, right after this talk. So you'll understand better how to obtain this load deflection curve. Once the load deflection curve is obtained, we obtain the equivalent load, the post-cracking equivalent load as a function of the area under the load deflection curve divided by the deflection up to which we want to determine the load deflection, the area. Now, this deflection limit has been specified in many codes, and in India, as per IRC or IS code, we take it to be 300, N to be 300, that means we take it up to 3 mm. Sorry, N as 150 mm, so we take it up to 3 mm. So the test is run, we obtain the load deflection curve, consider the area up to 3 mm, divided by 3 mm, and you will get an average load capacity in the post-cracking regime. That when substituted in your flexural formula, we will get the equivalent flexural strength. Now, this demonstrates how we are bringing in the load deflection behavior, the energy absorption capacity, convert it into a strength term, and apply it in the moment equation. So we bring the FEN value into the capacity estimate, the plastic moment capacity estimate, and you obtain the ultimate moment capacity. This is similar to what you would have done if you had reinforcement, and you would assume we would be calculating the plastic moment capacity as a function of the yield strength of reinforcement. Now, just to demonstrate how the performance of fibers in concrete is going to affect your design. So using this ultimate moment capacity estimate, we can estimate, or we can design the slab on grade for the thickness. And if we do a design for the thickness requirement using the design, the obtained equivalent flexural strength and FCT value, that is the flexural strength value for various fibers. If you see at the bottom, you see SFA, SFB, SFC, SFD, glass fiber, PP fiber, amorphous metallic fibers. This is the combination of steel fiber and amorphous metallic fibers. So the first 4 represents 4 types of steel fibers, and then you have the other type of fibers. The gray curve represents the values of equivalent flexural strength for an M35 concrete using 15 kg per meter cube, or equivalent volume fraction. For glass, it is around 5 kg. PP, I think, glass, I think it is around 10 kg. PP, I think it is around 5 kg. And so what we have done is kept the volume fraction same and taken the values for the equivalent flexural strength and the flexural strength. So the orange curve represents a corresponding flexural strength. Using these 2 values in the moment capacity estimate, if you design the slab, you can see the variation in the required thickness. So what would be clearly noticed is that if there is an increase in the equivalent flexural strength, there is a considerable reduction in the thickness requirement. Similarly, if there is an increase in the flexural strength, you have a considerable. So both flexural strength increase and equivalent flexural strength increase is going to affect your thickness requirement. And since all the SF steel fibers give similar performance, you obtain almost similar thicknesses. So this is how you translate the characteristic of the fiber reinforced concrete to your design. Another example, another way of expressing or demonstrating how we bring in characteristics into design is when we do a fatigue-based design for fiber reinforced concrete. So what we have represented here is a fatigue, a cyclic loading on the fiber reinforced concrete. The first one is when you apply a pre-peak fatigue, that is, you allow the cycling to happen before the first crack occurs, and then you obtain the the stress versus N curve, the SN curve. The second figure, the graph there, we have what has been done is we have applied post-peak fatigue, that is, the cycling is done as a function of the post-crack strength, and you obtain similar SN curves. And using these SN curves, what we can do is, if you have a design method where you have these moment estimates, this is same as what we have seen, Mn plus Mp. So in this moment estimate, you can use either the equivalent flexure strength or the residual flexure strength as it is given in the notched beam testing, both will have the same expression of the same pattern, then you can determine the moment. But if you want to bring in fatigue behavior, what we will have to do is to factor the strength parameters. Now, to factor the strength parameters, we can use the SN curves and use a safe stress reduction factor to factor your stress parameters to both the notched results as well as the unknotched test results, as the X and Y value will be obtained from both the pre-peak and the post-peak fatigue figures, fatigue models, and you can determine the required thickness. This method is to be followed when we are doing designs of cases where we are expecting high cycle fatigue, especially in pavements or in shop floors where you're expecting a lot of movement of vehicles. So now let me touch upon how to do selection of fibers. What you have to do is you should adopt the appropriate material parameter. Now we have seen that the equivalent flexure strength and the flexure strength, both are going to be part of your design equation. So whichever fiber, again, I have demonstrated one example where many fibers can be used for the same design. So you can choose your appropriate fiber based on the required material parameter, what is the required performance criteria, and you have a flexibility in choosing the fiber type and dosage, and any fiber type and dosage that gives sufficient material characteristic can be used for the application. There is no restriction on which fiber type or which dosage. The dosage and the fiber type combination, which gives you the required FEN value and FCT value, can be adopted for the application. So just one example where we have used the fiber reinforced concrete for a bridge repair in Kerala.
Sorry to interrupt, only 1 minute more.
Yeah, done, yeah. Stephanie, I'm done. Yeah, so we have this there was an initial repair with micro concrete which cracked, and so what we have said is we have repaired the bridge using similar concrete, but with 60 kg, with 15 kg per meter cube of fiber. But it was a combination of both steel and microfiber, and this is working very well, and the PWD is actually very happy with this work. So thank you. Do we have time for questions? Did I overshoot?
You finished it on time, but I don't think we have time for questions.
Sure.
We can go with the demo session, and after that, if we have time, we can.
That's also.
So participants, you can post your questions here. So Dr. Sunita will answer it at the end of the next session. Okay, you can continue.
Thank you. Now I will hand over to Ajish. We will show the demonstration of how to, there will be 3 sessions. What we will be doing, the first demonstration is going to be on the testing as per the Indian standard IS 17161, which is in line with the ASTM 1609 and JC SF4. And we will also show in the beginning how to fabricate specimens on site, and then we will show the testing, and after that there will be a demonstration of how to do the calculation. Mostly testing is known to people, but how to do the calculation from the parent file that we obtained from the software will also be demonstrated here. Ajish, would you like to take over? I have made you the co-host, Ajish.
Okay, ma'am. Thank you.
Hello everyone, myself Ajish, PhD scholar, working in the area of fiber reinforced concrete pavement design in the Department of Civil Engineering, IIT Palakkad. So today I am going to explain how to perform the flexural toughness test on fiber reinforced concrete using displacement control. This is our construction material laboratory, which is mainly focused on the physical and mechanical characterization of all construction materials.
Tests on concrete are generally done using any two control system. One is the open loop control system, the other is the closed loop control system. For the commonly done strength tests, it is the open loop control system that is used, in which the test is controlled using parameters such as load, applied load, which is not significantly affected by the response of the specimen. An example would be the compression test on concrete, where we generally give the loading rate, which is 145 kg force per centimeter square per minute, as the control parameter. There we are only specifying the load. Now, in cases where we would like to determine the complete load deflection curve of concrete, especially in cases like fiber reinforced concrete, for which the post peak response is very significant, using an open loop control system might not be sufficient. In such cases, we go for the closed loop control system. In the closed loop control system, the output of the controlled variable is monitored by the controller. Thus, it becomes possible to control the test using a control variable that is related to the specimen response. So, we can use any of the parameters such as displacement of the specimen,
Have we lost the?
Yeah,
Okay. No problem. I will play the.
you will play. Okay. Please share the video, ma'am. We can't hear. Please share the sound also.
using a control variable that is
Is it now audible?
Yeah, it's audible.
related to the specimen response. So, we can use any of the parameters such as displacement of the specimen, the crack mouth opening displacement of the specimen, etc., for controlling the test. Now, if you see the flexural toughness characterization of fiber reinforced concrete, there are two configurations. One is the 4-point bending
Excuse me,
test,
ma'am.
which is done in the similar
We can't see the
configuration
video.
as the Indian standard 516
Excuse me.
specification for the modulus of rupture testing. The other is the 3.
Can you, 1 minute, I'll just stop.
In India, we have
Are you able to
adopted
see now?
the unnotched test in the 4-point
Yeah, we are
bending
able to see the
configuration
window. Yeah.
for characterization of FRC toughness, and it has been published as an IS code IS 17161 recently. Today, in this presentation, we will be giving you a description of how to do the flexural toughness test using the unnotched specimen.
The objective of this test as per IS 17161 is to determine the flexural strength and toughness parameters of unnotched fiber reinforced concrete flexure specimens under displacement control in the 4-point bending configuration. The flexural behavior of FRC is analyzed by the enhanced post-cracking capacity expressed in terms of toughness parameters like equivalent flexural strength ratio, etc., obtained from the load deflection curve from the test. The test specimens were cast with the standard molds of size 150 by 150 by 700 mm by incorporating fibers in the required concrete matrix. The specimens were subjected to standard curing after demolding at 24 hours of casting. The flexural toughness test is done on the 28th day to get the flexural strength and post-peak behavior of FRC. The specimen is removed from the moist environment and allowed to dry for some time. Now, I will explain how the specimen is prepared for testing. Mark the span, that is 450 mm, and the 2 points at which the third point loading is to be applied. This marking on the 3 sides of the specimen except bottom will help to fix the yoke frame on the specimen. The loading frame should have sufficient stiffness. Also, the 4 rollers, including the 2 support rollers and 2 loading rollers, should all be well greased and freely rotating along its longitudinal axis. Of the 4 rollers, one roller, preferably one of the support roller, should be able to swivel about its transverse axis also. The loading head with the loading rollers should also be self-leveling when seated on the specimen. The specimen is to be loaded such that the direction of casting is perpendicular to the loading direction. That is, the specimen is rotated by 90 degree over its longitudinal axis with respect to the casting position, in order to negate the unconservative bias on the toughness that could result from fiber settlement, if any. Ensure the specimen is placed on the rollers correctly. Then fix the yoke frame at the end of the span on either side of the specimen. A yoke frame is used to fix the LVDT on either side of the specimen, which is clamped to the mid height, which is the position of neutral axis of the specimen. The yoke frame consists of a frame and a slotted holding bar. The slots on the holding bar allows free rotation of the bar when placed on the yoke, at the same time holds the LVDT in position. 2 S brackets are glued on either side of the specimen at the midspan to place the LVDT. These 2 LVDTs are used to measure the true deflection at the midspan. Normally, the average of LVDT values are taken as the specimen deflection. Connect the LVDT to the data acquisition system and complete all necessary connection to interface the data acquisition system, the transducers and the loading frame. Initially, the test should be started under load control to enable stabilization of the specimen and testing system. The loading rate is closely related to the expected peak load and allowable time for reaching maximum load. Normally, the peak load should reach within 3 to 4 minutes of test commencement. Initial load control testing can be done at a constant rate of about 100 to 200 Newton per second, which is verified from the constant slope of the load time curve. After reaching about 20 to 40% of the expected peak load, the test control parameter should be changed to displacement control. In general, the loading rate should be between 0.025 millimeter per minute and 0.1 millimeter per minute up to first peak, and later about 0.5 to 1 millimeter per minute. However, the optimum rate of loading may be arrived at based on the response of the machine and the sensitivity of the control system. The servo control testing system would generally allow dynamic control over the testing parameters, including the control parameters such as rate of loading, proportionality constant and integral constant, etc. Now you can notice that the load is dropping, indicating that the peak load has already been crossed. Now the specimen will start to display the strain softening behavior, which is captured by the descending branch of the load displacement curve. Based on the type, dosage, performance of fiber, this part is the most critical period of testing. The operator should continuously monitor the load deflection behavior and, if needed, make modification to the control constants as and when required, unless the control loop system is capable of adjusting by itself, which may be possible in high-end machines. Here you can notice the slow extension of the crack and the well-controlled test characteristics. The test can be terminated at a little over 3 mm deflection or when the load drops below 3 to 5% of the peak load. Once the desired deflection or load level is reached, the test is terminated and the data is saved. The test data will be available in spreadsheet format, and this data can be used to plot the load deflection diagram and to determine the flexural toughness parameters.
Okay, we can take some questions now and then we will demonstrate the calculation, because if there are any...
we have like 5 questions from the audience. So I'll ask one by one.
Please.
So, any cost comparison of the various products? Do you have any cost comparison for the various products you are discussed in the presentation?
No, I have not done any cost comparison, but maybe when we have discussions from industry, maybe you can ask this question to them, because I have purposely not done any cost comparison between these fibers.
Okay, and can you discuss about the optimum dosage?
Please. This is something that you must understand. There is no thing called optimum dosage, because it is a design dosage. It is never an optimum dosage. Whatever is the requirement of the design. If again, I have demonstrated that various fibers can give various type of various response, right? So based on the response, the characteristic will vary. So for each type of fiber, there's a different performance. So how can we specify the optimum dosage as a generalized value? So this is not possible. It has to be done through characterization, and after characterization, the obtained characteristic should be compared to the design requirement, and only then we can finalize the dosage of the fiber. I hope I have can.
Can you please switch on the video so that we can see?
Sure.
And the next question is, what is essential mandatory acceptance criteria on fibers where there is limit? So where there is, you can answer first.
No, please.
Where there is limitation of test facilities available at the lab or at the site.
This is a very important question. See, the test requirement depends on the application. See, for example, if it is a flooring application, so we have to mandatorily have the equivalent flexural strength and the flexural strength value. So flexural toughness is an essential and a mandatory characteristic. Similarly, for tunnel lining, we will require the residual flexural strength for the design itself. So based on the application, we have to do the corresponding testing. Now, if it is for other applications such as shrinkage or additional crack resistance, then we need not go for elaborate testing. We can use the test results that are provided by the fiber manufacturers, and then we can compare between the fibers based on the tensile strength, tensile capacity, and its again workability is another issue that we must have be considering when we are using a fiber. So it's mixing easiness. So there's no one stop test which I can specify for choosing a fiber. So I hope I have answered the question. It's mostly application dependent.
Okay. So how do you calculate the aspect ratio for fibers?
Aspect ratio is just length by diameter.
Yeah, that's okay. Does mixing, it's like a two-part question. Does mixing in central concrete mixtures cause adverse deformation in steel fibers? And also, does the orientation of fibers affect the concrete strength?
First part I will answer first. What we have found out and we have experienced both on lab conditions as well as site is that if there is sufficient slump, that is around 80 to 120 minimum, even the longest fibers do not have any adverse effect on due to the mixing. But if the slump is lower, there may be issues in losing the shape of the fiber, which I did. There was a mention about that in the video itself. So other than that, we have never had an issue of adverse effect due to mixing on fibers, provided there is enough slump. The second part of the question, I'm sorry.
Orientation of fibers.
See, orientation, again, in general, we prefer three-dimensional orientation, but there are cases where we have very slender applications where we have slender elements and where the crack direction is already known to us. In such cases, it might be better to have a preferential orientation. It will not affect the strength, it will improve the crack resistance. So preferential orientation is only when we go or where we are already sure what will be the direction of crack. So can we go to the...
yeah, we have few more questions. Can you answer them or like we can take 2 more minutes?
Yes, yes.
Okay. So is the fibers to be added based on percentage of weight of cement? Is it mandatory?
That is how we take the kg per meter cube. But if it is volume fraction, it's not with respect to weight of cement.
The next question is, what is the potential application for functionally graded FRC?
Sorry, I did not understand what is functionally graded FRC. May I know? Okay, maybe the participant can pose the question once again.
Okay, okay. And is there any analysis and design comparison available on conventional and FRC concrete of same grade?
Yes. You are asking whether design calculation, design thickness was of conventional versus. I have it. I think I have not put it here. I think it is there in paper. See, what I have found is about 20% reduction in thickness is obtained if we go for around 15 to 20, somewhere around 40% of RE value. RE is the non-dimensional flexion toughness value. So that is around, but where there is an enhanced, where there is a post-cracking flexion strength, which is about 40% of the peak strength. There you can get about 20% of reduction in thickness.
Okay. That's all the questions. Thank you, ma'am. Thank you for your valuable time. And
Sophie, one more calculation part. We have one demonstration.
Oh, you have? Okay. You can carry on with that. Yes. Sure. Try to finish it with 5 minutes.
No, 2-3 minutes. It will be.
Yeah. Okay.
Ajish, can you take over?
Yes, ma'am.
Yeah.
Yes.
So we'll now have a demonstration of what to do with the result that is obtained from the testing.
Okay. So can I share my screen? Yeah. Is my screen visible?
Yeah.
Okay. Okay. Thank you. Okay, so our test is finished now, and we got the load deflection data in Excel format. So the test data can be used for further calculations. So this will be explained in a minute. Okay, so first of all, look at how the raw data looks like. So this is our test data. Here we can see the load and two deflection values measured using two LVDTs. Okay, Then, so you can see that the entire test data is captured, and now the average displacement value can be calculated from the readings of the two LVDTs. And this average value has to be used to plot the load deflection curve as well as for all further calculations. So we can calculate the average of these two displacement. Okay. So this is the load deflection curve of the test, which is plotted using the test data. So the load deflection may be made in the same Excel file, or the data may be exported to any suitable plotting software, and then the plots made. Okay, so the similar plots may be obtained for all samples in one mix and combined in a single plot. So this is a sample diagram with all plots on the same curve. Clear? Okay. Then now let us see how to calculate the various strength and toughness parameters from the load deflection data. The first step is to find the flexural strength of FRC specimen. For that, find the first occurrence of peak load from the Excel corresponding to the first crack strength. Okay, so we can determine the peak. So 31.24 as the peak load. And here we should be careful to check whether this load corresponds to the first peak, because in certain cases where the specimen may display strain hardening behavior, so there may be multiple, normally two peak loads occurring after first crack also. So based on the peak load, we can calculate the flexural strength using the following equation. So this is the equation to calculate the flexural strength. So this is the simple bending equation or flexural formula. FCT is equal to Pmax into L by BD square, where FCT is the flexural strength, Pmax is the peak load, and L is the span. B and D are the average width and depth of the specimen. Okay. So using this equation, we can calculate the FCT value. So we got the flexural strength as 4.17 MPa. Okay, then next we have to determine the equivalent flexural strength. The equivalent flexural strength is calculated for specified deflections given by L by N for the values N is equal to 150 and 300, where L is the span of the test. For N is equal to 150, we will get a deflection as 3 mm, and for N is equal to 300, we can get the deflection as 1.5 mm. Now for each of these specified deflections, area under the load deflection curve up to the specified deflection need to be obtained. So for that, consider the load deflection curve between consecutive points as a trapezoid. Okay, so load and deflection, the consecutive points are considered as the trapezoid, and find the area of trapezoid for each pair of adjacent displacement values. So we are using the same formula of symbol bending here also. The only difference, instead of peak load, we are considering the average load, because we are calculating the deflection up to a specified limit of deflection. For that, we are considering area under the load deflection curve up to the specified deflection. On dividing this area by corresponding deflection, we obtain the average load carrying capacity. Okay. So calculate the area of the trapezoid for each pair of adjacent displacement value as discussed before. So here you can see the equation for calculating the area of trapezoid. Okay, the sum of areas up to 3 mm, here the average value up to 3 mm will give the total area under the curve up to 3 mm. On dividing this area by corresponding deflection, we obtained an average load carrying capacity up to the specified deflection, as I said before. That is, the total area up to 3 mm is taken and then divided by 3 mm will give the equivalent load up to 3 mm deflection. So here we can see the total area up to 3 mm, and this is the average load carrying capacity for up to 1.5 mm, and this is for 3 mm. And using this average load, we can calculate the equivalent flexural strength, that is Fe 300 and Fe 150 value. Then another toughness parameter which can be calculated using this test data is the equivalent flexural strength ratio. It is represented as REN here. The equivalent flexural strength ratio is a dimensionless quantity which is obtained by normalizing the equivalent flexural strength with the flexural strength of each specified deflection limit, that is L by N. It is normally expressed in percentage. So here we can see the RE300 and RE150 values as 73.95 and 75.47. Okay. And finally, we can calculate the residual flexural strength, FRN values for N is equal to 600, 300, and 150 using the same flexural strength formula, but corresponding residual loads. That is load at 0.75 mm, 1.5 mm, and 3 mm deflections. So these are the obtained FRN values for deflections of 0.75 mm, 1.5 and 3 mm deflection respectively. Okay, thank you.
Thank you, Ajish.
Yeah.
So we will move on to the next presentation.
Okay.
So the next speaker is Mr. Ganesh Chaudhary, who is the founder of FMG in 2019. And this organization has been established as a consulting and EPC concrete flooring as an organization. He has global experience in designing and building durable concrete floors, launching new flooring systems such as jointless and seamless floors. I now invite Mr. Ganesh Chaudhary to deliver his talk on FRC applications. Can you please share the screen, sir? Mr. Ganesh?
Ganesh, you are now the co-host. I think you can now.
Good afternoon. I think we are reaching. Okay. Okay. Can you see my screen?
Yes, sir. Yes, sir. Confused.
Okay.
Sorry, we are not able to see the screen yet.
Okay. Hello.
Yeah, we are not able to see a screen. So can you share again?
Yeah. I don't know. Now you can see my screen?
No, no, sir.
Should I try making you the host, Ganesh? Yes.
Or can you share the presentation? Maybe I will share the screen and you can present. Mr. Ganesh? Sorry, everyone. I think we lost him.
Sfrc, shall we play the next?
Yeah, I have admitted him. Let's try once more.
Sure.
And
Sure.
then,
Yeah.
can you please make him co-host? Yeah, I have admitted this.
Yeah. I'm back.
Oh, yeah.
Can you see the screen now?
Yes, we can see the screen and we can hear you. You can start the
Super.
presentation.
Sorry, guys. Sorry. Yeah. Okay. Thank you. I will not waste much time. We'll go on to the topic now. So I'm going to talk about FRC applications. We have seen about the material characteristics and the testings and the beam and the calculations. How after the calculation we can implement it to the practice. This is what is my topic about. I'm going to take over the audience FRC applications done with different type of fibers across the globe to the extent knowledge available. So these are various fibers. Yeah. Every fiber works. So we cannot say this fiber doesn't work or that fiber doesn't work. Every fiber practically works. Yeah. But we also should remember, as Sunita said in her lecture, yeah, all fibers are not equal. Every fiber has a different way of performance and it performs differently in the same type of concrete. Yeah. This is a basic fundamental we should keep in mind while using FRC. Because whenever we give FRC conferences or lectures, there's a standard question coming, how much kg we should use. Yeah. So every fiber works, but they are not equal. Yeah. So I have bifurcated the FRC applications in 4 or 5 different applications. To me, FRC is a technology with unlimited possibilities you can use in many different applications. Mostly 60 or 65% of fibers today in the world are used in slab on grade applications. Yeah. So these are just some examples. A normal socket floor somewhere in US for Bridgestone Tire Company. This is Coral Engineering in Coimbatore, where they have used plastic fibers. Yeah. This is again Godrej Agrovat in Maharashtra, where plastic fiber tough strand is used. JCB. These are the projects or these are the applications we as a community should be aiming at. I think Steffi has the question of jointless floor. So this is a jointless floor done in Gujarat for JCB with steel fibers. Yeah. Again, an application with glass fibers and the same applications of industrial floor somewhere in Halol. Again, in Andhra Pradesh, a normal socket floor with steel fibers of Dramix. Mercedes-Benz in Scottsdale. So we are really having applications coming from India or US or many different countries looking for different application. This is composite concrete, which is on a metal deck. Reliance Cash and Carry, I think this is in Ahmedabad with stringent flatness requirement, normal socket floor with steel fibers. A lot of times we get questions that can fiber be used for, the floor with spices or chemicals. This is an example where a plastic fiber has been used for a spice factory, Shakti Masala in Coimbatore. Samsonite, again, super flat floor. I'm sure some people in flooring industry are attending the session with a super flat floor. This is done with steel fibers somewhere in Europe. Yeah. Heavy industrial floors, some factory in China done with steel fibers. These are all about slab on grade applications. Now I move to another applications which is considered as a heavy duty, which is outdoor pavement or a normal pavement on a bridge decking. Yeah. This is an application of glass fibers somewhere in Germany. This is bridge decking. I think most of us have traveled this beautiful place and we must have taken a ride on this bridge. This is a bridge decking is done by plastic fibers in Nevada. Sports centers for a soccer facility somewhere in Kazakhstan, steel fibers. Another application we all should aim at and we should move the fiber industry is the seamless floor. Seamless floor is the floor with fiber reinforced concrete which has no limitations. There are no control joints and construction joints are not seen because these are restraints. So this is the application of seamless floor or combi slab. It was commonly known as before in Kazakhstan. Volvo India, somewhere I think it is near Bangalore, is done for a parking lot. Again, a heavy duty pavement in Barcelona, Spain, done with steel fibers. There are other applications such as composite deck, screed or overlay. Some international and some local applications. We as a country have also gone much ahead into fiber reinforced concrete. There are enough applications done in India, all the applications. Yeah. So this is a composite deck in Hyderabad. This is in financial district. A lot of people must be aware if somebody is attending from Hyderabad. The plastic fiber has been used for composite deck of this structure. I don't know this project. This is in Phoenix. It's an elementary school. Yeah. Again, a concrete overlay with glass fibers. The aim of showing this different locations and different floors and different fibers is you can use every fiber almost for every application. As long as you make right calculations, every fiber can be used. Yeah. Retail store in Bangalore. This is a large retail store with 400,000 square feet of fiber reinforced concrete. The plastic fiber has been used for screed applications. Another fantastic application is facades, where you are going for architectural shapes or you want to create beautiful elements from concrete, where GRC can be used. This is, I think, Sfrc from Jaipur. This is another building, I think, somewhere in Europe with facades. Precast is a new technology, I would say, comparatively less used for fiber reinforced concrete, but there are very innovative applications. This precast wall, Gettu sir already talked about. If somebody is traveling from Bombay to Pune, you can easily see this wall, left side of your wall. This is still standing. I think we constructed it around 2007 or 8. Fantastic application. The customer saved almost 600 or 700 rupees a running meter by doing a proper calculation. Prefab house, a lot of times it is difficult to do use a rebar reinforcement. So this is done with Sfrc in Europe, ready-made houses. Commonwealth Gave in Delhi, the crash barrier was used because they were facing problem. If the crash barriers are constructed by rebar, there was breakages on the corner. So they use steel fibers for crash barriers for Commonwealth Games. Some fantastic applications as precast facades done with steel fiber, very high tensile strength fiber. Precast pipes, a lot of people must be aware. Precast foil, specifically when they are casted vertically, we can use fibers in a very effective way. Structural application, this is the way, this is the next generation, I would say, fiber applications. Something like combined reinforcement in column, reducing entire section of the column, reducing weight on the building, reducing the foundation and things like that. A building somewhere in Japan done with steel fibers. Raft or mat foundations somewhere in Slovakia. And of course, clad rack systems for PepsiCo. There are many clad racks now happening with steel fiber more and more. Yeah. This is another use of fiber reinforced concrete where floor on piles. I think here also in India also places like Oragadam or places like Calcutta where we are not having a proper soil, or we can use this technology in terms of floor on piles. Yeah. This underwater concrete done in Belgium. Tunneling, I think tunneling is the next important and major application of fiber reinforced concrete, also in India, also worldwide. Some examples of projects, Baglihar project in ZP3 using steel fibers. Baglihar project is one of the first projects which started using this technology in India after Bakran Angle project. Yeah. Testing spot get to Sir Sod, Chennai Metro segmental lining with steel fibers. And there are many metro rails across the globe has been done with fiber reinforced concrete, which is France or London. I removed some photographs as Singapore and Australia. This is Dubai. Right now, what expo is going on, it is connected by a tube, and this is fiber reinforced concrete applications. Very important applications for government of India for defense. They are storing crude oil much below the soil level, and I think 13 kilometers inside the soil. Crude storage. Yeah, I'm sure the road which started the revolution of expressway in India, Bombay-Pune Expressway. Many tunnels here are done with steel fiber reinforced shotcrete. Tehri HEP, Tehri hydroelectric projects, also one of the first projects which started the shotcrete FRC revolution in India. Other applications, I got this data from a lot of fiber manufacturers. I could not specify, so I put it into other applications. These are applications done with glass fibers in Bangkok or Tokyo with hotel or rail lines with glass fibers. This is another cable stay and slabs and some sustaining walls for platform done with steel fibers in France. Yeah. These are a bit of a summary of what fibers you can use for different applications in different continents. So as a material, fiber reinforced concrete does not have any limitations. It can be used in a lot of applications in a lot of different conditions. These are last three sides of my take of how we should and we can increase the use of this technology. Yeah. Testing, these are our standard testing we do for concrete, right? It is cube test, mix design, mechanical properties such as compressive or flexural strength, or we use IS 456 or we use IS 10262 specifically for the candidates who are joining from India. Depending on different countries, there may be different standards. Yeah. These are basic hygienic tests for any concrete, but these are not sufficient testing or standards for FRC for widespread use. If you continue using these standards or these states for fiber reinforced concrete, you will never ever respect fiber reinforced concrete as a technology. Yeah, unless you want to use fiber just to make concrete from good to very good. Yeah, which is not an engineering use. You are just putting some material to it to increase the properties. Yeah, what should we do? Yeah, we should always do beam test as shown by Professor Sunita and Ajish. Yeah, We should look at equivalent fracture strength or a post crack performance. We should look at energy absorption if it is tunneling. What standard we should use? If you want to use beam, if you want to use fiber reinforced concrete, irrespective of any fiber you want to use, you should use IS 17161 or even IRCSP for 6 power pavements, or EN 14651, or our document of ICI, which is ICI TC01. Or you are going for tunneling, we should use FNARC or EN 14487. So the test or the process on the left side are hygiene and to be done on the concrete, but based on this test, based on mixed design, based on compressive strength, it is a bit criminal to decide the fiber reinforced concrete performance. How should we specify? Because always consultant ask, how should I specify? I like the material, I like the testing results, I like the performance. How should we specify? Generally, it is very easy to say you put 10 kg of meter cube or 2 kg of meter cube or 25 kg of meter. This is the easy way to say. Or percentage volume, where you are considering fiber as an admixture. But let us not forget, whatever we put kg as meter cube or percentage of volume, these are to enhance the mechanical properties of the concrete, which is not the primary aim of a fiber reinforced concrete. As we said before, every fiber works, but every fiber is not same. So we cannot have a generalized rule. I think somebody also asked, what is the optimum dosage? I repeat here, there is nothing such called as optimum dosage. You need to design your fiber reinforced concrete for the application and for the toughness and for the fiber you are using. What should you check? You should check toughness of fiber reinforced concrete. You should check either FR values, or you check RE values, or you check ductility values. What do you expect from fiber reinforced concrete? A lot of times I see some commercial brochures or some sales comment being made that use our fiber and there will be zero crack in your concrete, or there is no crack, or there is a crackless. These things are very nice and nice to hear, but fiber is specifically a post-crack behavioral material. So expectation from a fiber reinforced concrete is what is the post-crack behavior, and you define that post-crack behavior by conducting the test on the fiber you want to use. What is the applications? So these are the applications we should target at. So this is a project in Surat, Gujarat, India. This is the way you should look at the progression of a fiber reinforced concrete applications. So this is a floor for 65 meter length. There are no joints. So this is the way to use the technology. This is the ways to embrace the technology. I think somebody also asked the question of how much jointless we can do. By technicality, we can do jointless to any capability, seamless to any capability, any square meter. But I think right workable solution, at least in Indian context, is you take 80 or 120 meter cube of concrete and convert that to square meters. So 600 to 800 square meter, irrespective of the dimensions, you can cast. And depending on your dimension aspect ratio, you can decide whether you go for a jointless floor or a seamless floor. So I want to repeat here, technically from fiber reinforced concrete capability, there is really no limit. You can go on casting, but we have a limitation of the concrete supply, how much can be done in 4 or 5 hours, and also the finisher, how much he can do. Finisher is like a painting job. One person can do only so much. So that is the criteria, not on the technical side. Of course, we should move to structural applications like clad rack. And some nice applications like Valencia in Spain, which I am aware done with fiber reinforced concrete, or our nice Mumbai airport with glass fibers. So this is the way I look at as applications for fiber reinforced concrete.
Thank you, Mr. Ganesh. Thank you
Thank
for
you.
showing us numerous application of FRC. It's very informative. Thank you. If you can answer one question,
Yes.
it will be good. So is it possible to replace the FRC or composite SFRC as the main reinforcement? Can we completely replace the main reinforcement?
For slab on grade, yes, 100%. Yeah, 100%. For slab on grade applications and for tunneling, 100%. Yeah. Does it answer your question?
Yeah, you can. Yes. And can you explain any cost comparison, which comparison between fibers is? Can you tell us?
For slab on grade application, as long as your existing section is designed properly, fiber, and you use a right fiber and right design method, you have to save 5 to 10%. Yeah, if you are not saving 5 to 10% of the cost per square meter basis, does mean one, either you are not using right type of fiber, or you are not using right design approach, or your existing design is under design. Yeah, if the fiber was just a technical approach and it was not a commercial approach, the technology would not have success so much. So 5 to 10% is you should look at as a saving from conventional concrete. Okay, apart from the time saving.
Okay, so one more question. Is it possible to replace the composite FRC as a main reinforcement in bridge decks? Is it possible?
I am not capable of answering this question. Somebody from structural, I can answer on the flooring, but bridge deck, I am really not an expert.
Okay, maybe we will take it in the open forum at the last of
maybe
the
Gettu sir or
professor
from US can answer.
Yeah, sure. So we will end this session. We'll have a break for 5 minutes because we are running late. We'll take the break for 5 minutes and we will come back by 11:05.
Okay. Thank you. Thank you, Steffi. Thank you, everybody. Hope you enjoyed.
Thank you, Steffi. Thank you for moderating this session. We will gather here again at 11:05. Now we will be displaying the first sponsor of this event. I request all of you to please go through the details given in the slide.
Sunita, I cannot see any slide.
No, I'm just now is it visible, sir?
Yeah, now it's fine.
Welcome back to all the participants. So let us resume the session now. I hope all of you have had a break. So next we will have the session. In this session, we will have two speakers and there will, three speakers, and there will be two demonstrations. Again, as discussed earlier, we request the participants to post their questions on the chat box. So the first speaker for the session is Professor Gopal Ratnam. He is from the University of Missouri. He has extensive experience on laboratory and field testing of materials and structures. He is an expert in developing test procedures and instrumentation techniques for building materials and developing of modern materials. He is a fellow of the American Concrete Institute and a registered professional engineer in Missouri. He is also one of the pioneers who have started application of FRC technology around the world. And now I welcome him to give his insights on the case study that he will be presenting today. Professor Gopal Ratnam, I have made you the host, sir. I hope you can access the presentation.
Okay, are you able to hear me and see me, and
Yes,
also
yes.
the presentation?
Yes, we are able to see you and hear you.
Okay. I would like to thank Sunita and Ravindra for organizing this workshop and giving me an opportunity to talk. Also, all the sponsors who made this workshop possible. The topic that I chose today was try to address some very unique type of applications. And this is a project that we worked on about 5-6 years ago. It is on designing a special mix for use on wearing surface system for the steel orthotropic deck. And I'll give you a little bit of background of what the structural system is and why we chose what we chose. So as I said, I'll talk a little bit about the background. This project is really a part of much larger project. We were primarily responsible for the wearing surface system choice and design and testing. The larger project involved actually widening of a very well-traveled bridge in St. Louis, Missouri. We have done prior research on this bridge, as well as on bridges in New York and California. And the current research is what I'll focus on, both talking about laboratory testing and field trials, as well as design issues and logistical choice of the wearing surface material. And I'll also show a few slides on the actual construction and report on the service performance since construction. This bridge, as I said, is in St. Louis, Missouri, which is right in the heart of US, both east-west and north-south. It's called a Midwest city. What you see is the landmark St. Louis Arch. The bridge is actually two sets of bridges side by side with about 6 inches gap. So they are independent bridges. Each one supports 4 lanes of traffic. And some of you are familiar with the interstate system. It is the national highway equivalent. This actually supports 4 of those highways, and it supports a state level highway. So it's a tremendously traveled bridge. The bridge connects Missouri, which is one state, to Illinois, which is the neighboring state. And in between, normally in the US, rivers define boundaries between states. So this is a Mississippi River bridge crossing. So that gives you a rough idea of the location and the geography of this problem. Midwest typically is blessed with very horrible winters, a lot of snow, a lot of ice. And so we necessarily have to use de-icing salts, particularly on bridges. And so that also is reason for our structural decisions with regard to chloride penetration and potential corrosion of the steel deck. As I mentioned, this is an 8-lane bridge. It carries I-55, I-64, I-70, and US 40. The US designation is a state highway, and the I designations are all for interstate highways, which is basically federally or central government controlled. Right? It crosses the Mississippi River, and it connects Missouri to Illinois, and there's a very substantial amount of commercial traffic. Trucks would constitute about 60-65% of the vehicular traffic, and these are generally 18-wheelers. This bridge was built in '67. I'll explain a little bit on why the term orthotropic steel deck. The total length of this bridge is a little over 2,000 feet, 660 meters, and its width of both the bridges together is about 104 feet. The longest span is 600 feet, and it has a river clearance of 82 feet. The reason this bridge is called an orthotropic bridge is because of the structural detailing of this type of bridge. It has 2 radically different stiffnesses in the 2 directions. One along the axis of the bridge, which is primarily supported by very large box girders. In this particular cross-section shown, we're showing a 16-foot deep box girder. In many places, it is closer to 20 feet, closer to the support. So you're talking about a very stiff structural member. And then in the transverse direction, you have a floor beam. Let me see if I can. You have a floor beam that is about 3 feet deep. Right? And the bridge is decked by a very thin steel plate, a 14 millimeter thick steel plate. And it is also stiffened by a series of trapezoids. Right? And so the stiffness in the transverse direction is quite different from the stiffness in the longitudinal direction. And this also has an implication with regard to structural behavior. So that is why it is called an orthotropic bridge. In the 60s, steel was relatively inexpensive. So these bridges became very popular type of construction. Today we use plate girder bridges more. And because of this type of construction, the deck, steel deck, is so lightweight that the bridge actually behaves like a trampoline. Right? You have a lot of deflection. And so that also has an implication with regard to the wearing surface. Also in the previous years, that is around 60s, we always thought of the wearing surface as something that is sacrificable every so often, and it doesn't contribute to the structural behavior of the bridge. Okay? After our project, we convinced the authorities that we could very well take advantage of the wearing surface as a stiff composite with a steel deck. Therefore, we can do structural analysis differently. Okay? So the top figure shows eastbound and westbound lanes with a small gap that you can see in between. And the process of this construction and widening involves moving the entire bridge, the eastbound lanes, by about 9 feet. Okay. Let me see if I can get the laser pointer working here. Yeah, somehow I'm not getting it to work. In any case, before we start any of the testing or specification for the materials, we wanted to make sure that we understand what the bridge is currently seeing. These bridges, as I told you, were built in 60s. One of the significant aspects of why we are having problems with the wearing surface is that traffic volume since the 60s has increased 5-fold. Tire pressures that we allow today on trucks has increased more than 60%. And the volume of traffic has increased quite a bit with more of the truck traffic. So that being the case, wearing surface materials are being punished significantly more than when this bridge was designed. Okay? So since this bridge is very complicated to analyze, even using finite element methods, we wanted to see the as-built behavior of the bridge. So we put a series of strain gauges inside the box girders of the bridge. And our goal mainly was to find out what is the tensile stress that we should be expecting on the wearing surface and what potential bond stress issues we are likely to encounter. So we actually left in a computer-based data acquisition system over a 6-week period to gather data on a very continuous basis so that we could create a histogram of strain levels and reproduce them in fatigue tests in the static as well as fatigue tests in the lab. We're also able to do some simple structural analysis for the transverse bending effect. The wearing surface is largely subjected to compression in the longitudinal direction. This is like a two-way slab or a plate. In the transverse direction is where we expect tensile cracking right over all the stiffeners. Right? And the moment you have large tensile stresses, you're also going to have some bond failures in the vicinity of the. So two things that we're interested in: tensile cracking of the wearing surface over stiffeners and bond failures in the vicinity of the stiffeners. And since I told you that this bridge deck is very flexible, we also analyzed using yielding supports because the trapezoidal stiffeners basically deflect quite a bit too. So with a little bit of actual data in hand, as well as theoretical background, we were able to do work on 3 different bridges, all of the same type. They're all orthotropic steel deck, but of course with different geometries. We worked on this bridge, which is called Poplar Street Bridge in St. Louis for a long time, and Bronx Whitestone Bridge, and each one had a slightly different solution because the problems were different and the weather conditions, the climatic conditions were different. California, for example, it doesn't get very cold and it doesn't get very hot too. So the weather conditions are slightly different from New York or St. Louis. In the lab, what we have is a facility to simulate the kind of stresses that we measured in the field. Okay. What you see here is a closed loop testing machine. We have custom built a thermal chamber to go around all the specimens so that we can heat it and cool it to reflect real life variations in temperatures, which in Missouri can go from minus 30 degrees Celsius to about, I'm more familiar, I'm thinking in Fahrenheit and trying to convert it to centigrade, about 150, 160 degrees Fahrenheit on the high side. Okay? Because the deck surface is black, it absorbs a lot of heat during the day. So during summertime, even though the air temperature is only about 100, 110 degrees Fahrenheit, the deck temperature can go to about 150, 160. This is the kind of specimen that we create, used to simulate the stress levels in practice. You have a steel plate on which the wearing surface is placed, and we measure deflection, we measure slip between the wearing surface and the steel so that we can monitor cracking as well as potential bond failures. This is a close-up of a test specimen. What you see here are polymer concrete test specimens that we tested for a bridge in California, but similar things I'll show you for the steel fiber concrete wearing surface. There's a lot of instrumentation involved here, and we measure cracking using changes in stiffness. We also glue a very thin wire on the surface so that can tell us cracking long before we can visually see the cracking. And since it's in a temperature controlled chamber, we have cameras mounted on top of each specimen so that we have continuous access to photographing the specimens as cracks develop. Right? One of the very interesting observations, and this is more by way of background, you see we tested two different types of wearing surfaces for the California project. One is epoxy asphalt, which is this light blue and red line. There are two different specimens to replicate. And what you see is a plot of apparent modulus versus temperature. So you can see here, and the reason we call it apparent modulus because they are back calculated from the composite. So we basically say that steel modulus we know at all temperatures, it is approximately the same. And therefore we can calculate, and that is why we call it apparent modulus. It's not directly measured on epoxy asphalt or polymer concrete, but it's back calculated. What is the important thing here to note is the modulus changes tremendously. When you go to hot temperatures, that is 110, 120 degrees Fahrenheit, the modulus is almost zero, right? Very close to zero. Whereas when you go to the cold temperatures, winter temperatures, the modulus goes way up, about 200 KSI. Unlike the epoxy asphalt, which is very temperature sensitive, the polymer concrete is somewhat less temperature sensitive. But the key thing is at hot temperatures, you have very little contribution. Okay? And this is one of the reasons why we ruled out both any polymeric type of material, because that would not give us the kind of stiffness that we desired for the important purpose of this project. Okay? These bridges are very expensive. Okay? And so if we can somehow, through creative engineering, extend the fatigue life of this bridge by 15 or 20 years, we greatly allow us to stagger investments in infrastructure, because all the bridges on the highway system were built around this vintage, late to mid 60s. Okay? And so all of them now need rehab or repair. And we don't have the kind of resources to invest in all of them. So if we can buy more time through creative engineering, and that is why we started looking at alternates. So one criteria is that we do not want the wearing surface to be so temperature dependent, because we wanted the wearing surface to essentially contribute to the structural behavior of the bridge. Right? This is a slide that tells you, based on mechanics, if our modulus is high, the blue is the wearing surface stress, red is the steel stress. So if my modulus of the wearing surface is high, right, at the left end of the graph, I can reduce my steel stress by almost an order of magnitude. So if I reduce the steel stress, my fatigue life of the bridge can be tremendously enhanced. So this is one convenient way where we think of the wearing surface not as a functional only member of the structure, but as a functional as well as structural member. Right? So our goal is to provide a higher modulus material that is not very temperature sensitive and that is not very rate of loading sensitive. Okay? At the same time, one should recognize that if I add a wearing surface that is very heavy, it contributes to the dead load and therefore it takes away from the fatigue life performance. So there's a compromise between density of the wearing surface and its mechanical performance. And that is why instead of just choosing steel fiber reinforced concrete, we chose lightweight steel fiber reinforced concrete. Okay. So this is the rate of loading effect on epoxy asphalt. At the hot temperature, you see that there's not very much rate sensitivity because the modulus is very low to begin with. At room temperature, there is a significant rate sensitivity, and at cold temperatures, the rate is also there. So we don't want rate sensitivity, we don't want temperature-related effect, and we don't want a heavy density. So we do also understand that there is an effect on the wearing surface itself with regard to the thickness of the wearing surface. So we had multiple parameters that we had to carefully navigate in designing this wearing surface. So we looked at various type of field tests and lab tests. I'm not going to go through the details here in the interest of time. One of the things for bond, we want to make sure that with continued traffic, the deterioration of bond is not there. And so we do pull-out tests where we actually drill a core all the way up to the steel and then bond it to a pipe cap. And using a load cell, we measure the load diffraction characteristics of this pull-out. And depending upon the type of failure, we can say if there has been some bond deterioration. Okay, you can see that test being done on the bridge for different wearing surfaces. Also, another test, we talked about tensile cracking criteria. We do what is referred to as a resistivity test, where we use water with a few drops of detergent solution to make the viscosity very low so it can penetrate very thin cracks. And then we try to measure the resistance between the top of the wearing surface and the steel deck. Okay? We do this also in the lab tests. So the mandates of the new wearing surface are to stiffen the deck, thereby reducing the fatigue stress in the steel, make the deck less temperature dependent, reduce the rate of loading effect, reduce the deck weight, and reduce potential maintenance effort and cost. And that is exactly where we came up with the solution of steel fiber reinforced lightweight concrete. In addition to these, there was also a question of being able to place it with the bridge in service, meaning they would basically close only the lane that we are constructing the wearing surface on. There will be traffic on. So they wanted concrete that could be pumped. So there was mixed design challenges there. We need to make sure that it can be pumped well over 30 feet so that we are in a position to control the traffic The lightweight aggregates that we used or we settled on was expanded shale. And you can see the weight density. So it was about half the weight density of conventional coarse aggregates. Just to give you an idea, this is the mixed design. Although we did all the mixed design, in the contract, if a contractor could prove to us that he meets the performance specification. So we are not specifying the fiber type, we are not specifying the fiber dosage, we are not specifying anything. What we are specifying is the concrete compressive strength, the tensile, the flexural ductility performance, the density, the temperature sensitivity, and chloride penetration tests. So those were the specified thing. As long as they can meet those goals, any mix that they come up with is okay, and they have to prove it using validation tests. This is what the mix looks like. It is a very high volume fraction fiber, 2% by volume, which is quite unusual. We used 38 millimeters fibers and the aspect ratio was 41 inch. These fibers were crimped. We created laboratory specimen. Although this fiber reinforced concrete could be used without any shear connection to the deck, Missouri Department of Transportation is a very conservative department. So they did not want to rely on my advice for the wearing surface to be placed directly on the, so we had a metallized zinc coating and we had shear studs and additional continuous reinforcement so that they were concerned about this wearing surface coming out in small blotches. Right? So this was what we did in the lab. You can see some without any steel reinforcement, some with steel reinforcement, just to reflect what Missouri devotee wanted to do. In principle, I personally feel that the wearing surface does not need any reinforcement in this application. Right? We did all the usual tests that Ravindra and Sunita spoke about: compression test under closed loop conditions, flexural toughness test. So this would be the kind of response that you get. This is a 14-day test. We had a specification of 6,000 PSI, which is about 40 megapascals at 28 days. And these are two of the actual mixes. This is silica fume mix, SF, and TB is a ternary blend with silica fume and fly ash. So you can see both of them perform comparably well. We wanted to make sure that whatever supplementary cement material that the contractor uses would all be able to achieve the type of performance that was desired. Right? Again, these numbers specifically are not very important. They are important for the design and performance, but in terms of this presentation, we had a series of specifications and we measured all of these properties. One of the issues was with regard to toughness index. We used a standard that is now defunct, but also it gives contractors a very nice practical way of thinking. I5, for example, this is from ASTM C1018. I5, if the index is 5, I10, if the index is 10, and I20, if the index is 20, essentially represents an elastic plastic behavior. So post-cracking, it is an essentially flat plastic behavior. So if I got I5 numbers larger than 5, I10 numbers larger than 10, or I20, so it is doing better than elastic plastic behavior. Right? So we had all the specified, and this is a typical result as you've already seen multiple times this morning. You can see that the post-cracking stiffness and strength carrying capacity is quite significant as a percentage of the ultimate capacity. And so we did all the tests on mixes that we thought would work before specifying. But as I said, the contractor is free to choose any mix that meets this. So it's basically a performance specification based. I can quickly go through some of these because these are not so important, but we just duplicated the tests on structural systems, both to represent one-way action as well as two-way action of these slabs. So we tested a beam and we tested a plate. This is actually, the contractors were pretty skeptical when I told them that you need to put in 2% by volume of fibers. They said it's not doable, but we designed a mix with proper amount of superplasticizer and air containing agent. And therefore, we actually ran a demonstration project because they wanted proof that it'll not give them trouble on the bridge. So we actually had trial pours of two mixes, one with fly ash and silica fume, one with just silica fume. And you can see the trial. And they were very convinced after this and confident to implement this on the bridge, because the cost of messing up the bridge job would be tremendous on them. This is the bridge deck. The old wearing surface has been removed. We use shot blasting. Okay? You can see that because of water vapor in the atmosphere, you can see a little bit of rusting after the shot blasting. But we continue the shot blasting till we actually apply a coat of zinc. Okay? So this is a metallized zinc. And these points that you have are so to keep the steel clean for welding of the studs. Studs are being welded. As I mentioned, studs and steel reinforcement are not necessary at all, but because of the highway department decision to go ahead with them, we agreed. Okay? So this is an overkill really in terms of connection, shear connection to the deck. This is where Sfrc is being placed using pumping. This is the finished product. Often we have to work through the nights to be able to minimize the amount of traffic disruptions. So to conclude, I would say that the wearing surface was effortlessly placed. The design thickness varied from 2.75 to 4 inches to accommodate transitions. Remember, this is a 9-lane bridge, so we had to work with the traffic, and this material provided all the flexibility that we needed to be able to do all of this without disrupting traffic. Field tests were run immediately following the construction. The only specification that was not met exactly was the chloride permeability, and it was waived by inspectors primarily because we asked them to use lightweight aggregates, and lightweight aggregates are inherently porous. Okay? So if they did not meet chloride permeability by much, we waived that option. But they were able to meet ductility, compression, crack resistance. The contractors really were thrilled because they had one more material in their arsenal. And they were convinced that 2% volume fraction can be placed provided we have good mix design in terms of workability. A very limited number of, now we have about 6 years, 7 years of experience, a very limited number of hairline cracks, which is largely due to restrained shrinkage cracking from thermal loads, and none of which are structural concerns. And the wearing surface performance is excellent. And so this is like a model for many other states to implement. I'll stop here, and if there is time, I can certainly address any questions that you might have.
Thank you, Professor. It's a great case study for a revelation by itself. A couple of questions are there, but just before that, let me ask one question. The use of lightweight aggregates must have had an effect on the modulus, right? So you are saying that the addition of fibers has increased the modulus? Is that what you're saying?
No. All I'm saying is the modulus is much higher compared to polymeric wearing surfaces.
Okay.
So the modulus is of our usual concrete type of modulus, about 3 million PSI.
In spite of using lightweight aggregates.
Yes, yes. And that is because we worked on the paste content very well. So we could achieve 6,000 PSI, which is 40 megapascals, even with use of lightweight aggregates, significant use of lightweight aggregates. The concrete density, the steel fiber concrete density was about 2/3 of normal. So about 1,800 kilograms per meter cube, as opposed to 2,400 kilograms per meter cube.
Oh, thank you. Thank you, Professor. Now I will take a few questions from the audience. There's one question, is the fatigue resistance enhanced more by fibers or the fly ash and SCM, or a combination of both?
The impact and fatigue resistance is tremendously increased by the use of steel fibers, and particularly at 2% dosages, it is really several orders of magnitude better in terms of energy dissipation. So yes, that was one of the primary reasons, because as I told you, this wearing surface is very flexible, and therefore the wearing surface, this deck is very flexible, therefore the wearing surface is punished quite a bit. So we needed a material that withstands that level of fatigue punishment.
Okay. Yeah, there was one question in the previous presentation which was related to bridge decks. So I will take it now.
Okay.
So an audience had asked, is it possible to replace the composite fiber reinforced concrete as a main reinforcement on bridge decks? Yeah, I think.
Do you want me to answer? Do you want?
Yes, sir. Yes, sir. If you could.
Yeah. This issue was quite a bit of interest to you, to us when we were doing fiber reinforced concrete. If you use fiber reinforced concrete in addition to continuous reinforcement, that has been done, the role of fibers essentially becomes quite different. It does do all the advantages that we talked about so far, but in terms of structural behavior, fibers do much more in the compression zone to confine the concrete when you use it along with conventional reinforcement. We actually have a procedure and a paper published on this, that we get the benefits of tensile behavior that we discussed so far, but in a structural application where continuous reinforcement is used, we really need to account for presence of fibers in the compression zone, which is very similar to confining the concrete, which greatly increases the ductility as well as the strength of conventional reinforced concrete.
Okay, but we cannot replace the conventional reinforcement.
Yes. No, we cannot replace the conventional reinforcement, but the mode of analysis is very clear when you use it along with fiber reinforced concrete. So you will use the tensile capacity, but you'll also use the confining effect in compression.
Right. So this also answers the question on the same lines. There was a question on whether we can replace the conventional reinforcement in beams. So it is almost the same.
I'd qualify the answer further. In many applications where fiber reinforced concrete is not used in a structural capacity, like pavements, you can eliminate steel reinforcement. But whereas it's being used on, let's say, pavements where there's a potential for washout because of bad subgrades, nominal conventional reinforcement should be used, because then the pavement becomes more like a beam. Right? So where there is flexural strength needed, you cannot replace conventional steel.
Yeah, that brings a lot of clarity. I think, thank you, Professor. Maybe if there are a couple of questions and you would join at the end of the sessions in the evening, we can take a couple of more questions.
Sure, I'd be glad to. Thank you.
Thank you. Thank you very much. Now we have a demonstration session next on the notched beam testing. Steffi, would you please take over?
Yes, ma'am. Yeah. So let me share the video. Can you see my screen?
Yes, it is visible.
Okay. Hello everyone, I'm Steffi JST. You can hear also, ma'am.
Yes, we can hear.
A postdoctoral researcher working in the Department of Civil Engineering, IIT Madras. Today I'm going to show you the casting procedure of fiber reinforced concrete. The procedure is pretty much same as plain concrete, but how you add the fibers make a lot of difference. So that I'm going to show you today. So I welcome you to the lab. The fibers are added into the concrete after the water and superplasticizer are completely mixed into the concrete. It is important to add these fibers very gradually into the mixture. Adding it very fast or dumping the fibers into the concrete all at once can cause fiber balling, and hence it has to be avoided. So it is very important to gradually add the fibers into the concrete mixer. So once you get a uniform mix, you can remove the concrete from the mixture and place it in the molds of dimension 150 by 150 by 700 mm. Now carefully observe how the concrete is placed on the center of the beam first, mold first, and then on the sides. And it is preferable to use a table vibrator to compact the concrete. And you have to vibrate the specimens until the concrete is completely leveled, and the vibration time should not exceed more than 20 seconds. So now the concrete is made, fiber reinforced concrete is made. So we will keep this concrete for 24 hours to set, and after the concrete has hardened, we will put these concrete specimens in the mist room for curing until testing. So now I will be explaining how to notch the specimen before testing it. So 3 days prior to test the specimen, you have to cut a notch and then keep the specimen for curing, so that if there is any thermal crack, it will heal. That's the reason we are going to cut it before 3 days of testing. Width of the notch will be 3 mm and the depth of the notch will be 25 mm for a size for beam of size 150 by 150 by 700 mm. This particular procedure is taken from EN 14651 and Rylem TC 162. So now let's see how the notching is performed. Now we have brought the specimen, 28-day cured specimen to the lab for testing. So the testing will be carried out on a closed loop control system which uses a displacement control as the control parameter. Okay. The size of the beam is 150 by 150 by 700, which complies to the EN 14651 and Rylem TC 162. The objective of this test is to determine the residual flexural strength of the concrete, which can be used further in the design. This beam is cut at the center for notch, and I have placed the beam such that the loading surface is at the bottom and the notch surface at the top. So how do you decide which surface will be the notch or the loading surface? Is the casting surface. So the casting surface should be always perpendicular to the notching surface. Okay. So the notch is cut at the center of the beam. Thereby we are making this plane as a weak plane, and the crack will originate from the notch. Okay. And we have placed a knife edge on across the notch area, and this knife edges will be used to host the clip gauges. So this clip gauge will measure crack mouth opening displacement, which is otherwise known as CMOD. So as the beam is deflecting, a crack will originate from the notch. As this crack widens, the clip gauge will open, thereby the crack mouth opening displacement will be recorded. This crack mouth opening displacement, otherwise known as the CMOD, will be the control for this complete test. Further, we have two LVDTs which will be attached to the either side of the beam, so that we can measure the mid deflection. And this markings on this side, both the side, is to host the LVDT using the yoke frame. Markings is separated by a distance of 500 mm, which is the span length. Now I have rotated the beam so that you can see the loading surface, and we have also marked the loading point, which is at the center of the beam. Okay. Now let's move on to the loading frame. Let's see the loading frame. So the loading frame has two rollers at the bottom and one roller at the top. You can see that the top roller is able to swivel in the other direction, and one of the bottom roller is able to swivel. This roller is separated at a distance of 500 mm. Now let's bring the beam and set it up here. Now the specimen is mounted on the frame. The specimen is placed such that the notch is at the bottom and the loading area is at the top. Now we will attach the clip gauge onto the knife edge. Now we are placing the LVDT onto the beam by means of yoke frame. A T-shaped rod is attached to the yoke frame, which will host the LVDT. This is an acrylic holder which will be attached to the T-frame. To hold the LVDT in place, we are keeping a metal plate so that the LVDT doesn't go inside the notch. This is the final setup of the beam with all the LVDTs and clip gauges kept in place. Now the clip gauge and LVDTs are connected to the data acquisition system, and now let's check if the connections are proper. First we will start the testing under load control at a loading rate of 100 Newton per second until the load reaches 20 to 40% of the expected peak load. Then we will switch on to the CMOD rate control at a loading rate of 0.05 mm per minute, which is equivalent to 0.83 micrometer per second. So after the test, the CMOD reaches 0.1 mm, we will be switching the CMOD to a loading rate of 0.2 mm per minute gradually, which is equal to 3.3 micrometer per second. At this stage, you will be seeing a crack occurring from the notch surface, and you can see even though the crack has widened to a larger extent, the test is being controlled in a stable manner. So this is the importance of controlling the test using CMOD rate control. After this CMOD has reached at a level of 4 mm, the test will be terminated and the data will be saved. Thank you. So now I will move on to the analysis part. Can you see my screen?
Yes, yes, we can.
So this is the output from the test. Okay, so this is the output that we will be getting from the test. So it has load results and displacement. This displacement channel 8 will be our clip gauge output. So these two values will be copied to the Excel sheet. So we are copying it here. So load will be copied here. And output from the clip gauge is also copied. So after copying it here, you have to convert the CMOD. This CMOD, whatever we are getting from the output, is measured at a height of equal plus the clip gauge. The knife edge. So the knife edge reading also. Sorry, someone has gone. So the CMOD output, whatever we are getting, is the CMOD at a height plus the knife edge height. Okay, so we have to convert it into the CMOD value at the notch depth. So we are using this formula where the CMOD y is multiplied by the depth of the beam. The depth of the beam is 150 mm divided by depth of the beam plus the thickness of the knife edge. So the thickness of the knife edge which was used in the experiment was 5 mm. So we are using that to calculate this CMOD, and this is all converted to mm. And you can see this is the result, like load CMOD graph generated from this result. To determine the design parameters, we have to find the LOP. LOP is the limit of proportionality, which is determined from the FL. FL is the peak flexural strength. So the peak flexural strength, the first peak flexural strength, which is always taken within a CMOD level of 0.05 mm. So within the 0.05 mm, what is the peak strength? We will have to note it, and that value will be used to calculate the LOP. So FL, so here if you note down, the FL value is different from the maximum total strength because it has a strain hardening behavior. The maximum strength of the concrete is higher, but FL is little lower. And this value is used to calculate the LOP. So further, to calculate the residual strength, what you have to do is we have to see the load, flexural load at different crack openings. So the crack opening level at 0.5 mm, 1.5 mm, 2.5 mm, and 3.5 mm. So what is the residual load? The F1, F2, F3, and F4 is noted, and that value will be used to will be put in this equation to calculate the residual flexural strength. So like this, you have to do for minimum of 6 specimens, and the average of these values will be used in the design. So thank you. With this, I'll stop sharing.
Thank you, Steffi. So if there are any questions, yeah, there was a question where they have, there was an audience question in which they asked, can we use 100 by 100 by 500 mm beam for the test?
Yes, you can, but you have to scale it down accordingly. All the notch depth and the span length, everything should be scaled down accordingly. Yes, you can use.
Okay. Another question is, instead of notch cutting by using concrete cutter, can I make a notch while casting?
Yeah, people have done that, but the problem with that is the fiber could orient and it can, at the notch, the fibers tend to orient themselves. And so you may not replicate the actual behavior. So it's better to cast first and then cut the notch.
Code number.
Okay. So there are no more questions in the chat box. So thank you, Steffi. Maybe if there are more, okay, just one more question. How the fiber aspect ratio is going to affect flexural strength? Sorry,
So,
flexural toughness.
Yeah. So depending on the length, the fiber aspect ratio is nothing but length by diameter. So if the length is higher, it has more anchorage. So it can actually resist crack width of higher value. So aspect ratio plays a major role in terms of length. If you see the length of the fiber, if it is higher, the toughness is also higher. But short fibers will mostly used in shrinkage applications, whereas longer fibers, macro type fibers, are being used in structural application.
Thank you, Steffi. Thank you. Yes, yes. I think that's it. If there are more questions, we can take it later.
Yeah, sure. Thank you.
Just one more question. Shall we take? Ma'am, getting CMOD is difficult. Is there any other? Is there probably it is asking any other characteristic?
You can do by using deflection method as shown by Sunita ma'am. Yes, you can use displacement control as well. Yes.
Yeah, but then you'll have to go for an unnotched specimen.
Then you have to go for unnotched. You can't no more go do the notched specimen. Notch test.
Thank you. So we'll go to our next speaker. Thank you, Steffi.
Yeah, thank you.
So next we have another interesting talk from the industry by Mr. Mukesh Kotyal. He is a person of practice and is the quality head of the transportation division of Mega Engineering and Infrastructure Limited. He has vast experience in implementing many projects with shotcrete technology, and he's also an expert in tunneling and executing projects in extreme weather conditions, repair and construction defects, and underground projects. Now, I welcome Mr. Kotyal to give his presentation. I will stop sharing and I will make the co-host. Mr. Kotyal, could you please just confirm whether you're able to access? Mr. Kotyal? Hello? Am I audible to you, Mr. Kotyal? Just give me a minute. I will just check up on you.
Okay, ma'am. File to me.
Yeah, we
Welcome,
can hear
Mr.
you.
Kotial. Yeah. Hello, Mukesh.
Hello.
Yeah,
Yes,
we
ma'am.
can hear you.
Okay. Are you?
We are seeing you. We are seeing you on the video. Could you please try to share your screen? Yes, yes, we are able to see your screen. Yes, we are all set. Please go ahead.
Good afternoon. Thanks to faculty, Ravindra sir, Salih sir. Today I'm going to brief about the short kit. What is short kit actually? Design parameters, how to make it successful in any weather condition. What is the actual requirement? How to make it successful, and the engineers at site to understand the short kit and its rheology, the material testing, its practical aspects, and the equipments and techniques and the temperature factors. It all will cover in this lecture. So first, the short kit. Introduction. The first spray concrete job were done in the United States by the cement gun company Altown as early 1907 with the spray concrete product name Gunite, using simple to operate compressed air driven pump similar to that in figure. You are watching this figure which was developed by the Altown company 1907 with air compression and the dry mix type of material which they have spray into the surface. Spray concrete mortar is a mixture of cement, silica, fiber, aggregate, additive, and water pneumatically projected at high velocity on the surface and compacted by its own momentum. With respect to specifications, certain criteria should be fulfilled. As we talk about the short kit, but as per the present, today we are using which kind of short kit, like dry short kit, wet short kit, the plan, the fiber, the synthetic fiber, the other kind of fiber. They all have different purpose and the different aspect where we have to use what is the requirement. These all will govern in this lecture. With respect to specification, certain criteria should we fulfill, which shall we cover into this topic to ensure the construction area is safe. Why we prepare the short kit? Because today our constructive approach, whether it is a transportation tunnel, whether it is a railway tunnel, whether it is underground, there always be a progressive approach we have. So the construction area is safe without any further delay after blasting, stand-up time, crack control, face stability, careful excavation and design support in drop. The excavation to be carried out a step of certain distance. If there is different kind of geology, we have to take care and we have to support it as per the geology and ground condition to take the proper support. So the short kit is to be applied as per the requirement or as per the direction or the designer has taken into the consideration. What is the benefit of this spray concrete? Increase the load carrying capacity due to redistribution of stress. Next, two kind of short kit has been sprayed so far: dry short kit and wet short kit. Presently, also in India, the dry short kit is being used where what is the dry short kit? Basically, pneumatically covered short kit in which most of the mixing water is added at the nozzle. Advantage can we spray without equipment? Like we don't have the circuit machine, we don't have the sufficient crew and like plants and setup. So we can go with the dry circuit. The dry circuit having the low cost because the dry circuit machine can be obtained easily and can be made at site. So it can be sprayed by a local arrangement. And there is where the accessibility approach or the condition is not feasible to move the transit mixture, mobilize the circuit machine, we can spray the dry circuit at any surface. Next is wet mix circuit. Circuit wherein all ingredients including water, chemical fibers and mixing in the batching plant. It is also pneumatically sprayed onto a tunnel surface. This wet mix circuit having good advantage, we can say everything is controlled more precisely and proper design mix is being followed at site. Effective and more production with proper design mix. We have to take a schedule in a day, like 200 cubic meter or near whatever we have scheduled. We can spray by deploying so many machine and the arrangement we can make. We can do faster progress by the wet circuit approach. I have a video to show what is the circuit, how we spray at site, because today Ravindra sir and the other speakers spoken about the design parameters, the specification, the requirements, the other detailing. But I will brief about the circuit, how it looks, how we have to control what the design parameters to be set, and what is the essential requirement while designing the circuit at site, while applying the at site. We have just a video and just the circuit mix after making the design. It looked like this, and it is a robotic arm automatic high-end machine with the transit mixture we have supplied at site. The circuit is going into the pump, then it will go and spray at site. It is a tunnels where the ground condition is not so good, but the operator is very high skilled and he is spraying at optimum pressure at site as per the site condition. The dosage of chemicals, how he is controlling, it is showing in the screen. The air pressure is showing on the screen. And at site, what is the essential requirement like curing and other works is going on parallelly to the circuit because it is very essential. You can see on the screen. The curing is very important because when we spray the circuit after 2-3 hours, curing may require, because after adding the accelerator, the circuit get more hydrated and the hydration process rapidly start. So we have to give sufficient curing so that the surface area of the circuit and the surrounding mass would be more strengthened, and we can say the circuit is taking the load by taking its all benefit by curing. Now, what is the other parameters to take the decision how to make a good mix design? There is the most suitable curve. Before thinking for circuit, first of all, we have to make the good material, durable material, and to establish the mechanical properties of aggregate should be sound, durable. 10 mm aggregate crusher sand FM between 2 to 2.8 is best combination to meet the Austin curve or FNR gradation curve, which is essential. Without this gradation curve within the envelope, and the without matching the 2 to 2.8 fineness modulus, we can't make the proper mix design. If our aggregate and sand is not making compatible, or as per the required envelope curve is not falling into the same, our other properties cannot be established until unless it is not being into the same. Previous experience, there was crusher sand like this, the 10 mm has been added, but there was a gap gradation. We have tried to blend it, but it was again not falling into the curve. So we have taken some expertise of crusher, like deploying some additional equipment or recrushing and making some particles into the crusher sand, so that the combined gradation should be within the envelope. When the combined gradation is like this curve, maximum minimum from the EFNR or the Austin curve. If it is successfully, then it is okay. And the requirement to establish such as workability, requirement strength, and energy absorption capacity. This is the material, entire material which we use into the sort kit. And there is the cement. We should try optimum cement content to achieve our requirements. Where the weather condition is normal, we can go with the so many trials at lab, and then if the confirmation of the all parameters, then we have to use at site. Until unless our requirement is not meeting, we cannot go directly at any kind of content of cement. We cannot fix it. This design mix which you are watching, this is the based on the experience and so many years into this field. The silica probably give the better workability, consistency, and the durability. It is not to increase the strength, but it have to pump the better pumpability, better mix into the surface. The PCB admixture 0.8 to 2% is sufficient. HCA, we will discuss later on this lecture. Crusher sand and 10 mm should be 55 to 65, the crusher sand. If our fineness is more, our mix will be nicely stay on the surface, but it will not give you the correct core strength, or your energy or other flexural strength or toughnesses will not be achieved on the higher side of fineness of the crusher sand. If you have the sufficient amount of filler material like 10 mm, 35 to 50, it has been experienced and we have the results. So it is good, recommended 35 to 55 to be adopted. Or you can do the trials on which percentage dosage of aggregate, amount of aggregate and sand is making the curve, and your results is satisfactory, you can follow the same. But it is a general experience. WC ratio, not to go at higher side, it should be limited between 0.32 to 0.37. It is my personal experience. If we go beyond 0.32, your cement content will be higher. If you go beyond 0.37, your water content will be higher. Your strength or energy will not be achieved. And the workability at plant or at the initial stage should be 160 to 230 mm. It is the best established retention, and it should be at least 90 minutes as per the codal provision. But if you are going with the HCA, you can make it. I will brief in detail further with the other slides. So you can take the retention up to the desired period. In the sort kit, basically there is a 3 J class. What is the J class? The J1, J2, J3 indicate the application of sort kit as per the ground condition. Application when sort kit must be placed as quickly as possible in the thick layer in flow of water observed and stresses occur. J2 applicable when early active rock pressure is present. J3 applies only to exceptional cases. High early strength generally lead to reduce strength increase at later age. So this should be meet while considering the design of sort kit. Requirement as per specification. Being an engineer, being a practitioner or a designer, as a consultancy lab, as a professional engineer, you have to think about the requirement, what should identify, how to make the mix, what parameters should consider before designing to shortcut. Criteria for shortcut, or you can say spray concrete, formally you can say shortcut or spray concrete design and anticipated the requirement before application at site, which should be verified through pre-construction testing. What is pre-construction testing? The material, the ingredients, the parameters, the manufacturer recommended guidelines, the material, what, how, and what is their properties should be established, should be checked, verified from third party as well as in-house. So you will be sure your material, how is their properties, and what the benefits you are getting and looking for, such as loss of strength due to use of accelerator. Your accelerator play a vital role. If you add X amount of accelerator, your strength will be influenced by the accelerator. Influence of air pressure by air, as per the different kind of rock mass or surface, your strength will be depending upon the air pressure. Spray concrete mix should be confirmed the following: all material independent test, pre-construction testing. Strength without accelerator, you have to test it, analyze, establish the gradation curve and workability. Earlier, as we discussed about the gradation curve, it is mandatory. If your gradation curve is not satisfying, your strength, energy, and no parameter can be matched. The workability, you have to take the decision which kind of chemicals you are using, which is the mode of your placement, and how many time you want to make the mix as a retention, your transportation considerable, your application time. Sometimes you spray within 5 or 10 minutes of time, sometimes you need 2 or 3 hours. So you have to establish before application or doing at site. Early strength J class, Hilti, short bolt, and pull-out test. It is also mandatory for early is or green stage of shortcut. If your early strength is satisfying at the appropriate dosage of accelerator, chemical, and percentage of chemicals and aggregate, if it is satisfied, then it is okay. Core strength from 1 day to 28 days or 56 and 90 days if required by the designer, or if you need to evaluate or assess your 1 year or have a period of strength, so you can make it or check it for your one study also. Energy absorption capacity, you have to make the sufficient fiber content, how much energy you have to be achieve at recognized period, so you have to add it accordingly and test it. It is the mandatory criteria. Flexural strength and toughness, it is basically testing in steel fibers only, where the steel fibers or polypropylene fiber also you can do index I5 I10. So your index I5 I10 you can you have to do it in situ strength 0.8 to the characteristic strength. You have to establish fire resistance as per ACI. You have to do in case of the design has been done for final lining. Then codal provision. Codal provision for short kit, you have to consider loss of strength. You can see here, if you have M25 grade of short kit, your strength should be targeted 42 MPa because loss of strength and influences of air. So there is a huge requirement of influences and the loss due to chemicals. So if your strength for C30, C means grade, 30 means characteristic strength, so your requirement will be C38. Here J1, J2, J3 curve, as per your requirements, you have to be achieved. It is as per the Austin guidelines. Also, there is a measure when you have to take the core from site. The code is mentioning ACI 318, 48 hours to be taken into the curing, and after 7 days it should not be tested. for in situ core sampling. Somewhere the engineer insists to take the sample immediately and test it, but it is a wrong practice. For FNR specification, they also mention that if the grade or the cube strength is 40, then your cylinder specimen strength should be 0.8 of the characteristic and 0.84 for in situ sampling. Establish accelerator doses. Cement accelerator compatibility. To establish the dosage of accelerator, the cement accelerator setting test to be performed on different doses before trials. You have to keep in mind when you are establishing the shortcut design, you have to check the accelerator with the relevant cement to which you have proposed, what the dosage is suiting your cement, like 4, 5, 6%. So your initial should be below 4 minutes and the final should be below 8 minutes. And if it is achieving, then there is no issue. Cement content versus rebound. Rebound of shortcut is key factor to assess the performance of mix, quality of accelerator, efficiency of equipment nozzle. It all influence the mix, how you have to make it, and then your overall rebound. Like you have to spray 5 or 10 cubic meter shortcut in 2 meter of length, and you are actually supposed to spray 2 cubic meter, but you have sprayed 10 cubic meter. What is the problem? Maybe your cement content, maybe your material and equipment is not appropriate, which is resulting better poor performance. So you have to analyze and improve your skill, your nozzleman skills, equipment efficiency, and proper design mix. Due to insufficient cement, the strength cannot be achieved and influence the rebound. The following to be considered: optimum accelerator doses. To be used, high doses may lead to reduce the final strength. In case of optimum, means less dosage you are using, your dosage your rebound may go higher. If your percentage doses go higher, 8, 9, 10%, your energy and your final potential strength will be low. So you have to be keep optimum side of the accelerator and establish, and it has to be follow always, not a single time. If you use higher size, you will certainly make the surrounding ground mass strengthen and faster progress you can do it, but as a final the strength and energy capacity or other parameters may not achieve. Optimum cement content and silica dosage help in less rebound. You can see the 375 to 450 kg cement as per the manufacturer guideline is given. Like your wall is there, 7% will be rebound, while like overhead 15% will be rebound. Like minimum cement content, your rebound will be higher. So cement content can be decided based on your aggregate quality, your overall equipment efficiency, your nozzleman skills. These all make your mix design beneficial as well as importance of the application. Admixture and additives. Admixture, second generation polycarboxylate ether polymer with high early strength is suitable admixture. Right now, the admixture which is being used, normal plasticizer, is not recommended for high grade and fiber shortcut, because you need the shortcut beyond the time. So you need high quality PC based chemical. Mycosilica is basically benefited for the cohesiveness, energy, increase the strength, not directly increase the strength, but it make your concrete more dense and low permeables and better pumpability. It is like that. Hydration control additives. Spray concrete mix can be used for longer retention as per anytime ground condition requirement. The sign is unique non-chloride chemical system which control the dynamic of cement hydration by suspending the hydration process, the reactivating the hour even day later, no loss of quality of shortcut. When dispensed into the water mix, batching plant if fully stabilize the hydration process, forming a protective area around the cement particles. Hydration control will establish work with the all cement particles C3S, C3A, C2S, C4AF, and gypsum. Better scheduling, easier to planning. When very poor condition, poor ground condition is being executed, the doses may be established. When you are spraying the shortcut, you have to keep in mind whether your mix is compatible or suitable at that time. If it is within the limit, there is no adverse reaction, because if you go more than 3-4 hours without adding HCA, your shortcut strength will not be there. So you have to think about it. And the next slide is about that. Hydration control additive are important in long tunnels, as well as the duration transportation where is required. Where 1 to 2 hour traditional mix you have to use, there is no issue. 90 minutes or 120 minutes you can use, and with normal pasteuриzer. Where with the hydration control additives, you can make the mix up to your desirable period, 3 to 72 hours. You can make it standby at site in an ATM ground. Tunneling method, there is when the poor condition of geology or tunnel is being excavated or is in progress, you have to keep the shortcut available at the face. Once, or in case of any loose fall, any problems happen, persist, you immediately remove the excavator or the change the activity. You may apply the shortcut immediately on face, so your face will be more safe and you can go further. Testing and requirements. The shortcut basically required the fineness between 3,500 centimeters per gram to 5,000 centimeters per gram. The fineness should be there. The blend value of cement. The C3 tricalcium aluminate should be more than 7. The spray concrete temperature, where the extreme condition more than 13 is recommended, and where the normal condition 15-20 degrees, there is no issue. Workability should be 160 to 30 at plant, and at site it should be preferably 150 to 200 at site at the time of pouring, to make the better mix, low pulsation, and best performance, best application. So it is the recommended slump. Air pressure, some manufacturer of equipment says 6, 7, 8 bar pressure is recommended, and the operator sometimes, engineers sometimes follow the same sequence, but it is not like that. As per the poor rock condition, the operator should know the less pressure is desirable and the less thickness at least 7 days for shortcutting. Testing the early strength, you are watching that penetrometer, you can determine by that. And this is the shortcut tensile bond strength. The compressive strength of a green shortcut can be measured. You have to pull out the tom and the force, and the whole of this tom out area can be calculated from this graph. This is the accelerator and feasibility trials. The panels and the boxes are here. For pre-construction testing, you have to spray it, and it is the core sample taken from them, and it is inside. When the work is going on, you have to review time to time the mix. If required, you can change the design also as per their requirements. Accelerator, high performance alkali-free accelerator, 4 to 8% to be used. It is best. As per my experience, and the industry or manufacturer also recommend 4 to 8%, because if the accelerator dosage is more, your shortcut will be stick immediately, but your other parameters will lose. Panels don't move from site 18 hours until it is not been set. Strength must follow J class, as already discussed about the J class, and keep the temperature more than 13. So it is good practice.
Sorry to disturb, Mr. Mukesh. I hope you will find up in another 5 minutes.
Yes, within 5 minutes it will finish. Yes.
Thank you.
Core compressive strength, we have taken from the site. What is the requirement? We will brief about this. The 28 days during the field suitability trials, it should be FCK plus 1.15. like it will be for 30, it will be 38. Shortcut routine core testing, it should be FCK plus 4. The in situ strength should be FCK into 0.85 as per the FNR class. In case of the steel inside the core, it reduced 10 to 15% reduction in compressive strength. The effect of melted steel is higher on stronger concrete and it locally moved from away from end. However, presence of steel parallel to the axis, you can see this. This is the core. In case your core having the steel, and you have to check whether first of all you have to avoid the steel during the cutting, because it will reduce your 10 to 15% reduction of compressive strength. So if you want to check it with the steel, this is the Graham-Trees formula precisely, and you have to make the core strength character by multiplying the bar, and the as per the equation you can calculate it. Plate bending tests, already the Ravindra sir and all speakers brief about the energy test, its parameter. So I will not go into detail, because as our side and everywhere we are doing the test, better fibers give you better results. It is my submission. If you have substandard fiber, it will not give it. It will give more bunch of fibers. It will create the choking of pipelines, and it will not give good results. If you have good fibers, good testing machine like controls, so your results, your accuracy, and your consistency will be rare. The technical benefit of fiber. You can see the photographs where the wire mesh is applied, and in another the wire mesh is being considered into design. The designer can reduce the thickness of spray concrete and make it lesser thickness, and you can see the time period you can save. So this is the all about the brittle nature of fiber, lead to certain mode of the failure will tighten the nature, lead to ductile mode of failure where the element still continues to hold together. Fiber in concrete work precisely on this concept, wherein the brittle nature of concrete in transform into ductile one by addition of fiber. The presence of fiber at crack faces provide high level of post crack tensile capacity in the concrete, which lead to all associated improvement and different properties of energy capacity of concrete. I will also not go detail, because already about the fibers and their benefits has been discussed, and today we are well known, but we have to think how to make it successful, and the time saving, and what the practical approach is at site. This is also about the fibers. To achieve higher energy capacity, accelerator must be obtained due to its burning effect. If your accelerator is more, your burning effect will be rare, your energy will be less. If your energy class is not matching, your shortcut is going somewhere, losing you. Correct design, efficient spray machine, and skill nozzle band, good role of agile, and the results, high tensile strength, young modulus, and these all parameters gives you better results. You can see that spraying technique. Nozzle bands have confirmed the strength criteria, achieve less rebound, good appearance. The nozzle band has a good important role in the shortcut, how and what the distance should be keep during the spray, and how to control the finish, good appearance. So it is all about the nozzle bands skills. The equipment, spraying concrete is being used as final lining. The main factor is high-end quality equipment, a precise dosing system, and powerful pump with minimal pulsation to distribute concrete continuously, quicker, and eventually best results. You can see the correct nozzle distance, the angle, and the 360-degree angle. Some manufacturer make good equipment which is precisely and good for the shortcutting works, and you can see the results of low pulsation. The temperature. Temperature is important key. Spray concrete is normal or extreme weather condition. Low temperature is low setting. If your temperature is low, your setting is low. Proper material storage set to be ensured, which we are maintained at site. Hot water should be plus 60-degree temperature. Spray concrete temperature should be plus 13 degree. It is mentioned in the Austrian guidelines also. Accelerator admixture you can heat up to plus 15 to 20 degree, not more than that. And you can see the photographs which is showing inside the tunnel, the containers having the heating insulation system and being used inside the tunnels only. And it is the storage shed, and the plant is covered full proof of the snow and extreme condition and is being executed at site. This is a real case study of implementation for controlling the shortcut temperature and other parameters in extreme weather condition, like minus 24 degree temperature, the accelerator, water, and everything is being heated. I have a short video to understand in extreme weather how the works is going on, and it is a real case study of my side. So this is the last slide from me, and thanks.
Thank you, Mukesh. I think we couldn't have asked for a better exposure to this technique. I think you have covered the entire technology of shotcrete in this presentation. Very informative. Thank you very much for that. We'll take a couple of questions. From the audience itself, there's one question. What is the length of fibers used and what performance difference did you notice when you use steel versus PP versus glass fiber?
Yes, thank you for the question. And there is, we are using 45 to 55 mm thickness of class 2 fiber, which is polypropylene fiber. Steel fiber were used in my previous 10 years back in this railway project in USBRL, Pir Panjal Tunnel. The steel fiber is better to give some loose or poor ground condition. It works at that area only, and it gives the some disadvantage, like there is the heavy as compared to polypropylene fiber. When the labor or manpower is being used at batching plant, they will like to use lightweight fibers. So there is another kind of the corrosion behavior of the steel fiber, and the losing of the pipeline of the shortcut machine is the disadvantage. Advantage is, you know, the well distributed and as a structural support, it is good. And in polypropylene fiber, there is a advantage, is it is a lightweight and it gives the similar or same energy. But there is again, when we spray the shortcut into the surface or ground or tunnels, due to excessive air pressure, more than 5 to 6, 7 bar, it flow into the air. So the actual fiber content cannot be assured into the shortcut. So it is the difference between polypropylene and steel fiber. And glass fiber, as far as this tunneling, we have not used till now. Thanks.
Thank you. There's another question. What water cement ratio is recommended for shotcrete with fiber, especially in cold weather?
Yes, in shotcrete, their plain shotcrete, you can go with the 0.32 to 0.36 water cement ratio. If you are adding the fiber, it demand the water demand, water quantity per cubic meter, like 0.36 to 0.37, 0.38. The fiber hold the waters, so it like a little bit, it will require the water in case of fiber.
So in general, you're saying when you're adding fibers, you must slightly increase the water.
Yes, slightly, yes, agreed.
Okay. Thank you, Mukesh. Since we are short of time, I'm not taking more questions, but I hope that the audience can contact you sometime directly. We can share your email ID with the audience. I hope you will not mind.
Yes, definitely, ma'am. Thank you.
Thank you. Thank you so much. And now we will move forward to our next presentation.
Yes, thank you.
Thank you. Yeah, next we have a presentation by Federica Bini. She is working as the product manager for Controls, which is a global leader in manufacture and supply of high caliber equipment, especially in the realm of civil engineering applications. Federica is a member of the Italian normative working group, which works on cement, mortar, concrete, and reinforced concrete. And today she will share her experience at Controls. Federica, can you access the system and please share your presentation? You are muted.
Hello, can you hear me?
Yes, yes, yes.
Good. So I'm going to share my screen. Can you see my screen?
Yes, it is seen. It is clearly visible.
Good. So Control started around 20 years ago in manufacturing equipment for fiber reinforced concrete testing. And today I will let you have an overview of the most common test methods for FRC, and I'll present the latest solution Controls has in its range for these determinations. So although fiber reinforced concrete has been patented in the 60s, it has been usually considered a new material. However, things are changing and its use is increasing because of the advantages provided by fibers. In fact, fibers give a marked structural contribute. Plus, they control the microcracks due, for instance, to shrinkage or freezing towing cycles, thus increasing strongly the durability. They also improve impact, abrasion, and fire resistance. Since 2010, the new FIB model code is a tool for structural design of FRC. This code and others provide a performance approach to identify design values by experimental tests. Fibers, as stated, control crack opening and propagation, thus determining the post-cracking behavior of the material. The main mechanical property which is affected by the fiber content is the tensile post-cracking strength. The directness as a consequence, the direct tension test is the most representative test method, but unfortunately, the test execution is not simple, especially for materials having softening behavior due, for instance, to poor fiber content. For this reason, usually bending test method is preferred for the characterization of FRC. We usually perform a bending test on beams or on slabs. Beams is usually widespread due to different reasons. For instance, the sample is small and easy to handle. Specimen dimension fit the Flexion machine commonly used in testing laboratories. Plus, Flexion beam is a well-known test method where we use a simplified relationship considering bending theory for linear elastic materials and uncracked section properties. However, this method shows significant scatter in the test results. In fact, the non-uniform redistribution of fiber inside the specimen and the small size of the specimen lead to have samples that can be significantly different one from another, even within the same batch. On the other hand, slab testing is not commonly used because of the dimension and weight of the specimen, which require dedicated testing machines. In addition, it's more difficult to assess the material constitutive laws. However, slab testing better reproduce the behavior of statically indeterminate structure, as the big size of the specimen reduces the edge effect and allows wide cracked regions. There are two main testing standards about beams testing. The first one is ASTM C1609. ASTM 1609 method evaluates the flexural performance of fiber reinforced concrete using parameters which are derived from the load deflection curve. This test is conducted on a simply supported beam under 3-point loading, and this testing configuration reduces the influence of shear stress. The deflection is measured by two LVDTs, which are positioned at each side of the specimen, and the average displacement is used to control the test as feedback variable. In fact, it is not allowed to perform the test under stroke displacement control. In the 4-point bending test, there is a wide region of crack propagation between the two loading points, and generally the main crack will propagate starting from the weakest cross section. This means the crack pattern is not predictable and not repeatable, thus leading to, let's say, less consistent test results. The speed range is quite wide, and after the peak, it is allowed to speed up the test. At the end of the test, we will have a test graph which is similar to what is here shown. And we need to determine the first peak and the peaks load, which can be different or same values, depending on the type of material, and the corresponding strength values calculated by using the modulus of rupture formula. ASTM also requires the determination of the residual loads at specified deflection values and the corresponding residual flexural strength. Plus, it requires the calculation of toughness, which is the area subtended to the load deflection curve, which indicate the ability to absorb deformation energy before failure. The other well-known test method is EN 14651, which is also called the CMOD test. CMOD stands for crack mouth opening displacement. In fact, in this test method requires the specimen to be notched on the bottom part of its mid-span section, and this test requires to control the rate of notch opening. EN then investigates the tensile behavior of the concrete by evaluating the load versus CMOD curve. The sample is simply supported. In this case, the test is performed under 3-point bending. And this test configuration allows the crack propagation point to be predetermined, and as a consequence, this test provides a much easier and stable control of the test, especially during the critical stages, as just after the peak. Again, assuming simplified linear stress distribution and considering uncracked mid-span section, the standard requires to calculate the stress at the tip of the notch, considering both the peak load and the residual loads at different mode values. So let's see what EN and ASTM standards requires as for slab testings. In the EN method, a fiber reinforced slab, which is a square slab 600 by 600 millimeter, is subjected, which is sprayed according to the same standard, the part 1 of the same standard, is subjected to load under deflection control, obviously, through a rigid steel square block positioned at the center of the slab. The support frame in this case is continuous, so the system is statically undetermined. Thus, the direction and position of the crack is not always the same, is not predetermined, and is not so much repeatable. Again, we will have curve similar to what's shown, which is load versus deflection. And from this curve, a second curve is calculating, giving the absorbed energy, so the area below this load deflection curve, as a function of the slab deflection. Then toughness is calculated at the central deflection of 25 millimeter. In addition, we must consider that in this test, since the support is continuous, we have to consider that the friction between the specimen and the support is quite important and is affecting the final test results. This is the ASTM version of the same slab testing. So even in this case, we have a slab, but ASTM prescribes a bigger and heavier sample because it prescribes a slab which is 800 millimeter diameter. The sample normally, for this reason, for this dimension, requires a wide testing frame, which is able to host such big sample. The sample is supported on 3 steel pivoting spheres positioned on the specimen circumference at 120 degrees. And therefore, for this test configuration, the crack pattern is normally quite repeatable because the position of the cracks is more or less always the same, and this leads to better consistency and lower scatter in the test results. The performance of the specimen is quantified in terms of energy absorption, calculated again as the area under the load net deflection curve between the origin and the specified central deflection values. Toughness is normally calculated at central deflection of 5, 10, 20 and 40 millimeter, depending on what the material will be used for. For instance, 5 millimeter is normally used for watertight structures, while 40 millimeter, when concrete is intended to suffer important deformation on site. So here we have the two control systems that we as controls propose for FRC testing. On the left, we have the Automax Pro M, which is a touchscreen control system that can be possibly connected to a PC for remote control and test result calculation. While on the right, we have the Automax Multitest, which is our top of the range, which is instead a fully computerized unit. So let's see the difference, the different machine in details. The Automax Pro M, with its 7 inches touchscreen color display, allows the simultaneous display of load, stress, strain values, plus stress, strain, or load versus displacement curves. It features a very quiet DC motor, which allow to carry out loading and unloading cycle at controlled speed to automatically perform, for instance, the elastic modulus test, and provides the automatic calculation of test results in according to the main international standards. When the controller is connected to suitable frame and test accessories, it's possible to perform displacement control and tests on beams, as we have seen, the type of sample we have seen: beams, notched beams, round or square slabs. The machine will save the test graph and all the raw data in the internal archive to be then exported by USB to PC. In case the machine instead is controlled by PC via our software, the calculation of the test results according to the different EN or ASTM standard is automatically performed. This is the other system, the Automax Multitest. The Automax Multitest can be used practically for the same test methods and application as the Automax Pro M, but in this case, the console is supplied, instead of with a touchscreen display, is supplied with complete with a high-spec all-in-one PC for the remote control of the whole system. This console allows maximum flexibility, as it features 14 channels to connect up to 4 loading frames and up to 10 displacement or strain sensors that can be acquired simultaneously. Both the Automax Pro M and Automax Multitest use the same PC software packages. There are 4 software packages available. Data Manager, which is used for standard failure test, the E-module, which is used for elastic modulus and Poisson ratio determination, the UTS for tensile tests on steel rebars, because both of console can be connected also to a tensile frame, and the control for the displacement control test we have seen so far. So let's enter a little bit more in detail about the control testing software, which is the one used for FRC determinations. There are 8 preset testing procedures according to the main international standard meant for FRC testing. You see, there are several EN, UNI, and ASTM test methods. There is also the user shall select the standard or test method of interest, and then let's say that is everything is preset to ensure a easy and smooth test performance. There is also the possibility to set up customized test procedures, allowing the desired loading history. During the test, we will have a screen like this, so we will have the possibility to see up to two curves in real time, where the diagram axis, so the variable to be shown, can be selected by the user. During the test, it's also possible to modify all the test parameters. For instance, the active channel, which is used by the console to control the test execution, the load, or in case of the displacement control test, the load or the displacement rate, so the speed of the test, basically. All the control settings, the target values, etc. At the end of the test, the software will provide the automatic calculation of the test results according to the standard which have been selected, and everything will be automatically saved in the archive. Then from the archive, it's possible to export test report both in PDF or Excel format. In case of Excel format, the Excel will also include all the raw test data for any possible further elaboration. So I'm finished. I'm stopped sharing my screen.
Thank you, Federica. Thank you for that detailed presentation on the test methods and the equipment available. Now we will have the presentation by Shailesh, Mr. Shailesh from Controls, on the testing of the square panels. Shailesh, would you please take over? Shailesh, are you able to access?
Hello.
Yes, yes,
Yeah,
please share.
yeah. Are you able to see?
Yes, yes, we can.
Okay.
Hello everyone, myself Karthikeya Jadhav. I am product manager in Chirag Control Private Limited. We are having factory at Vadodara, Gujarat. Chirag is a leading supplier of testing equipment in civil engineering. I am going to explain how to perform energy absorption test on fiber reinforced slab using displacement transducer. The objective of EN 14488 Part 5 is to determine load deflection response of a slab specimen in order to calculate energy absorption capacity at specified deflection. Square panel test as per EN 14488 Part 5 is designed to determine absorbing energy from the load deflection curve measure of toughness. A fiber reinforced slab specimen in this test is subjected to load under the deflection control through rigid steel square block positioned at the center of the slab. This test is allowed to check load bearing capacity for an imposed deformation and to control the capacity of absorbing energy under the large deflection. The square panel test is also called FNAR test. The panel test is simulating laboratory scale for the structural behavior of the system anchored board square concrete under flexural and shear load. Panel correspond much better with real concrete tunnel lining than a beam. The panel support on all edge simulate the continuity of concrete spread lining. A square specimen shall be produced from panel spread and cured in number accordance with EN 14488 Part 1 with dimension of 600 by 600 mm and trim to thickness of 100 plus or minus 5 mm immediately after spraying. The prepared slab shall be cured in accordance with EN 12390 Part 2 for a minimum of 3 days. The prepared slabs shall be performed at 28 days. The test shall be carried out in testing machine conforming to EN 12390 Part 4. The stiffness and the control system of the testing machine shall be such that the test can be displacement controlled. The stiffness of the loading frame, including load cell, loading block, supporting frame, shall be 200 km per annum. Displacement calibrated transducer resolution of 0.01 mm is required. This is Automax multi-test servo control automatic load and displacement control machine with high stiffness flexible frame. This is square panel test accessory having dimension of 20 plus or minus 1 mm thick and 500 by 500 plus or minus 2 mm to test sample of 600 by 600 100 mm thickness of spread concrete sample. A rigid steel square loading block having contact surface of 100 by 100 plus or minus 1 mm and thickness of 20 plus or minus 1 mm position at the center of the upper face of the slab. Now we will fix this frame on flexural testing machine. Make sure that the rigid square structure frame is bolted properly on bottom. Now we will fix displacement transducer having 50 mm stroke at the center of the sample. It is placed such that the sample deformation at the center of the sample is measured with respect to square frame conforming to the EN 14488 Part 5 standard. After fixing displacement transducer, we are placing metal plate on it. This is very necessary to protect displacement transducer from any damage by placing sample on it. Now we will place sample on a square frame. We need to make sure that it is placed at the center of the frame. Square loading arm must contact at the center of the sample. How to set system for conducting energy absorption test as per EN 14488 Part 5. Since this is multi-test equipment, we need to test set system for EN 14488 Part 5. This system is having number of channels and we need to make sure that correct channels and correct calibration is uploaded. This is just one-time exercise only. If you are using this system for one type of repeated test, then there is no need to upload calibration and select channel every time. But we need to make sure that correct channel and correct calibration file are applied. Another important is to feed all imported data in software. There are two types of data. First, parameters which are affecting to conduct tests like selection of test standard, channel selection, preload, peak sensitivity, feedback control channel, and very important is PID parameters. PIDs are specific parameters which are given in manual as per different tests. These parameters require little modification which depend on type of fibers and stiffness of sample. This is also one-time exercise if you are conducting same test again and again. Since this is high-end system, presence of expert operation is very much required apart from constant monitoring. Second, parameters which are used as printing report like name of customer, type of fiber, type of concrete, state of casting sample, data of testing, identification number, etc. This is basically data management parameters which need to be set carefully. After doing all setup, now just press start button. System will start and pause at preload. This pause is for checking sensors and zeroing displacement reading at preload. Preload is the starting point of the test. Means after this point, system will apply parameters like test speed and PIDs. Hydraulic system require minimum pressure to start with this preload. During initial phase of the test, load will increase quickly until it reaches to peak. After reaching peak, first there mostly at bottom of the sample will break because maximum deformation will happen at bottom of sample. Load will decrease and then will increase again. Since this is displacement control mode, system will maintain displacement rate of 1 mm per minute. This sample is containing steel fibers. Initially, there may be few peaks which depend on type of fiber and mix design. We have experienced that steel fiber are giving few peaks. It's also depend on method of casting and expertise of casting sample. Sample must be casting using spraying method and need to make sure that the concrete mix is well mixed and prepared. Fiber must be distributed equally in the sample. You can notice that system will stabilize and there may not be further fall, but it all depends on sample behavior and spread of fiber binder and all over mix design. We are noticing another peak. It may be come from breaking of inner layer. Please also note that we have come up to 360 seconds, which is 6 minutes, and sample deformation is also 6 mm. You can also notice that when fiber is breaking, sample goes back little upper side and then again and again going lower side. Means this behavior can be noticed from reading of displacement transducer, which is placed just under touching the sample. Machine must maintain deformation of sample at 1 mm per minute, which is happening here. Stroke control or piston control system are not recommended in standard. So now we are getting smooth riding. No more peaks now. This types of graph is giving more information about peaks and falls, type of fibers, binders, etc. This is only possible when we measure real displacement of sample. About 15% of our days reached about 900 second minutes, 15 minutes, and our displacement is reaching about 15 mm. Means we are going good. Energy versus load, etc. X and Y parameter can be selected during diagram. Energy is being calculated live during the test. means 1800 seconds. Energy value must be reported at 25 minutes. After 30 minutes, test is completed. We can stop it manually or it can be stopped automatically if we choose at the start of the test. Now, this is important stage of the test. We need to save data. Data can be saved in software format as well as in Excel format. We can choose the folder at which data can be saved. We can create complete report with graph and energy value along with the all sample details.
Thank you, Shailesh. Thank you for presenting that. I have one question here. Can we conduct this test using piston displacement?
Tell me, ma'am, again.
Can we conduct this test using the piston displacement?
Yes.
Measuring?
Yeah, we can conduct. Definitely, we can conduct. But I mean, as the standard, if you follow the standard clearly says that we need to measure displacement of a sample, basically. And we need to control displacement of sample. There will be some difference between if we do test with piston and on sample. If you do with piston, it will include all the deformation of frame as well, which is little bit. So it's better to do with on sample.
Okay. If there are,
I would add that. Sorry, I would
yes,
add
Frederica.
that for Yan method, as Shailesh said, it's preferred to use the deformation of the sample as a feedback instead of a piston stroke. And for ASTM, it is not allowed to use the piston stroke.
All right. So it basically a code requirement. But I was just wondering if there, even if we measure the specimen displacement, maybe control can be done using the piston displacement.
The piston displacement. Yes, it's a possibility. It's not so strict, let's say. I would use, at least for the calculation of the test results, the displacements of the sample. And then for the control, it's acceptable, let's say, to use the stroke of the piston as a control feedback variable.
Right. Thank you. I think that video was well demonstrated. It is one of the most important tests that are being done in our country also because of the widespread use of fibers in tunnel lining and basic requirement of our shotcrete testing. So thank you for that presentation. I think we are just overshooting, so I'm not taking any questions now. We will probably keep it till the end of the day. And we will take a short break. Before that, we will have a short presentation by our sponsor. After that, we'll break for lunch and assemble back at 2 p.m. So right now, I am handing over to our second sponsor from Tremco. Santosh, Mr. Santosh, are you there?
Hello?
Yes, Mr. Santosh.
Are you able to hear me? Yeah.
Yes, we are able to hear you. Please
I'll
go ahead.
Share my.
We have a, yeah. The question that is there in the chat box, we will take it up in the evening. I hope that is fine. Or I'll quickly tell the type of sensor used to measure the center displacement is the LVDT itself. We have to use the LVDT for the displacement transducer. So,
My presentation is visible.
Yes, yes.
I think we are overshooting the time. Probably, yeah. This is Santosh here from Tremco CPG India. Welcome to all the delegates on this workshop. I'll quickly run through company introduction and then how we can add value and support the FRC industry. So basically, I'll take you through 3-4 steps. Introduction of Tremco CPG. Why is FRC? Types of fibers in market and its performances, and the opportunities what we have in the market: slab on grade, composite extra construction, less joint floors, and many more opportunities which we have in the market. So coming back to our organization, we are a US organization, Tremco CPG. We are $6.2 billion company with a 66% of the industrial products and 34% consumer products. We are listed in US Stock Exchange, and then we are globally 15,000 employees working for the organization. So 156 manufacturing facilities across 26 countries, and we have sales in 170 countries with acquisition of 175 acquisition in the last 30 years. So major divisions what we work in Indian market, Tremco waterproofing solutions, where we work on cementitious polyurethane and single component polyurethane waterproofing products. Hillbrook, which we deal in glazing solutions. Flowcrete, which is one of the prominent brand in India for last 12 years, and then we deal with epoxies, polyurethanes, and MMA technologies. And one of the largest Delhi Airport T3 is done with this terrazzo flooring. And today topic, Euclid Chemicals, we deal in construction products and admixtures, where we have fibers, grouts, sealants, repair and rehabilitation mortars, admixtures. And another 3 brands, Windseal for expansion joints, Nullifier for fire protection, and Drivit for external facade installation. So this is one of the state-of-the-art technical and training facility what we have in US, Cleveland, where 9 professional works across 365 days, and the technicians to work on R&D. This is our R&D facilities, where we have facilities for fiber testing, synthesis. We have synthesis labs, petrography, and we have a state-of-the-art concrete labs, and testing of coatings will be done, and then also metal testing lab in Cleveland. Coming to fibers and new opportunities, what we have in the market for us. So I think this I'll not get into it because all experts have spoken about fiber, which is a huge history where we started with mud bricks thousands of years ago. Basically, structural fibers provides additional tensile and structural capability. Fiber supports in integrity and durability of the concrete. Coming to our services to the market and the support, we have all kinds of fibers with us. We can consider and design for shrinkage reduction, replacement of steel in non-structural sections, composite decks, and temperature control concrete. In India, we deal with 2 kinds of fibers, tough strand and tough strand SF, where these are classified as micro and macro fibers. Coming to fiber replacement, where we can replace the steel, non-structural steel can be replaced. Slab on grade, we can work on parking and industrial projects, where Mr. Ganesh was explaining in the morning. We have done a couple of projects with them. Pavements for road projects, overlays, composite metal decks, shotcretes, precast, and short retaining walls. And also for building structures, MLCP and RCC slabs, we can add our structural fibers, put the design and back up in place is concerned. If we can evaluate and support the project's design and also execution of the project along with our partners. This is our global design team, Mr. Amir and Michael, who supports us from US for the design of fiber reinforced concretes. And to be more precise, our tough strands SF is 59,000 strands you get in 1 kg. And then it can replace, it can be used for drying temperature and plastics in concretes. It has 2 hours of fire rating by UL, and it is one of the patented technology from us is concerned. Coming to the advantages when you work with the we manufacture, we test as per the ASTM standards, we design the structures and we specify, and also we work with customers projects with authorized flooring contractors for right execution to be delivered at a site. This is a FRC lab and testing with as per ASTM C1609 at US facility. And these are a few projects what we have done, slab on rate, how you can deliver the slabs. And what are the main advantages? What we have key features is in FRC. One is you can increase the size of the joints from 8 by 8 meter by 8 meter to 15 meter by 15 meter. It can increase your fluctual strengths, and then it will give a lot of advantages. Our doctor explained in the morning. Coming to slab on grade roofs, we refer a code of ICA 360. Coming to the examples or the projects what we have done in India, Jai Mataji wearing house, which is around warehouse, it is 40,000 square meters have been done. This is one of the state-of-the-art project what we have done in US. And to add to the list, Mahindra racetrack L&T slab on grade we have done. And Jai Mataji, as I earlier explained, warehousing at Chennai. Bharat Biotech, 2,000 square meters. We have completely replaced the steel with our design of fibers. Rajarajeshwari Temple in Bangalore. Godrej projects in Baramati. And we have executed IKEA projects along with Mr. Ganesh, who was one of the speaker today in the morning, around 30,000 square meters, just completed the project. And another major projects in Coimbatore called Coral Engineering is executed with our fibers. So opportunity to explore precast, especially septic tanks and precast concretes. All these elements can be where we can use the fibers. For shotcreting, we can use, especially this can be used for even for exploring fire and explosion, spall resistance. These fibers can be designed and used. And pavements, especially road projects internationally, we have done in US specifically. And for your sound walls, your canal lining, this can be used and then you can design. And for even polished concrete, we can design the concrete, execute, and then we can get the floor to this level. So these are the few applications where the Tremco can add value and support our customers at the back end is concerned. Thank you very much for the slot given to us for showcasing our company's concern.
Thank you, Mr. Santosh. Thank you for sponsoring this event. And we will take a short break. And after that, we'll meet again at around 2 p.m., where after that, we have an interesting session on textile reinforced concrete, totally new technology that is being introduced into construction scenario of our country. So I hope to see you all back here. Thank you.
Thank you.
If you have any questions, you might even post it in the chat. Even we can take it up in the evening at 4:30, where we have the Q&A session. Thank you. We will start shortly after this presentation by on our third sponsor.
ફોટો પાડી લેજો કુનાલે મોકલવા માટે.
Welcome back to all of you. Thank you for joining back in time. That was a presentation by third sponsor, Milestone Engineering. Now we will move on to the next session. This is an interesting session on textile reinforced concrete. And our first speaker, we have 3 speakers in this session. And after that, there is a demo. After the break, then we'll have a demonstration, and then we'll have the discussion. So our first speaker for this session is Sachin Paul, Mr. Sachin Paul. Sachin is a PhD research scholar at IIT Madras, and he's also, is my slide visible?
Yes, your slide is visible.
So he's also the assistant professor. He's working as an assistant professor at Marathanishis College, MA College Engineering in Kodamangalam, Kerala. He has been sort of leading the research in Professor Gittu's group at IIT Madras, where currently there are around 5 to 6 projects exclusively on textile reinforced concrete. So he's one of the most experienced persons on this area. So over to you, Sachin. Without much delay, please take over. Yeah. And I hope you are still the co-host, right?
I think I am, yeah.
I'll stop share.
Is it visible?
Yes, it is. But it's still not in the presentation mode.
Okay, fine. Right. So good afternoon all. Thanks for the warm welcome, Dr. Sunita. I am Sachin Paul. I'm a research scholar at IIT Madras. I hope I'm audible.
Yes, clearly audible.
Yes. So I'm here to set a platform for textile reinforced concrete. I'll give you a brief introduction of what is textile reinforced concrete, why we need the concept of a textile reinforced concrete, and what are the aspects to look into it, what are the characteristics of textile reinforced concrete that are relevant to application in the field, and also as a researcher, what should you look forward if you're going to do some research in textile reinforced concrete. It also gives you guidelines for people who wants to execute work in textile reinforced concrete of what to do and what to look forward regarding the applications related with textile and selection of materials for textile reinforced concrete. So with that, I start with the slides where Professor Gettu have stopped regarding sustainable construction. So this marks the necessity of concept like textile reinforced concrete. So again, your sustainability pillar can be divided into 3 major pillars: the environmental, social, and economical. And one of the major aspects of your environmental consideration or environmental concept is global warming, water shortage, energy consumption, and raw material usage. And as an engineer, we always try to address these aspects of environmental and social and economical aspects to address through our construction and to address through our material selection in construction. So reduce carbon dioxide emission to reduce global warming, energy consumption, use low energy production and manufacturing construction materials and equipments. Raw material usage is also a very important aspect regarding construction. Why? Because these days we are a scarce of a lot of raw materials, especially aggregates and other materials. So reducing the consumption of raw materials is a way for the future, and it is something very important. So optimization, in short terms, we can say that optimization of material comes as a very important head for the future construction, and that is where we are looking forward with the textile reinforced concrete. Now, if you look at the social aspect, housing for all. So cheap and robust construction. You have to be able to construct a large amount of houses So we have to look at prefabricated construction scenario, and also whether we can assemble lightweight materials, construction materials or housing materials at site and make a large amount of housing with a very low labor and also with economy. Is that possible? That is a question that we ponder every time. Aging of infrastructure is yet another challenge, because all our construction boom has happened 50 years back. So all our structures are at the stage of repair or retrofitting. So most of the reinforced concrete structures have a lot of corrosion problems these days, and we are addressing them one by one as we progress. And this scenario will be adverse in near future because of the aging problem and corrosion effect of reinforced concrete construction. If you look at the economic aspect, limitation of real estate, that means we have to go for vertical construction. We can't go expanding in horizontal direction. We have to go for vertical construction. And reduction of the weight of components of structure also comes as very important when you go for vertical construction. You can't have heavy materials, because then you again will require higher amount of reinforcement. Maintenance cost. So you should have materials with lower maintenance. You should not have materials which require higher maintenance, like corrosive materials. Also exposure conditions like marine conditions, where the maintenance is very high for the steel members, is also very relevant. Transport cost. If you optimize material, if you have a smaller section for material, then you have a higher advantage in transportation of materials. So all these aspects can be combined together with these bulletins or these ideas of a future material that could fetch or address at least some of these problems, and try to find a solution which can lead to the direction of the sustainable construction. The first one is efficiency and economic construction. Efficient construction or economic construction, both in terms of material optimization and also economic in terms of material selection, both are very important for construction. A low carbon emission, that is, the total carbon footprint from the starting, from the excavation of materials to the completed construction, should be as minimum as possible. So we should be looking at this aspect of construction to address the future development. Durability of structure. We can't construct and demolish structure as we go on. We have a limited resources. Our resources are finite, and we have to deal with our durable options for construction. Reuse and recyclability of materials and sustainable based design should be also something that we should think about in the future construction. So if you address some of this, then we will understand why we need a material like a textile reinforced concrete. And there are a lot of other upcoming materials like textile reinforced concrete. One of them is only textile reinforced concrete. It doesn't mean that this is the solution for everything. So let us see what is textile reinforced concrete and how it adheres to, or how it addresses all these demands of the sustainability. So textile reinforced concrete is basically fine-grained concrete embedded in textile mesh. So fine-grained concrete, why? Because you have very small mesh opening sizes, therefore, and very smooth surfaces of the textile. So therefore, you need a matrix wear or the concrete wear. Your aggregate size is very minimal. Usually, we keep the aggregate size to be less than 2 mm. So you can also call it as a textile reinforced mortar instead of concrete. But generally, the strength is very high. We range from minimum of starting strength around 30 MPa and then above it for general application, because it needs good penetration into the different layers of textile. It needs good bond between smooth surface of textile. The textile usually comes with coating. So those bond aspects and the penetration aspects define the metrics. So development of metrics for textile reinforced concrete is a complicated scenario. You have to be specialized in that. And it's a mortar, it's a flowable mortar. Depending upon your construction type, it can be a flowable or a stiff mortar. Generally, it's a flowable mortar, which has good penetration capacity. Now, what fibers can I use? What can we use for construction? Generally, a textile that is used for construction with textile reinforced concrete are made up of glass and carbon in common applications. And most usual application will be AR glass or alkali resistant glass, which is inert to the alkaline environment of concrete. So they are very stable in concrete, and they are much cheaper in comparison to carbon. They come in the form of yarns. So it will be a bundle of each yarn or each weaving in a textile will be a bundle of hundreds or thousands of individual fibers combining together to form a yarn. So that is the structure of a textile. So it is generally open mesh textile because we need to penetrate fine grained concrete, or concrete or the mortar should penetrate into the textile meshes. Now, in combination of both these elements, this textile and the fine grained concrete, we get a composite that is called as a textile reinforced concrete. Now, if you look at the basic advantage that we were trying to address regarding sustainability, is that these are corrosion-free materials because we use corrosion-free reinforcement, so they are corrosion-free. So durability aspect is covered to a great extent because of this non-corrosive nature of the reinforcement. Second aspect is that a conventional reinforcement usually requires a cover to protect against external environments, and it is very, very dangerous to use such thin elements in applications where extreme weathers like marine environment is considered. So optimization of materials by removal of cover, because since this is a non-corrosive material, we don't need a cover. We just need a concrete to cover just the surface of the textile. So we need minimal cover, and you can go about 10 mm thickness for materials, even 10 mm thickness for materials to get around 20 MPa tensile and 35-40 MPa flexure capacity. So it is possible to have very high strength with very small cross section with these materials. High design feeder. Since these are flexible materials, because textile fiber yarn itself is a flexible material, you can actually use this, have higher flexibility in the construction with respect to these materials. You can form it into any shape, you can convert it into any aspect of construction. So it is very good for architectural aspects where you can fabricate very thin elements with very high precision and very good surface finish because you have fine mortar and with architectural aspects that you need. And lastly, very importantly, you have a targeted orientation of your fibers. In fiber reinforced concrete, you have random orientation of fibers. This actually reduces the efficiency of the total amount of fibers that you put in. But in case of textile reinforced concrete, for example, if you take a flexure element, you need reinforcement below the neutral axis. And that is what is addressed in case of textile reinforced concrete, where you're putting the reinforcement at the required place, at the required location. So that gives a higher accuracy or higher efficiency in our development, of a higher efficiency in our design of the system. So it covers basic optimization of the section, durability, less transport volume because of the optimization, lower dead weight, because we always deal with very thin sections in case of textile reinforced concrete. You have higher shrinkage and crack resistance because you have a distributed reinforcement throughout. So crack arresting is very high. It also have very good impact resistance in comparison to normal conventional reinforced concrete. And it also have a lower carbon footprint emission, basically from two aspects. One is optimization of material. You're reducing a lot of materials in this. And also if you're using recycled material like recycled glass, then you can again enhance whatever quantity of whatever amount of carbon footprint you're developing. Now, where are these applications? What are these basic applications that we are focusing on? The basic applications of textile reinforced concrete are related with thin section elements, and as it started with a lot of use of facade panels around in Germany, and yeah, so it started with the facade panels, and then you have structural members like bridges and roofing systems made up of textile reinforced concrete. So anywhere you have structural or semi-structural elements with very thin cross section, then textile reinforced concrete is something that you can definitely think about. In India, major applications in actual industrial level has been done by Reina, who will be presenting, Dr. Reina, who will be presenting on the next, who will be the next presenter, and he will explain more about what are the challenges in application in India and Asia Pacific, and he will deal with what the major construction that he have covered in India regarding textile reinforced concrete. We have done quite a bit of textile reinforced concrete fabrication at IIT Madras. We have done retrofitting of materials, and retrofitting was one of the first applications that was developed for textile reinforced concrete, because there is a high compatibility between the parent concrete, which is the initial concrete or the first concrete that is actually existing in a structure, and the overlay concrete. So due to this high compatibility, textile reinforced concrete is a viable option for good compatibility for retrofitting purposes. We have developed a lot of construction, structural and semi-structural application. One of that was related with IGST's Indo-German project that deals with water tank by textile reinforced concrete. So we were developing modular water tanks, which can be transported and erected at sites. And even the base of this water tank that you see is actually reinforced with textile meshes. So we'll go in details about all those things later in the coming presentations. So moving along with the design, the aspects of textile reinforced concrete, we will start with the concept of textile reinforced concrete. So characterization or find the properties of textile reinforced concrete, or the stress strain response, is what generally defines the mechanism of textile reinforced concrete. How do we test a textile reinforced concrete, or TRC? We test by using a uniaxial tensile test. So this is a general setup for uniaxial tensile test. We do according to RILAM standards of TC 232, which was published in 2016. So you can see that it's quite recent that we have developed the standards, but still internationally accepted standards are not there other than the RILAM TC committee. So it's a very fresh, very new concept regarding construction. Now, the aspect is that you have two materials which are brittle. One is your concrete, and another one is your glass or carbon, which are both brittle. So when you combine two brittle materials, the question is whether it's going to be a brittle failure, which we do not want in reinforced concrete construction. So the mechanism of textile reinforced concrete itself defines why it is not that big a problem when you consider the two brittle materials. When you take a stress strain curve, when the material is loaded, the initial portion of the curve, which is marked by the dotted line, is actually representative of the behavior of the matrix itself until the first crack is formed. So when the material is loaded, the first portion of the curve is actually the first portion of the matrix is controlled by the matrix properties and all. So the modulus of this curve, or the slope of this first curve, dotted line curve, is actually noted by the properties of the concrete that is used for construction. Once the composite reaches, the matrix reaches its ultimate capacity under loading, ultimate tensile capacity at loading, the first crack is formed, and it stops the linear portion of the curve, or the initial linear portion of the curve. There, a crack is formed, and the crack is bridged by the textile that is bridging between them. On further increase of load, what happens is that the other parts of the composite also reaches the ultimate strain, and further cracks are formed. So the next phase, which is denoted by zone 2, is defined by the formation of multiple cracking. So there will be multiple cracks formed during the zone 2, and until a point where the crack saturation happens. That means that there is no further crack possible to have in the section. So at this point, when it is not possible to have any further crack, then all of the composite strength is transferred to the textile, and the textile takes the load. So the later portion of the curve, the last portion of the curve, is right now controlled by the behavior of textile alone. So the strain hardening, this is generally called as the strain hardening zone of the textile response, of the TRC response. This is completely controlled by the textile modulus and the amount of textile that you put inside. So there are three phases. One is the initial phase of the curve, which is controlled by the properties of the matrix. Then you have multiple cracking phase, which is controlled by the amount of volume fraction of materials, the bond properties, and a lot of other factors. And the last portion of the curve, which is actually controlled by the properties of textile. Right. So in this multiple cracking zone, what happens is that whatever cracks are formed in the multiple cracking zone, they starts to expand. So this is called as a crack widening zone. So in this portion, the crack widens, and it fails when one of the fiber sections reaches its ultimate capacity, and the fiber failure happens, and it fails by rupture. So this is the basic stress strain response, or basic response of textile reinforced concrete. Now, Now, can we use any fibers for textile reinforced concrete? So the answer is no, you cannot use all the fibers for textile reinforced concrete, basically because the question is whether textile reinforced concrete, in the case of textile reinforced concrete, what we need is a strain hardening behavior. So if you use high modulus fibers like glass or carbon fibers, what you get is something like a strain hardening behavior, as you can see in the initial research by Pele Mawashir in 2010 in that era. Now you get a strain hardening behavior. That means that after first crack, there is enough load capacity for the composite and it fails by ultimate failure of the textile. But in case of materials like PP or PE, polypropylene or polyethylene or PVA fibers, where the modulus velocity is less, then what happens is that you have a horizontal segment of response without a strain hardening response. So you will have a larger deformation on the material. The composite will deform a lot. The crack width will be very high, but you will not get a strain hardening response. The response will be more like a ductile response, but still without much increase in the ultimate tensile capacity. So the question is what you need from the textile reinforced concrete composite that you are designing for. If the answer, if the requirement for your composite is basically to have high tensile strength or high flexure strength, then you should use a high modulus fiber. If your requirement is to get more ductility and you're not concerned about the enhancement in strength beyond the first crack, then you can go for low modulus fibers like PP, PVA, or PE, where you get higher ductility without the failure of the material. Now, the properties of textile reinforced concrete. Now, Sunita ma'am, you're there?
Yes.
Can you see a line in the screen?
Yes, we can see.
I'm stuck with the line. Can you tell
you will
me?
have to go to the go out of the presentation mode and then you have to delete it. I think it was annotated by you.
Yeah, it was annotated.
So you can just go out of the presentation mode and.
Okay. Yeah. Okay. Okay. So am I visible now?
Yes.
Yeah. Sorry for the inconvenience. Yeah. So again, what are the properties of textile reinforced concrete? So this is mechanism of textile reinforced concrete with multiple layers. So what we understand from here is that for some reinforcement ratio, for example, a single layer of reinforcement did not show any strain hardening behavior. It actually showed a strain softening. After your first crack, there is a softening point and then you have the failure. So there is a minimum reinforcement ratio in all the cases where below a particular reinforcement ratio, the composite will not show a strain hardening behavior, or you will not get any enhancement in the ultimate capacity of the concrete. Okay. So as your layer increases, as the number of layer increases, what you have is a strain hardening behavior and the increase in the ultimate capacity. It also comes with aspect that the number of cracks increase with the number of reinforcement or number of volume fraction of the reinforcement. This is actually a good thing because the total strain that the material undergoes is a constant. So that means that for a particular higher reinforcement ratio, the crack opening will be very small in comparison to a lower reinforcement ratio. So you will have multiple cracks happening in higher reinforcement ratio, but with a very small crack open. So such reinforcement ratios are preferred in most of the application of textile reinforced concrete, especially in cases where you have water retaining structures. Also, we could also find a transition between a bilinear and trilinear curve. So if you look at 4 layers and 5 layers, the 4 layer is actually a trilinear curve, as we have discussed earlier. You have the first phase, then a horizontal plateau, and then a strain hardening phase. But as we increase the reinforcement ratio, what we observe from our research is that instead of having this, it becomes a single straight line with a curvature that is equal to the property of the textile. So as at higher reinforcement ratio, you actually get a bilinear curve. And this is something that we are focusing on our design aspect of textile reinforced concrete, that we should actually have a trilinear response in case of a design. Moving forward with the other aspect of textile reinforced concrete, we should understand the fact that a textile yarn is not an individual yarn like we see in a fiber in a ferrocement In a ferrocement, what you have is a single element or single strip of metal. In case of a textile yarn, a yarn is consisting of hundreds or thousands of fibers, and all these fibers have different mobilization capacity. So if you take a fiber, only the exterior fibers of the textile yarn is in contact with concrete, and the interior fibers are almost free to move. What this actually imparts is the exterior fibers are generally called as sleeve fibers, and the interior fibers are called as core fibers. What this generally causes is that when a load is transferred from the matrix to the reinforcement, to the yarn, only the sleeve fibers or the exterior fibers take the load, and the interior fibers are almost free from this load because they are capable of moving, or they are not very compact with each other. So the exterior fibers fail at the when the ultimate capacity of the exterior fibers are reached, and then it progressively failure happens towards the interior, and this mechanism is generally called as a telescopic pull-out failure, and this generally happens for the uncoated textiles. Now, if you have coating for textile, then there are different types of coating. There are flexible coatings like styrene butadiene coatings. There are stiff coatings like epoxy coatings. So in this case, we are explaining two different coatings. One is a coating one for F2 textiles yarn, where the coating is uniform. You can see that all the cross section of this textile is uniformly coated. And this coating for F1 yarn is a surface coated textile. That is, the coating is only in surface. So the yarns are made and they are dipped into a coating solution. So you can see that all the interior fibers are distributed. They are not in contact with the surface. So what happens when these kind of fibers are used in construction is that only the exterior fibers will take the load. The interior fibers, since they are free to move about each other, they will only take part after the failure of the exterior fibers. So the ultimate capacity of the composite will be corresponding to the sleeve fibers or the exterior fibers. So if you take efficiency is the ultimate tensile strength of the composite divided by the tensile strength of reinforcing yarn. That means it is the performance of a fiber inside a composite. You can see that the F2 fibers, which is fully impregnated, shows very high efficiency of around 0.6 in comparison to F1 textiles, which shows an efficiency of around 0.4. So clearly, a coating, the distribution of coating or the extent of coating has a clear implication on the tensile capacity of these materials. Now, second aspect is the coating type. Depending upon whether it's a flexible coating and epoxy coating, the properties of the material also changes. So a fully impregnated textile will have higher efficiency in composite. Now, when you add other aspects, we are looking at different aspects of textile reinforced concrete. What are the other controlling aspects of textile reinforced concrete? The first one is addition of fibers. Generally, a lot of people add a lot of fibers to textile reinforced concrete, and this is coming as an application potential in different aspects of textile reinforced concrete. So let us see what happens when you add fibers to textile reinforced concrete. When you add large volume of fibers, you have high increase in the first crack load on the textile. You also see a increase in the number of cracks and lesser crack width if you have high volume fraction of fibers. But ultimate failure or ultimate load is almost constant for a composite with fibers and without fibers. So it does not actually give you any additional ultimate capacity, but it gives you a lot of advantages in serviceability condition. It enhances your first crack load, and it also reduces the increases the number of cracks and reduces the crack width. A similar effect can also be observed in case of textile with geometrical difference. What happens if I have textile with very close opening in comparison to a textile with very large opening? So we have tested two textile with larger opening size and smaller opening size. What we generally observe is that there is a higher first crack load when you have a smaller opening size, because there is more crack arresting mechanism in case of fibers with smaller opening size. Now, can we bundle the textile? I have 4 layers. I need 4 layers as per design. And can I put all the 4 layers together? In concept, that seems to be logical because the ultimate capacity is based on your ultimate load of the fibers or yarn. But in reality, that is not true. For example, in this particular case, we are using AR glass, F2 textiles, 4 layers of textile with spacing and without spacing. You can see the blue line indicates without spacing. So when we bundle them, there is a reduction in efficiency. And this reduction in efficiency is caused because of the slip between layers of textile when they are tensioned or when they are subjected to tensile stresses or flexure stresses. So these are the basic aspects of tensile or a behavior aspect of textile reinforced concrete that are concerned to us as a general designer or general application potential of textile reinforced concrete is considered. Now, what are the durable?
I hope you would be finishing.
I'll finish in
couple of minutes.
Yeah, 6 more minutes.
Okay.
Yeah. So another aspect that I want to focus is the durability aspect of textile reinforced concrete. So you can use a lot of. I said that glass fiber is most used type of textile in construction, but what all types of glass can be used? So there are basically two types of glass available. One is alkali resisting glass, which is AR glass, and another one is E glass. So in general, AR glasses, which is having zirconia content in it, performs far better than the E glasses, which actually degrades under general applications in alkaline environment of concrete. Why this happens is because whatever coating you are giving for the E glasses, they actually disintegrate after a due course of time and under exposure of this alkali solution, and that leads to potholes, which results in cavity formation in fibers. So you can see the cavities in fibers. So this is the basic types of failure that you observe in presence of OH minus ions in glass fibers. So these potholes act as wedges or initiates the fracture mechanism of the fibers, and this results in the failure of the composite and the fibers. Now, why should we think about E-glass fibers? If AR glass fibers are safe, then why we want to think? The basic aspect is the economic aspect. AR glass fibers are generally 3 times as expensive as comparison to E-glass fibers. So it is not applicable for all the general applications or low budget applications when you consider the applications of TRC. Also, there is lack of production of AR glass in India. We have to import this, and it comes with a lot of taxes. There is a lot of problems in market available E-glass fibers because a lot of confusion is actually there. This is to address the people in industry. A lot of textiles are coming as coated E-glass textiles which have poor durability. There is a lot of glass fibers which say that they are AR glass, but they are saying that they have AR coating over it. So what is the reality of all these things, and what we can do for a quality check? So we did some samples regarding markedly available AR glass, which this is a pure AR glass which has zirconium inside. So general content of zirconia content should be around 15%. If you look at the EDS image, you have around 15% zirconia in this particular glass fibers, where this is a markedly available AR glass, which says that they have AR coating over it or they are zirconia coating over it. If you look at the spectrum value of zirconia content, the value is very less. It's around 1%. So the point is, a lot of markedly available materials which say to be AR glass are not AR glass at all, and their performance in actual exposure to the alkaline environment of concrete is very bad. So this is the surface coated, what the manufacturer said as AR glass, performed very bad during the alkaline exposure and also during the performance of the composite. So in the composite, what we observed is this is the initial state of the stress. It has a capacity of 500 newtons in flexure for a coupon specimen. The complete degradation of the material happened after 90 days of hot water bath, which is actually an accelerated mechanism to find the durability. And the material completely lost the strain hardening behavior. So whenever you see AR glass, check whether this is a real AR glass or whether it has a zirconia content of more than 15%. So quality check is very important aspect, and that is something that we are looking for as an awareness program towards the manufacturers and the people who use textile reinforced concrete. Can we use E-glasses? That's a big question. Yes, we have to use E-glasses because there is no other way in large scale construction in India, because E-glasses are cheaper, and for large scale construction we have to rely on E-glasses. Now, how can we make E-glasses more durable? The first thing is have good coatings, uniformly coated, and a modified matrix. A modified matrix means that we are trying to reduce the pH of the matrix. So we have done a lot of work on reduction of pH of the concrete, and this modified matrix and well-coated e-glass showed that around 70 to 75% of retention of strength can be possible with the e-glass. That is very good in comparison to cost comparison, which is around 6 times that of AR glass. So it is actually possible to have good e-glasses with a slight change in the metrics and a very good coating that is on the element. Now, summarizing all the points, the sustainable design of TRC should be based on the mechanical, economical, and durability parameters of the metrics and the textile. The tensile response of TRC changes from a trilinear to a bilinear curve as the reinforcement ratio increases. Use of microfibers and close yarn reinforcement can increase the first crack. Efficiency factor for textile depends on coating, the uniformity of coating, and the cross section. And the proper testing of durability is mandatory before you use any types of e-glass fibers. I know I have extended a lot of time, but thank you for the patience for listening. I hope this was fruitful. Now,
thank you, Sachin. I think we will keep the questions till the end because we've overshoot the time. And anyway, we are meeting again at 4:30.
Yes.
Thank you. Sachin, would you like to take over the session?
Yes. So I will take over the session and I will introduce you to the next speaker. Let me project. Yeah. So our next speaker is Dr. Mohit, a very dear friend of mine, and I'm expert in the field of textile reinforced concrete. Dr. Mohit completed his PhD at RWTH Aachen and worked at various posts in RWTH regarding strategic development of textile reinforced concrete and other key relevant positions. In 2014, he actually came to India and started the company Reina Industries. Reina Industries focus on development of textile reinforced and fiber reinforced concrete infrastructure materials. And right now they are focusing extensively on marine application where the durability of a conventional reinforcement is a big problem. Dr. Reina also as a part of various international research projects, including one with IIT Madras. Right now, we are collaborating with RWTH Aachen and Mohit, and also with IIT Madras with a clean water project, which could be a part of a Swachh Bharat project in future. And we are developing clean water sewage treatment units using textile reinforced concrete. He is visiting faculty in many universities, and in 2001, Reina Industries have got National Award for successful commercialization of technology of textile reinforced concrete in Indian market. So I welcome Mohit for the next session, and I am sure that this will be a very fruitful session where he explained different aspects and his journey on the successful commercialization of textile reinforced concrete in India. Welcome, Mohit.
Thank you, Sachin. That was a very, very kind introduction. You'll have to stop sharing your screen though.
Yeah, sure.
Thanks. Yeah, I'm here to basically give you a run through what kind of works have been done with textile reinforced concrete. I hope all of you can see my screen with the presentation on there. Can you all see the screen?
Yes, it is.
Yes, Mohit, yes.
With the presentation as well, correct?
Sure. Yeah.
So what I'm going to today majorly talk about is yes, textile reinforced concrete, a little bit of fibers also to go with it, and I'll basically start with a quick introduction about different construction materials for tropical climates. Yes, we are in a tropical zone on the globe, and we have this problem of corrosion. So I'll be talking a little bit about that. And the challenges what we face in construction when it comes to lightweight materials, when it comes to corrosion, and how can we overcome those challenges using fibers and textiles. I'll also talk a little bit in more detail about the textiles. So Sachin has done half of the job for me already by explaining a number of technical stuff. I'll just show the commercial side of it a little bit, what we have to keep in mind while really manufacturing these kind of textile reinforced concrete things, and then the matrix, what is used, and I'll take you through a couple of engineering applications, and then the cost dynamics, because everybody wants to know the cost. So I'll tell you about the cost a little bit as well, and then we'll summarize the whole session. Let me start off. So we have got a very tropical climate. Yes, we are talking of relative humidities 35% to 100%. Mumbai, especially as on today, right now, we call it a winter day here in Mumbai with 26 degrees Celsius, but we have a relative humidity of around 80%. And this is moisture in the air, which basically penetrates the porous concrete, and it basically helps in doing this. This is something which we do not want in our structures. We do not want our structures to corrode over a period of time. The steel in there, which is the reinforcement basically, which helps it stay in place over a very long period of time, our structures, we do not want that to corrode. So the steel industry has been using a number of concepts on how to stop this corrosion. So they said, okay, we'll take conventional steel rebars, we'll galvanize them. So it's basically a small coating on the rebar, or you could also have fusion bonded epoxy. So this is what the steel industry is doing. They all have a specific lifespan between 5 years to 20 years. And then the cost also varies from X. If conventional steel is costing X rupees, the fusion bonded epoxy rebars will cost you 2X. So you anyways are going for a very expensive material. Off late, I would say during the COVID period in the last 2 years, the steel prices have also been really going through the roof, which basically means that anybody who requires non-corrosive reinforcement in their concrete has to look for other allied options as well. And that is where they face a lot of challenges. So these are some snapshots of projects where people had some challenges, and we came to the rescue, or we tried to figure out solutions with fibers and textiles. So this is one very intricate facade design where the architect wanted it exactly this way, and it had to be really thin. And they tried it with the steel reinforcement, but no good, because you had to really bend the steel in all different angles and positions. And that was a very tedious task, cost-consuming task, and still you were not secured about the long-lasting behavior of a facade like this. Another example, some benches to be manufactured. These are just off the street benches. You see them at every nook and corner in cities. They are also normally reinforced with steel, but there are clients who want them to last for 50 years, where the internals of the reinforcement in that concrete should not corrode. Another challenge which was posed, it normally happens that in conventional precast concrete, you want to achieve very beautiful structures, but if you have to really hoist them to the top of a building on a 30th floor, let's say at 60-meter height, 80-meter height, 100-meter height buildings, then they have to be lightweight. And people want to go for solutions which are where you use the least amount of concrete. You simply eliminate the steel reinforcement, but still it has to stand there in place and create a very wonderful structure. So these are some of the applications, and this is off late. We have been addressing some of these applications in the marine world. Saline waters, India, a coastline of 7,512 kilometers, an internal waterway of around 4,300 kilometers, all are rivers. And there is so much of infrastructure which is just rotting out there, because it is a lot of it is steel reinforced, and the country is now heading towards solutions in reinforcements which will not corrode, which will last the test of time. And we could have solutions which are economical, but at the same time they do not cause multiple times of refurbishment and redoing the whole thing. So this is where textiles come into place. And since I love textiles the way they are, I always bring on this very simple graph to understand why textiles and why fibers. It's very simple. For all the engineers right now sitting in the room, it's a simple load elongation curve of different fibrous materials. You start right at the bottom with polypropylene. which can be really extended, not like a rubber band, but yes, you can extend it. But your tensile load carrying potential of a fiber like polypropylene is not very high. Nevertheless, these fibers are used in concrete. They are used for shrinkage cracks. You put a lot of these fibers into the concrete RMC mixer so that when the concrete is being formed or is being laid, you have a lot of shrinkage cracks, and you require something flexible, a fibrous material which is flexible, which can avoid the propagating of the cracks. So that's polypropylene for you. Then you've got steel fibers. We talked about them extensively today in the first half of the day. Steel fibers being used for reinforcement of concrete. They also have they have got a potential of a higher modulus, but yes, they also have certain limitations when it comes to their flexural strength or their elongation properties. And then you go into these domain of high modulus fibers. Sachin very thoroughly spoke about alkali resistant glass. We spoke very thoroughly about carbon fibers. There are also aramide fibers for some kind of impact applications, bulletproof applications. But let's stick to AR, glass, and carbon. So two fibers, the cost difference between the two fibers, the carbon fiber would cost you around 3,000 rupees a kilo. The AR glass will cost you around 300 rupees a kilo. The E glass will cost you around 100 rupees a kilo. For everybody who keeps asking the costs, these are the costs, dynamics of these different kind of fibers. The wisdom lies in using specific fibers for specific application. There is no answer to having one fiber for all applications. We had in the first session of the day or the first couple of sessions of the day, the question was asked how much percentage of fibers to put in, whether on weight, whether on volume. The answer to it is very simple. It's a question, and that question is, what is your application? Your application determines the amount of fibers you put in there and what kind of fibers you put in there. Just to give you a comparison, how it is, the bottommost bar, you see a 12 mm bar. It's a steel bar. That's how steel bars look. Then you have got a fiber reinforced bar. So you had our Minister for Transport. He was showing around a similar kind of fiber reinforced composite bars, which are being slowly used in certain infrastructure projects in India as well. For the benefit of corrosion. So they are all non-corrosive. So they are fibers which are coated with the resin, and they form rebars. And then you have got something what is called as a roving. A roving, as Sachin correctly said, is a strand of individual fibers. Could be hundreds, could be thousands. I'll come to that in a while. And then you have got the single monofilament fiber, which is also sometimes used in certain applications. That too, I'll come to in a few seconds. Let's look at how they look on the inside. If you make a fiber reinforced concrete or you make a textile reinforced concrete, how do they look on the inside? On the left hand side, you see a X-ray analysis of a 70 mm by 70 mm by 70 mm cube, where you have the distribution of fibers randomly there inside the cube. It's a very dense distribution of fibers. You see there are some places where the fibers have kind of settled down on the left-hand corner of the cube, but there are other places where there is less amount of fibers. So this is how fibers normally settle down in concrete. On the right-hand side, you see an internal image of how textile segments are really, or textile mesh kind of segments are really placed inside concrete. You could have 1, 2, 5 layers, as Sachin really put it really well. And you could have them of different materials as well. AR glass, carbon, E-glass is something which we have still not got there commercially, but yes, we are trying hard with IIT together to find a solution for E-glass as well, so that we could have a reduced cost component on the reinforcement, and maybe invest a slight bit more in the matrix structure itself, so that we could have some great structures made out of E-glass reinforced concrete. But currently it's AR glass, it is carbon which is currently used, and these are some of the benefits. So the moment you put a textile into a concrete structure, so you're reducing the reinforcement necessity by around 80%. If you were to do the same thing with steel, you would have 80% more steel. So here you're reducing the reinforcement by 80%, you're reducing the amount of concrete and cement by around 70%. Eventually you end up getting a lighter product.
So if you do a per square meter analysis of textile reinforced concrete versus steel reinforced concrete, you will realize that the textile reinforced concrete is 80% lighter because it becomes very thin element. You do not require the concrete cover, which everybody speaks about when you talk about reinforcing concrete. So you do not require to have those tensile elements really surrounded by a lot of concrete. At this point of time, I know everybody is an expert here, but I normally put in one simple phrase for all of you just to revise it. Concrete is there for compression, the fibers, the steel, the textiles, it is always there for the tensile component in structures. So they take the tension, they take all the load when you really pull or stretch, or you have got such kind of loads acting upon your final structure. Moving on, what are the different kinds of fibers? A lot was spoken this morning about steel fibers, but yes, there are other fibers as well. You've got alkali resistant glass fibers, you've got carbon fibers, the more expensive ones. Then I talked about polypropylene being a kind of fiber which has got higher elongations, lesser tensile strength, but there are specific kinds of polypropylene fibers as well. Excuse me one moment. Yeah, special kind of polypropylene fibers as well, where you have got a serrated surface, like the one you see in the image here. Let me point it out with my mouse. And then you have got similar kind of fibers which have got a dog bone shape cross section. So these basically help anchoring the concrete much more strongly. And then you have also got these mesh kind of fibers. They're again used a little bit for the plastic shrinkage, and then for certain really high flexure applications, you use brass coated steel fibers. So this is the fiber world. What happens in the textile world? In the textile world, textiles are basically form of structures, fabrics. They are. You have lino-woven fabrics. The one you see here on the top. This is a lino-woven fabric. It is made on a weaving loom, and then you have got a warp knitted fabric. It is made on a knitting loom. So warp knitted and lino woven are the two kinds of fabrics which are conventionally used. You could have a three-dimensional fabric as well, which could be used in certain kind of applications where you require multiple layers and you need to have them at a specific distance from each other. These are all made in the form of rolls. This is one thing which is new to the civil industry. The civil industry talks about cubic meter of concrete. The textile industry talks about square meter of concrete. Marrying the two worlds together is the biggest challenge, and that is what is where all the fun lies as well. So coming to understanding a little bit the basics of textile reinforced concrete. So Sachin has touched upon this particular graph. It basically shows the three phases, as Sachin correctly put it. The first phase where you have got the matrix taking the entire load on the loading elongation curve. Then the second phase where you develop the multiple cracks, that is phase 2A, and phase 2B where you actually have the textile coming in and really showing how strong it could be in terms of stiffness and in terms of absorbing the tensile forces. If you mix fibers with them, if you take the textile structure and mix fibers with them, then as Sachin correctly said, it's more or less the similar, but yes, sometimes it is slightly higher depending upon the break load is sometimes higher depending upon the number of fibers you put in there and what kind of textile structure. Now, there are different kinds of textile structures. I will focus on this one specific textile structure to go a little bit more in depth from the practical perspective. As Sachin correctly put it, a lot of these textile structures which are being used, they are grid form of structures made out of alkali resistant glass. Let me explain you some parts of this grid. So you normally have the warp yarns. You see it in your upper left-hand corner. You've got the warp yarns, and then you have got the weft yarns at the lower left-hand corner. And then you have got the one in blue, which is the binding yarn. So you basically have got two yarns, and then you have got a binding yarn. Not very complex. What makes it complex? It is this. The choice of the green yarn, the choice of the red yarn, the choice of the blue yarn, it could vary depending upon application. You could have alkali resistant glass in green and red. You could have alkali resistant glass in green and carbon in red. You could have them of different linear densities. It could be a 320 tex, 640 tex, 1200 tex, 4800 tex, 2400 tex. So what is tex? Tex is basically the weight in grams per unit, per meter of strand, or roving as it is called, per kilometer, sorry. You could have different kinds of carbon being used. You could have 3K, 6K, 12K, 40 up to 48K carbon being used. So 48K stands for 48,000 individual single monofilament strands in a bundle, which comes as a bundle of 48 different, for 48,000 fibers. Now, the criticality when we discuss these parameters from the textile world with the construction world is, in the construction world, we basically talk about the grain size. You talk about the size of cement as a grain. You talk about size of sand as a grain. You talk about the size of the different aggregates. So in basic Hindi terms, it would be reti, khadi, and cement. So these are the three major things which you put together to make your matrix. And this kind of components of the matrix decide what is the spacing of your yarns in a textile. The X and the Y you see here, they are very critical, depending upon the kind of mortar, depending upon the kind of matrix structure. If you are putting in, for example, 20 mm aggregates, your grid size here has to at least accommodate one aggregate, or else you will have a delamination happening. So when we manufacture these kind of textile reinforced concretes, we make sure that we are having our grid size according to what is actually our aggregate size. So there is always a correlation. If we have got a 20 mm or a 10 mm aggregate size, then we normally go for mesh sizes 25 mm to 40 mm. This all can be adjusted on a textile machine. And the same thing is also with the element Y. You can increase the spacing between the yarns. You could have a skewed spacing. You could have the distance X between the green yarns. You could have it maybe as 25 mm, and with the red yarns, you could have it maybe at 16 mm. So we have tried multiple combinations. It is all dependent upon what kind of load carrying capacity you are looking at, what kind of reinforcement structure you're looking at, and how do you want to design your entire precast element. So moving on, what should the matrix look like? The matrix, as I said, you could use the bigger aggregates. Normal practice with TRC is, as Sachin correctly said, finer mortars with really high slump. So this is a small video showing you the slump of a mortar. This is a mortar which has got a water cement ratio. It's not a very high ratio. It's a 0.12 water cement ratio. It can give you strengths up to M80, M120, so 120 megapascal. And we use such kind of mortars where the aggregate size, as I told you in the earlier slide, is somewhere between 2 to 4 millimeters. So we can afford to go for a grid size here of around an inch by an inch, so 25 by 25, or also 16 by 16. And our mortar will really flow through all the crevices of the textiles and really integrate the textiles into itself. Sorry, moving on, we do carry out testing. So normally fiber and textile, so the textile reinforced concrete is tested the way Sachin presented it in his presentation. When we only look for fibers, we follow an ASTM standard. So when we are working with textile reinforced concrete, again, based upon the application, you could go from concrete densities ranging from 1400 kgs per cubic meter to 2400 kgs or 2600 kgs per cubic meter with very low water cement ratios of 0.08 to 0.18. It's very rare that we go to a water cement ratio of 0.24. Flexural strengths starting from 12 MPa going as high as 24 MPa. And compressive strengths, yes, it's not very relevant in the world of TRC, but yes, we do measure it between 50 MPa to 150 MPa, because these are strengths with which we could also get the compression also with very thin walled elements, as in you can get that compressive characteristic also with very thin walled elements. So you go for high strength materials. Moving on, this is a typical application for a facade wherein we use a lot of textiles and facades not only as primary reinforcement, but we also do use it sometimes to demold faster. There is a constraint, especially in the precast industry. You have got a limited number of molds, and if you want to complete a project really on time, you have to be able to be in a position to demold faster. So that is where we use textiles. It helps us that way bit to give that higher initial strength, higher initial flexure to be able to make it possible for us to demold a little bit faster. So this is how a textile is basically put in. It's completely impregnated on all sides by concrete. And then, yes, you have to integrate your fixing systems also into this entire thing. So if you're making a facade kind of a thing, then you have to really bring it onto the outer surface of a building. And that is where you need to have some kind of cast and socket elements. You need to have bolts, you need to have anchor fasteners, and these are all integrated along with the textiles to make sure that there is good enough load distribution happening in your entire screen. One such example here, these are 3.5 meters times 3.5 meter plates which have been manufactured. They're barely 18 mm thick, and they have got 2 layers of textiles in there. On the right hand side, you see how they have been lifted. The framework basically being provided to actually just bolt the entire screen onto the surface. And one important thing here to note is that these structures, if they were to ever break, for whatever reasons they were to break, be it vandalism, be it maybe a tower crane hitting into the structure, they would really first develop multiple cracks, and you will still have the textile holding them in place. They will never fall off like a big chunk of broken glass or something like that. It will just be very small. So there was a very beautiful technology by Saint-Gobain many years back. A patented technology called a Securite. It's basically the technology used for your front wind barriers on your car. So whenever your front glass of the car breaks, it normally breaks in very small particles so that it doesn't hurt anybody. A similar thing happens when it's an analogy. It's a similar thing happening with the textile reinforced concrete. If they were to ever crack and they were to really break because of vandalism, then you would have smaller pieces of concrete which are the broken components, so that it does not harm anybody who is around. So this is how a screen. I've got some shots from this very morning from site where a screen like this, I was pretty amazed by my team. We were installing a screen like this. You see the screen, the entire solid panel. This has got a textile reinforcement. Here, the textile reinforcement had 3 functions. The very first function was to help us demold faster. The second function was to help us lift and launch this faster. And the third function was to give it that additional reinforcement, to give it that longevity in an environment which has got around 80% air, 80% humidity, relative humidity, so that it does not corrode at all and stays there for a longer period of time. So an application from this very morning where we executed one more textile reinforced concrete. The whole journey, however, of textile reinforced concrete in India, it started around 2000, as in Professor Getu has been working on it since many years. Commercially, we brought this to India in 2014, and we started first making Swachh Bharat toilets out of it. The amazing thing is all these plate components which you see here, these plates are all textile reinforced concrete. If any one of you is ever interested, you can always give me a call or drop me an email, and we could drive around from Mumbai to Goa with a number of installations of these textile reinforced concrete in every single backyard of the Konkan belt, where people have appreciated this material majorly because of its non-corrosive behavior. Because these plates which we put in there, they do not corrode with a period of time, and they are very thin walled. They are barely 20 mm in thickness, and they provide you a toilet cabin which has got very high strengths. At some places, it was so high that people actually went ahead and made a different toilet for themselves and used the textile reinforced concrete toilets as storerooms for their valuables, because it was very difficult to break through them. So I'll now give you a quick update on the costs, how it is, the initial costs and the maintenance costs over a period of 25 years. We compared different materials, starting from a conventional galvanized iron sheet, going to brick and mortar, ACC block, cement board, gypsums. These are majorly based upon facade applications. But if you even go into conventional civil applications, if you go for solutions in the world of textile reinforced concrete, you will realize that there might be a marginal higher initial cost. But over a period of time, let's say 25 years, 30 years, 50 years, people want these days to have 50-year structures or structures designed for 50 years. You don't want to bring them down every 25 years. And these structures really will sustain. So you could have an element which is a modular element fixed onto a 25-year-old brick and mortar structure. And then once you want to pull it down and redo it, you could take the same textile reinforced concrete plates and again just fix them on with the conventional mechanical fixing. Yeah, so another comparison here with steel reinforced, there are various plus points here for textile reinforced concrete. Yes, there is one a bit of a small hitch where people normally say it is slightly expensive. Yes, it is. But if you consider the lifetime cost, it is actually cheaper for you. The initial slight escalation in initial cost, that is also currently being researched with e-glass fibers. The day we have the solution for that in our country, we will have a tremendous benefit. The other benefit is also going to be once the government of India thinks about reducing some of the import duties on alkali resistant glass fibers. They currently stand at 42%. So that would, if those duties are off, we would have alkali resistant glass fibers at half the price, and that would also make textile reinforced concrete much cheaper. And with certain building norms, certain codes coming in place, it would also become something which is there in every household in the coming years. So finally, I'll leave you with this one slide. I find this slide very powerful. So every time you hear any of these acronyms, FRC, HPFRC, UHPC, TRC, GFRC, SFRC, TRM, TFRC, GFRC, they all always basically mean it's fibers and textiles going into concrete, giving you a non-corrosive solution for having a sustainable future for our building industry. I'll like to very quickly summarize it with a few statements here. Yes, non-corrosive reinforcements, they are the thing which are going to go into the future. Yes, we have to have them designed very specifically based upon application. It's not a one rule fits all kind of a thing. You have to find out different fixing details, especially when it comes to facades and certain precast applications. And yeah, you need to engineer them. They are efficient materials and they need to be engineered, and always think about the lifetime cost of these materials. On that note, thank you very much for being a patient audience. I will be just jumping out of this meeting and rejoining at around 4:30, as I told you, Professor Sunita, and then I'll be looking forward to taking some questions then. But I hope I could get you all excited and intrigued about this new material, which is here to stay to help a sustainable future. Thank you very much.
Thank you, Mohit. That was a fabulous presentation, as always. And
always a pleasure.
It was so good with all the figures. I didn't have much of figures, so you actually explained what I could put in with more figures, and it was tremendous. So thanks again, Mohit. I hope you will come back for the question answer session.
Absolutely, I will rejoin.
Sure. Thanks.
So nice and right. So nice and right.
Yeah, I think we can move to our next speaker right now. Let me pull up her details and then we will discuss it. So next speaker is Dr. Steffi. Dr. Steffi is a postdoc currently working at IIT Madras. She has developed a software, SIG Concrete. She is an expert in both compression and tensile testing of concrete, and she's have done extensive work on fiber reinforced concrete and tunnel lining testing of fiber reinforced concrete. Now she got a national the prestigious award of INAE as Innovative Student Project Award in 2020 for her PhD project. Her area for expertise are tunnel lining segments, fracture mechanics, high performance concrete, sustainable concrete system, fatigue characterization, creep, shrinkage behavior, and now she's pursuing projects in TRC. I welcome her to the presentation and I give the mic to her to continue.
Yes. Thank you, Sachin. Thank you for the introduction. You can hear me, right?
Yes, you are audible. You are audible.
Okay, I'll share my screen. So can you see my screen?
Yes, yes.
And
yes.
also the pointer?
Yes, and both are visible.
Okay. Good evening, everyone. I am Steffi J. Stephen, postdoctoral researcher working in the Department of Civil Engineering, IIT Madras. Today, I'm going to explain the design aspect of textile reinforced concrete. Most of the experimental test results that are going to be discussed here are from the research work of Sachin Paul. And some of the concepts explained by Sachin will be reiterated here to enforce the importance of these properties in the design. I will be explaining the challenges faced in the design and how to use the different experimentally obtained parameters in the design. So as explained by previous speakers, TRC has numerous applications from being used in the construction of high strength concrete elements to retrofitting of existing concrete structures. You can make a thin and most economical and sustainable structure by using TRC. During the design of TRC elements, there are different parameters, different areas you have to look into before addressing the design. So the first one would be the material selection. So depending on the type and loading occurring in the structure, the fabric that is chosen for making the TRC has to be determined. So it basically depends on the strength of the fabric, stiffness, durability, how far it can sustain the environment, and also it should be economic. And then another parameter is the matrix. So the matrix will be designed based on its strength, of course, its strength, stiffness, and the bonding, how well it could bond with the textiles inside, which is present inside the matrix, and how well it can protect these textiles from the environment, and of course, economic. So so after the material selection has been made, we have to derive the mechanical response of this material which has been chosen, and we have to derive its tensile stress strain response of the material as a composite, and we have to identify different design parameters such as efficiency factor, which was already explained by Sachin, and how to idealize the material, how did I find an idealized material model based on the stress strain response. So once this has been characterized, we move on to the structural design. There are two types of design which are discussed in this presentation. The first one is efficiency factor method, and the second one is transformed section method. This first method is relatively simple, and but however, it does not account for the stress strain response. Whereas the transform section uses an idealized material model, which is further used in the design equations. So as explained by Sachin, this is the typical tensile response of the TRC element. So here you can see initially there is a linear portion, and then there is a sustained load carrying capacity of the TRC element, and then the strain hardening begins. So the curve can be splitted into 3 zones. So in the first zone, when the behavior is linear, the section is uncracked. So when the stress reaches, when the stress in the TRC element reaches the tensile strength of the concrete, crack occurs. So this behavior, this portion is influenced by the concrete matrix. And once the tensile strength of the concrete is attained, the crack occurs. So on further loading, the load carrying capacity almost is equal. It's almost sustained, but the multiple cracks occurs in the concrete. On further loading, your the strain carrying capacity and the strain hardening type behavior occurs while the crack is widening. So when the crack widens, the textiles in the concrete comes into the picture and it expands and helps in the strain hardening type behavior. So this behavior is, this tensile stress strain behavior is influenced by various factors such as number of layers in the textiles, number of layers in the TRC, and the spacing of the yarns in the TRC. So all these factors will influence the behavior of the tensile response. So as such, when comparing this the TRC element, the reinforcing yarn has a complex structure. So if you look in closely, you can see multiple fibers in a single yarn. So these are numerous number of yarns which are present embedded in the concrete matrix, and this is a single filament. And you can see the one that is on the outermost, this is the cross section of the yarn, a single yarn, and you can see this is the outermost filaments are called the sleeve filament, and the innermost fibers are called the core filament. So when you are applying tensile load on these yarns, what happens is because it has a very large amount of fibers in it, and only the outermost portion of the fibers are in contact with the concrete matrix. So there will be a differential stress profile occurring in this yarns. Okay, so because of that, there will be a telescopic type failure occurring. So these will be intact with the concrete matrix, whereas these fibers will get pulled out. So this is the type of failure that is occurring in the yarns. So because of this, the complexity occurs while using these parameters in the design. So the overall behavior of the composite depends on the type of coating. So basically this type in this figure, it does not have any coating at all. So if there is coating, and if the coating is impregnated, all the fibers will act together, thereby its response will be enhanced. And it also depends on the material, the type of material which is used to make this yarn. And also the behavior is also influenced by the number of fibers. If the number of fibers in the yarn is higher, its efficiency will be lower. So these things will be explained. So depending on how far this coating is impregnated into the concrete, its response will be different. So this one is without any coating. It's a uncoated textile, uncoated yarn. And this one is partially or surface coated yarn. And this one is completely or fully impregnated yarn. So if you see the stress distribution here, if this particular yarn is subjected to loading, the stress distribution will be higher, stress will be higher at the outermost portion, whereas the innermost portion will be subjected to almost no load, or almost no stresses will be occurring in these fibers. So when moving on to the surface coated, so these are surface coated and these are held together. So thereby, when the stress is occurring, when the load is applied on this concrete matrix, the stress transfer will occur in these intermediate, and some amount of stress will be transferred to the inner also. So the stress difference in drop in stress will be decreased when there is this coating. In case of completely and fully impregnated coatings, the stress distribution is almost same when compared to the outermost. So the basically this behavior is characterized by the factor called efficiency factor, which is the ratio between ultimate tensile strength of composite to the tensile strength of reinforcing yarn. So when you compare this between the surface coated textile and a fully impregnated textile, you can see that the fully impregnated textile has a better efficiency because the strength transfer is good. The efficiency is also higher. So the fully impregnated textiles have higher efficiency than the surface coated textiles. So moving on to the type of coating, what type of coating you are adding on the yarns. They also depend also influences the efficiency factor. So here you can see the epoxy coated yarns, and these are the SPR coated textiles. So the ultimate tensile capacity of epoxy coated yarns is higher than the SPR coated textiles. But however, if you see here, the efficiency of epoxy coated is lower when compared to XPR. This is due to the fact that the epoxy coated textiles have even higher tensile strength. So the efficiency factor is determined basically by calculating the cumulative response of the TRC divided by the tensile response. So when you are comparing that, the tensile, because the epoxy coated textiles have higher tensile strength than the XPR coated, it has lower efficiency. So that also, even if it performs better, the efficiency is lower. So that should be kept in mind while accounting into the design. And also the effect of type of yarn, depending on the fibers, which are depending on the type of fibers that is going into to make the yarn and textile, also influences the behavior. So here, if the fiber used fiber is having high modulus, that's say the glass fibers, you can see there is a strain hardening behavior, and it has very high strain hardening behavior. But however, it fails very, it has very low crack, it undergoes very low deformation, and thereby it has low ductility. So if you are using an application where the strength is important and not the crack width, you can go for glass fibers. And in case of low modulus fibers, such as polymer fibers, you can see there is low strain hardening response, but it has higher ductility. So in cases if you want to resist higher crack widths, you can go for our polymer type fibers. So the efficiency of these fibers, these are e-glass textiles. Sorry, these are e-glass textiles, and these are AR glass textiles. So if you compare, the AR glass textiles have higher efficiency when compared to e-glass textiles. And now that you have all derived all the efficiency factor, know what is the efficiency factor and how to derive it, we'll go on to the design, which is based on the efficiency factor. So first you have to calculate the ultimate load carrying capacity. So the factor, the ultimate load carrying capacity, is a multiplication of the efficiency factor K1 of the textile, and K2 is the efficiency, there is a factor for biaxial loading. So if the loading is occurring in a longitudinal direction, the transverse reinforcement will also help in some way to resist the loads occurring on the structure. So there is another factor K2, and another factor K alpha is also used, which depends on the orientation of the yarns. So it can be, the yarns can be either be 90 degree or it can be even 45 degrees. So depending on that, this factor will be chosen, and this will be multiplied with the cross-sectional area of the roving or the filament or the yarn which is being used, and this will be multiplied by the ultimate strength of the reinforcement. So once this ultimate load carrying capacity is derived, we can multiply this with the lever arm and obtain the moment carrying capacity. And if this is higher than the moment occurring in the structure, design moment occurring in the structure, then the structure will be safe. So however, these equations and derivations are simple. They don't use the stress strain response and does not account for the crack width in the design. So we go on to another even sophisticated design approach called design using transform section model, where it utilizes the stress strain curve, which I showed earlier. So the stress strain curve, what I showed was a trilinear curve, but Sachin actually explained how the trilinear curve becomes a bilinear when the number of layers is increased. So we are actually idealizing the bilinear curve as our tensile model, and the compressive model will be linear. Why? Because the concrete, since the concrete will always fail in tension, flexural capacity is always controlled by the tension, and the compressive stresses is normally in the low elastic range. So this type of model is chosen for compressive compression, and this type of model is chosen for tension. And all these parameters, this is the Young's modulus, and this is the ultimate tensile strength, and this is the matrix tensile strength, and this is ultimate strain capacity, and this is the matrix strain capacity. And depending on this curve, we can derive the moment equations. So based on this, first we will derive the stress distribution. So initially, when TRC element is subjected to flexural loads, when there is no crack, of course the stress strain behavior will be linear. So this is the stress distribution. The stress distribution is linear initially. So once the crack occurs, the curve becomes bilinear. So after this, after the crack has occurred, it is the textiles come into the picture and it takes the load. So these textiles will take the load, and on further loading, the crack progression will be increased, and thereby more textiles will come into the picture, and more strain hardening responses obtained. So this curve, this particular curve will be used for the design. This particular phase of the phase of cracking will be chosen to derive the moment equation. So this is the moment equation. This is the stress distribution in the across the cross section of the a TRC element of depth D, and the lever arm is at a distance of KD, and you can see that the compressive forces, there is compressive forces and tensile forces T1 and T2. So first, initially what we do is we normalize all the parameters which I showed in the tensile model and compressive model. We normalize them and have a normalized parameter, derive a normalized parameter, after which we derive the equation for compression. So the area under the area of the stress curve into the breadth of the TRC element will give you the compressive forces, and the same way the T1 and T2 is derived, and after which we have to determine the neutral axis depth. For determining the neutral axis depth, you equate the compressive and tensile forces in the section and derive the K factor. So once these are determined, when you multiply this factors with this moment, this force equations with the lever arm, you will get the moment carrying capacity of the section. So this moment carrying capacity cannot be used as such because there will be some reduction due to the variability in the material, workmanship, etc. There is a reduction factor of 0.85, which should be multiplied with the moment equation. So once this moment carrying capacity is known, based on yield line analysis for a particular element, in this case I have chosen a circular panel which is fixed at its edges, and it is lying on a subgrade. So it has an external load, and it has some also oil pressure also, which is coming at the bottom. So in order to determine its determine the deflection occurring in the structure, we use the inline analysis to determine the work done. We equate the work done in internal work done with the external work done. And so since both the loads are in opposite direction, the external load will, the work done due to the external load will be, work done due to the external soil pressure will be deducted from the work done due to external load. So, and using this equation, the external soil pressure, work done due to external soil pressure can be derived. And from this, the deflection equation can be derived. This equation can be further used to calculate the crack width occurring in the structure. So basically the design steps would be like, the basic inputs for the design step will be thickness, tensile and compressive stress strain curve, from which you derive the idealized stress strain curve. And then you normalize the design parameters with respect to the cross section and reinforcement ratio. And then you derive the moment equation using the material models. Then we derive the deflection occurring due to the applied load and calculate the crack width. And if the design crack width is less than the allowable crack width, it is safe. Else you have to change the reinforcement ratio. So this is the basic design step. So with this, the design of TRC is done. So I'll move on to the modeling, finite element modeling and analysis. So moving on to the finite element modeling, here you can see a flexural member, which is modeled in TNO Diana. So here modeled as a 3D nonlinear macro scale model. And it has, we have modeled of both the TRC, both the matrix and also the textiles, that both are modeled separately. And the interface between the concrete and the matrix is defined by the bond slip response, which was obtained by from the experiment. And then it is simulated to obtain its deflection and stress response. So here you can see the load carrying capacity of this member. So it actually, the simulation and the experimental results actually matched. So using this type of analysis also, you can predict the behavior by knowing its stress strain response. You can predict the behavior, this structural behavior. Here there is an example for of circular water tank, which has been designed. So in this also, however, we didn't model the textiles. Only the whole element is modeled as a TRC unit. So the behavior of the TRC itself is fed into the program, and the mesh size of this was 100 mm. And the compression and tensile strain, the compressive stress strain curve of concrete is fed into it, and the tensile stress strain curve of TRC is fed into the model. And we attach the loads and boundary condition. And so the loading will be triangular loading since it's subjected to water pressure. So, and this is the type of deflection that is occurring in the element, and you can see the stress distribution. And these values matched with the theoretically obtained values. So this is another way to determine the response of the by using the experimentally obtained stress strain curves. You can predict its structural response as well. So with this, I will conclude my session.
Thanks, Steffi. Thanks for the design aspect. Now, we have some questions in the comment section from previous presentations. I think we can break for the tea break and then come back at 4 o'clock for the next session, and then we'll continue with the question and answer.
Yeah, sure.
If
sure.
that's okay with everyone.
Sure.
Okay. Sunita ma'am.
Sure. Thank you, Sachin.
Yeah.
Before we break for tea, we will have the last sponsor presentation.
Yeah.
Please, Arya, would you like to take over?
Yes, ma'am.
You have to also share the
brittle. Typical stresses like impact, fatigue, and loading lead to cracking and eventual failure. Adding reinforcement to the concrete helps to absorb these stresses and to limit the formation of cracks, increasing the load-bearing capacity and ductility of the concrete structure. There are several ways of reinforcing concrete. We've all heard about rebar and steel mesh, but did you know steel fiber is just as strong and reliable? Since its introduction over 40 years ago, steel fiber reinforcement has proven its merits in the most demanding structures and applications. The core difference between steel fiber and other reinforcement solutions is that fibers are part of the concrete matrix, turning it into a composite material. Instead of providing strength in distinct locations, steel fibers form a reinforcing network throughout the entire concrete structure, increasing its overall ductility. So how does this translate into concrete behavior? Take a random concrete structure. When subjected to loading, compressive and tension stresses start to build. Over time, small cracks will appear in places where the stress reaches a critical point. Steel fiber interacts within the concrete matrix, absorbing tensile stresses at any point and in any direction. As a result, steel fiber picks up small cracks much faster than traditional reinforcement. When a crack occurs, the hooked ends of the fibers remain solidly anchored on each side of the crack, acting as a stress transfer media. Once the maximum bond strength with the concrete is reached, the pullout takes full effect. This enables the next fiber to take over, delaying cracks from growing. Different loads require different steel fibers. To meet any design requirement, Beckart offers 3 steel fiber types: Dramix 3D, 4D, and 5D. Each fiber has a different hook, strength, and ductility. Consequently, they also behave slightly differently when dealing with stresses. Let's take a closer look. First up is Dramix 3D. When a small crack occurs, the 3D hooks firmly anchor inside the concrete matrix. As the stress increases, the hook slowly deforms. As soon as the fiber loses its bond with the concrete, the pullout takes full effect. Dramix 4D provides the same process, but with even better anchorage and a significantly higher tensile strength of 1,650 Newton square millimeters or more. Dramix 5D behaves differently altogether. Here, the hooks never pull out from the concrete. As the stress increases, the wire slowly elongates until it reaches its maximum strength. With a tensile strength of 2,300 Newton square millimeters and elongation of 6%, concrete structures reinforced with 5D can take high flexural stresses over a long period. Based on these behaviors, we can conclude that Dramix steel fibers effectively increase the load-bearing capacity of concrete. It can be used in almost any concrete structure with or without additional reinforcement, where the ductility of your concrete structure depends on the length-diameter ratio of the fibers and the number of fibers used per cubic meter. It is essential that enough fibers overlap to create a continuous network in the concrete mix. Do you need help finding the right fiber and determining the right dosage? Beckart gladly provides expert guidance through each step of your project from design to execution. Visit www.beckart.com/Dramix to get in touch. Concrete is...
Now I invite Mr. Pratik Deodas from Beckart to talk about the company.
Yep, thank you, ma'am. I hope the video made the concept little more clear, and if someone wants to watch the video again, it's available on our YouTube channel on Beckart Construction. So just I'll take 2 minutes to give you a brief about our company. So Beckart is a company named after our founder, Mr. Leo Leonard Beckart. So Beckart is actually a family name, just like Bajaj or Tata in our country. So the Beckart company is 140-year-old company with its headquarters in Belgium, Europe. It's a stock-listed company in Brussels Stock Exchange, which is in Belgium. We have a combined sales of 5.1 billion euro per year. Transforming steel wire and applying coating is what we do. But doing this, we are active in almost most diverse industry sectors. To name a few: automobile, construction, energy, and utility. So Dramex is a product line from our construction division. So steel fiber, a product and the concept, was invented by Bekaert in 1973, and it has been more than 50 years now. This steel fiber technology has been used to reinforce industrial floors, warehouse floors, and in underground segment for tunnelings. Even in India, we are executing almost 1.5 lakh square meter per year, Dramix steel fiber reinforced flooring in different industries and warehousing segment. Also in tunneling, we are supplying around 10,000 metric tons of fibers per year. So that is how the product has got its acceptability even in the Indian market. And we would be more than happy to help anyone with their requirements and if technical queries, if any. And thank you once again for giving us an opportunity to showcase our technology and to give me a chance to speak about our company. Thanks once again.
Thank you, Pratik. Thank you for the brief introduction to your firm. And thank you for sponsoring this event. So I hope you will be around, and if there are any questions, we'll take it up during the question and answer session.
Sure, ma'am. Thanks. Thanks.
Yeah, we will assemble back at 4 p.m. Welcome back, all of you. Just a couple of announcements before we go to the next session. We will be sharing a Google form within a couple, 1 or 2 days, in which we request all the we will be sharing the form to all the registered participants, and we request you to give your feedback as well as give your complete postal address in that. This is for us to send you the certificates and the copy of the TC, the ICI document that we have promised for your registration. So kindly fill in your complete postal address in the Google form that we will be sending you. I hope all of you are clear, and we will be compiling the entire video of this sessions and posting it in YouTube, and we will also send you the link for your further reference. Now we will go to the last session. Sachin, I request you to take over.
Yeah, so good afternoon yet again. The last session will have two parts in it. One will be some of the fabrication that we have done at IIT Madras, and some of the fabrication techniques that we use for this construction. And the last part will be testing, which is already in a YouTube video that we have made for NPTEL, and we will display that. So we'll start with the fabrication systems of TRC. I hope you can see the presentation.
Yes, the presentation was.
Okay. Yeah, so this is a group work. We have been working on TRC for the last 4 to 5 years. The group mainly consists of me, Dr. Komati Murugan, who's a postdoc, and Ram Krishna. And we have expanded that to around 10 people right now, with collaborating with the IIT Palakkad, with Aachen University of Aachen, Germany, and also we have some collaboration with Mohit and ACRC. So this is basically the contribution of the combined group. We discussed earlier the application of TRC. Basic application of TRC is confined to thin section applications. And around the world, Germany was the first to initiate different processes of fabrication of TRC. And then some of the applications or some of the initial works were also done in US by Professor Basim Washer, and also some with Alva Pellet. So this was the time when 2002 to 2010 was the initial stages of TRC, development of TRC, where they thought about how to develop this material as a retrofitting material and also as a self-standing structural and non-structural element. We'll start with a retrofitting work that we have done. This was in a SAC building, that is Students Activity Center at IIT Madras. And this was renovated throughout, and there were 2 columns in the toilet unit which was severely damaged. So this is the image of the column. And generally what we were observing in the column was loose concrete at different places with a very low strength. We could also see the exposed rebars and the tie bars of the column were visible at most of the places. We were also seeing extensive cracking at different locations of the column. So what we initially did was a initial test with some NDT equipment. So we got column 1 to have an average strength of 18 MPa and column 2 to have 24 MPa. But in general, there are a lot of places in these columns which were very weak and very need retrofitting. And we could locate rebars and main bars were around 16 numbers of 25 mm bars, but there was uneven location of the tie bars, which was because of some of the tie bars were corroded. So we did intense scrutinization, characterization, and also a design aspect for finding what are the type of textile that should be used, how many layers should be used, and what will be the confinement that you will get out of this. And we concluded that 3 layers of a particular textile, which is SG45 from Saint-Gobain, which is AR glass textile, will be good enough to give a particular confinement that we were looking for. So the retrofitting method naturally requires a different type of metrics. So we looked at a very stiff mix for the combination for this purpose. So we developed a much stiffer mix than what we generally do in our laboratory. And we characterize this composite with textile with the composite characterization. You can see the stress strain response. So we do the uniaxial tensile test to characterize what is the tensile response of the composite. From there, it is the step-by-step procedure of jacketing. So initially it was plastered with 10 mm before we started the plastering. We started the retrofitting with TRC. So first layer was placed with a mortar, and after the first layer of mortar, we attached the textile ring to it, and then the next layer of the textile was placed. The placing of textile or the joining of textile was done with ties. We never used anything with which has corrosion potential. We used non-corrosive ties, plastic ties, and polymeric ties for the joining of 2 layers of textile and also wrapping up of the textiles. So the textiles were wrapped against one another, and each vertical section was lapped with 150 mm overlap. This 150 was obtained from a test that we have done for lap length for textile. So we actually did different lap lengths for this particular textile with a 50 mm, 100 mm, 150 mm, and 200 mm. And from that, we observed that 150 mm of lap is good enough to transfer the load from one level to other. So with that, we lapped, all our lapping was around 150 mm overlap, and with 3 numbers of textile row, we were able to cover the entire column. Then the second layer was laid, and then the second layer of textile was laid, then third layer of mortar and third layer of textile, and further the last layer of mortar, which gave 3 layers of textile with overall 18 mm thickness. So this was one of the jacketing works that we have done. Note that the cement that we generally use for jacketing or the metrics that we generally use for jacketing will be very stiff, because you have to have this mortar or matrix stick to the textile layers. Okay, so that was the one of the ways in which you actually retrofit on the layer. So the similar concept we used to develop a ring. So we wanted to develop a water container. It was actually water tank for a sewage treatment unit. This was a prototype. So we were looking at different possible way of developing it. So a similar approach that we have done for the retrofitting, we did for this. So we had a base ring element, and then we developed a very stiff mix, and we did a sacrificial layer. So this sacrificial layer was developed with a e-glass textile, which was very cheap, very thin. It was just the purpose of this layer was just for the mortar to stick in, because it was a steel platform or steel envelope. Okay, so we did again different layers. We did the first layer, and then we wound the first layer of textile over it, and then we finished with the second layer, and then again one more layer of textile and the final layer. And this was the final ring that was cast, and we stacked 3 rings. So the second and third ring actually had a notch at the bottom, such that the one ring will sit over the other. So the notch was also done with the TRC, and we specifically molded the shape of the TRC at those notching points, such that not with the it's a pivoting point. We kept it such that the shape is maintained, and one ring will go inside the other ring, and we could construct it. So finally, the 3-ring structure was developed, and the base of this 3-ring structure was also textile reinforced, and it has 3 layers of textile in the base platform, and 3 layers each at every ring, with a textile from Saint Gobain again, which is called as A27 textile, which was used for this construction. So the plastic sheet that you can see above is for loading. So we loaded with water, and we are trying with SEC to see the load capacity of the element. So we are trying to induce a maximum pressure inside using a self-compacting concrete. Now there is another technique that you have seen in Dr. Mohit's presentation, that you can also fabricate by stretching the textile and pouring the concrete in. So this is one of the general application or general method by which we make small panels in TRC. So what we generally do is we fix one panel, the textiles on towards one panel, and we stretch from the other side. We also use some additional spaces at the center, such that there was no sagging at the center. And then what we do is we pour NSCC. So the consistency of the mix should be such that it just freely flows into every nook and corners, because you have multiple layers in this textile, in this metric system, and the metrics or the concrete should be able to penetrate through different layers. So it was a well flowing self-compacting concrete with a particle size of, in this case we used a maximum particle size of 1.2 mm aggregates. So we used very fine aggregates, and this was executed, or this was one of the methods in which we made a lot of specimens with this. We did square panels for testing, and we did extensive testings on flexure and the square panels of this, and also circular panels with this method. Another approach other than stretching is by use of spacers. So this is from RWTH Aachen, Germany, where they have used spacers instead of stretching it into a exterior support system. They have used spacers. So you can use plastic spacers for each layer of textile. This is generally applicable for more stiff coatings like epoxy coatings. For SPR coatings, there can be bending of textile if you use spacers. So that is a limitation when it comes to spacers. If the coating material is very stiff and you are capable of keeping the horizontality of the textiles, then you can use spacers to keep textile layers at position and then have concrete over it. Another application, very interesting application that we did was fabrication of bench. Okay, so this was actually we actually did a bendable mold. So this is a horizontal. We actually did cast the specimen horizontal. So we did a long span panel, and then we did an SCC, self-compacting concrete. And once it started to set, what we did is, once it have gained enough plastic state and enough solid state, we bend it such that there was no crack developed. So we have to time it properly, and the mix should be very stiff. We used a 60 MPa concrete for this, and we were getting a very good finish at the corners. Even we didn't get any cracks in the corners. So this was a final finished product. This was a bench that we fabricated for that it still sits on outside IIT Madras work lab. So you can go there. If you're visiting the lab, you can go and sit on these benches. So we further extended that to a bigger dimension element. So this was like a 3 meter complete span. Horizontal span of this element was 3 meter, and we tried to bend it to form a stormwater drain. So this was a trapezoidal stormwater drain that you can see throughout into IIT Madras. And this was an individual panel that we made out of it. The overall thickness that we got was around 18 mm, and we used 4 layers of AR glass textile to do it. So bending of specimens is also possible. There is also another application of this. Once it has partially set, you can actually take this and put over any shape, any curved shape that you have, such that it takes the shape of the curvature. So you can make parabola and other shapes, or other curves like domes with this type of process. So there are endless possibilities with a textile reinforced concrete and flexible, and especially in architectural aspect, you can do a lot of things. Only limitation is your creativity. Now we did a different thing. We did a very huge water tank system. So we had to make a square water tank, and we were looking at what are the possible ways in doing it. So what we did is we did a horizontal panel with 4 units such that it forms a wall of the water tank, and we separated the joint in between, and we separated such that there is no concrete in that separation or the joint between the areas. And we used SCC, self-compacting concrete, for this. And once it was cast, the separations in between was removed, and we could make a box out of it. And later, this box was reinforced by FRP bars, fiber reinforced polymer bars, and then the corners were concreted, and this formed the square water tank system, which we tested after this with water. And this was also for one of the projects that we did for sewage water units. 3D textiles. This was executed by Dr. Komati Murugan of our TRC team. So 3D textile has a lot of advantages. What is 3D textile? Generally, what we were referring till now is a 2-dimensional textile which has a weft and warp. Now, what can happen when you combine two layers of textile? So you can combine 2 layers of textile by connecting yarns between them. So this we can do by joining during the weaving process itself, or you can fusion bond it after time. So we actually bonded them and formed a 3D textile. The advantage with 3D textile is that you don't need to put spacers, or you don't have to stretch them to keep in position. Just keep the textiles in a particular mold and you can fabricate it. So 3D textiles are very easy and very construction friendly aspect of TRC elements. So if you have a proper 3D textiles that your manufacturer is able to make, then that makes the construction of TRC a very simple procedure. Just have to keep these specimens inside. So there's a panel with 3D textile. You just insert that into a panel, into a mold, and then pour SCC over it, and you get a finished product panel. Especially this is good in construction of cylindrical containers and other vessels, where you can just keep the cylindrical container and inside the mold, and then pour the concrete over it, and you have the final finished product available. Okay, so these are some of the fabrication aspects that we did at IIT Madras. Should we take comments at this, or we will complete the testing procedure?
We'll complete the testing also.
Yeah, we'll complete the testing. So give me a second to pull out the testing.
So Sachin, have you?
Sorry. Are you able to see the presentation?
Yeah, but no, it's not playing, and now.
Okay. Yeah. So I'll play the presentation, and we will take queries after the presentation. So this is a basic video that we did for NPTEL, and you can also find this in YouTube. Search for textile reinforced concrete. This will be the first video that you will get. Okay. I hope you enjoy the video.
Hi all, my name is Sachin Paul. I am a doctoral research scholar working in Building Technology and Construction Management Department of IIT Madras. My area of research is on textile reinforced concrete. I'll be explaining what is a textile reinforced concrete and how a uniaxial tensile test is done for textile reinforced concrete and what are the factors that we need to consider while we are doing a uniaxial tensile test. This test can be also done for other materials with fine grain aggregates, basically mortars or fine grain high strength concrete can be also tested it. There is this limitation for testing on larger aggregate concrete, but this is basically as per RILAM standards of 2016 or RILAM test methods of 2016 for uniaxial test of textile reinforced concrete. Now I will explain to you what a textile reinforced concrete is. So a textile reinforced concrete is a concept where we are combining a normal concrete with textiles as reinforcement. Now what is the advantage of this is that textiles that we use are either carbon, polymeric or glass fiber textiles. These doesn't corrode in an aggressive environment, so it is a corrosion free element. So we can have a very thin element, structural, both structural and non-structural element with a high capacity and it can be used for very thin application, exterior applications, and it has very high durability since the corrosion is not happening in this material. Okay. So here with me I have an example of what a textile is. This is glass fiber textiles. These are e-glasses, coated e-glass textiles. So these textiles comes in a roll of 50 meters, usually have a width of 1 meter. So we incorporate this in fine grain concrete. Why fine grain concrete is because when you have textiles of small meshes, you need aggregates to be very small such that it could easily penetrate through the small gaps of the textiles. So that is why we are basically using a fine grain concrete. So this is a strip of textile that we have cut out from this roll. This is what we use for reinforcement for uniaxial tensile test specimens. This final specimen that we fabricate after will be looking like something like this. The dimension of the specimen will be 60 mm width, 10 mm thickness and a length of 500 mm. This is actually a 4-layer textile. So we have 4 layers of textile inside it with a spacing of 1.5 mm each. What we are trying to do is do a uniaxial tensile test with respect to this. The maximum size of aggregates that we use in this is around 0.6 mm. So it's a very fine grained concrete. So the problem with the uniaxial tension test is the gripping is the primary problem, how to grip the specimens. So what we use is a aluminum plates that is attached to the ends such that the crushing failure does not happen during the gripping process. These are specimens that is attached with the aluminum plates. So we cut out rectangular aluminum plates on the gripping area and we embed them or we fix them with epoxy resins and we let them cure for 1 day. Then we are doing the test after that. So this prevents the crushing failure of the support due to the pressure that builds up during the testing process or gripping process. Now the gauge length for the uniaxial tension test is basically a 200 mm gauge length as per RILAM standards. So we will be using a combination of 2 axial extensometers. One is an axial extensometer and the other one is a video extensometer, and with combination of this we will be trying to find the strain variation or the displacement in this material with respect to the load acting on the element. This is a 100 mm axial extensometer. So what we are trying to do, this is a contact type axial extensometer. So we will be attaching the axial extensometer to a 100 mm gauge length on the specimen, and this is a dual axial extensometer. That means that it has 2 axial extensometers, and what we get is the average of both the displacement from the 2 sides. Okay. So it gives you an average displacement that is happening in the 2 phases of the specimen. So here is a setup for uniaxial tension test for TRC. we use two systems for taking out the displacement or the strain of the element. One is an axial extensometer. So, this is an axial extensometer of 100 mm gauge length. As I have said, this is a dual axial extensometer where you have two setups for the axial extensometer and you get an average of the two displacement at the two faces. We also have a video extensometer. A video extensometer is a non-contact type extensometer. So, this is a video extensometer. The video extensometer has two sets of camera. The video extensometer detects the contrast between white and dark spaces in any image and converts that into pixel, and whatever displacement that is happening with respect to those pixels, it records as a strain or displacement. Okay. So, basically I have marked 4 points or 4 positions in the gauge length of the specimen. The first one is 100 mm gauge length, which is equal to the axial extensometer. Why this is to detect whether the video extensometer readings are as same as that of what we observe in axial extensometer. The second one is a gauge length of 200 mm, where that is as per the standards of RILAM for testing of textile reinforced concrete. So, the video extensometer can detect between any given 4 points or 5 points or any n number of points given in the framework of the video. Right. So, once we have tested, for example, if you need to find the gauge length or displacement between the gauge length of 200 mm, you can test between the gauge length of 200 mm, and then after testing you can actually go back to the video and then find the difference or the displacement between any other gauge lengths provided in the frame of the video. So, that is one of the advantage with a non-contact type extensometer. The other advantage is that this material can crack anywhere in the specimen. So, for a contact type extensometer, when you have crack near to the extensometer, it causes distortion in the readings. This can be avoided in case of video extensometer. Also, for a material like textile reinforced concrete, you will have multiple cracking that is happening in the gauge length, and that can be very well captured by the video extensometer. So, we are trying to see the interface of the axial extensometer and the civic testing machine, and we will see how the video is captured and how it is dictated and how the strain measurement is taken out by the video capture. Okay. So, in the screen what we can see here is 4 points representing the 4 dots that we have in the specimens. The first 2 dots is a gauge length of 100 mm and the second 2 sets of dots is a gauge length of 200 mm. The red lines indicates the marking points in the specimen by the video extensometer. What video extensometer measures is the contrast between the white and the dark. So, you can select the zone of interest and that zone of interest will be marked as the point of reference for the displacement for the video. Right now I have selected 2 points of 100 mm gauge length. Now after testing, if I need to find the gauge length or displacement in a gauge length of 200 mm, I can shift to the 200 mm gauge length and do the test again without repeating the test, just by rerunning the software, just by rerunning the video. So, that is one of the major advantages of axial extensometer, video extensometer, where you can do n number of repeated iterations with different gauge lengths with a single test. So, we will start the experiment. You can see the force and the displacement in the Now, you can see multiple cracking forming in the gauge length of the specimen. Now, this is where the influence or the advantage where non-contact type video extensometer comes into play. Since the cracks can form anywhere, it can also form in the position of an LVDT or a strain gauge. So, a non-contact extensometer helps us to take data out even if you have a mechanism like a multiple cracking. So, we have completed the test now and we will look at the stress strain plot of the TRC element and see what are different characteristics that is involved
in a TRC element subjected to tensile stress. Okay. So, this is a basic plot of force versus strain, percentage strain. Now, you can see two different slopes for the graph. First slope is representative of the matrix properties, and the first slope is ended by the first crack formation in the specimen. So, the initial portion of the curve in a textile reinforced concrete test, or when textile reinforced concrete is subjected to a tensile stress, is represented by the properties of the matrix itself. Once it starts cracking, it forms multiple cracking and it stabilizes at some stages. The stabilization process is such that further crack formation is not possible in the specimen. Once the crack has stabilized, then the strain hardening happens in the specimen. The slope of the strain hardening zone is the representative of the property of the textile. So, it basically depends upon the property of the textile and the volume fraction of textile that is in the specimen. The graph can be basically divided into two segments. The first segment till first crack of the specimen is dominated by the properties of matrix. The stiffness is directly proportional to the stiffness of the matrix itself. And the second portion is the strain hardening area or the strain hardening zone, where the properties of the textile is predominant. Once the multiple cracking has happened, then all the tensile stress is taken by the textile. So, we have discussed the specimen preparation procedures, how to mount the specimen, the gripping procedure, how the end plates are fixed, how we use a video extensometer and an axial extensometer to take out the displacement in the specimen, and also the stress strain response of TRC in uni and axial tensile test. So, that is all. Thank you from me. Yeah. So,
thank you. So, thank you, Sachin. Now we have a lot of questions to all the three speakers. So, I will read out some of the relevant questions. So, one question is, both glass and cement matrix are brittle materials. How does the glass reinforcement contribute to the ductile behavior in TRC?
Yeah. Mohit, you will answer or I will answer? Hi Mohit, I think your mic is mute. Okay. Yeah. So, that's something that I discussed in the initial stages itself, that in TRC, if you take the matrix is very brittle, and the concrete is also, and the reinforcement is also brittle. But what TRC does is it actually behaves like a pseudo ductile behavior. It actually has a strain hardening behavior, which is actually product of a multiple cracking and then expansion of this multiple crack. So, that is what gives the ductility to material. It is not the actual ductility, it is not the actual deformation as we see in the reinforced concrete. So, it's a very specific behavior, and that is what gives ductility to it. But in addition to that, as Mohit said, that once those who have seen the failure of a TRC, it doesn't disperse after failure. It actually confines, or it actually get hold of all the reinforcement materials, and it doesn't drop down, especially in slabs of testing of TRC. So, we have some testing slabs that we have done, and it doesn't dissipate after failure. So, that is because of the confinement effect of TRC, or that when you have flexion in TRC, not all layers are subjected to failure. Only the bottom layer fails and progressively fails from the bottom layer upwards. So, most of the layers in TRC is still intact, and they hold the remaining of the textiles. And there is also a third factor to it, that the post-peak behavior, which never we consider in design of TRC, but post-peak behavior is a lot dependent upon the bond between textile and the coating of the textile. So, if you have a coating like epoxy coating, which is very stiff and makes the reinforcement very stiff, you have a very sudden failure after the ultimate peak. But you have flexible matrix or non-coated textile, then you can see a progressive failure where you have the sleeve failure, and then it progresses to the core failure, and that gives some ductility, which we were able to observe in the tensile test. So the failure, even after post-peak, will be like a step-by-step failure. So there are different aspects of TRC that contributes to ductility. Ultimate failure of TRC, especially in slabs, is not a sudden failure. It doesn't fail all on a sudden. It just holds like very similar to what you see in your front glass of your windshield, as Mohit said, or what you say as a what double glaze glass, which you protective glass that you use. So it is very similar. I hope that answers. Mohit, your mic. Okay, I think Sunita ma'am, you have muted Mohit.
Is it? I mean,
yeah,
I think check again.
Now I'm on again.
Yeah,
okay.
Yeah.
I think somebody muted me.
Yeah.
Anyways, just to add what you said, Sachin, is basically people have this perception glass is like just a piece of glass you drink water in. It's not precisely that. So the fiber which is currently being used, or the alkali resistant glass fiber, if you go down to the fiber level, it is a fiber which is a high modulus fiber, which basically means that it is designed to take loads, the fiber itself. And when the fiber is designed to take loads, if you go into the fiber morphology, you will realize that there are amorphous and crystalline zones of the polymers itself. So those crystalline zones are, you have to imagine molecules and molecular chains. And these molecular chains are really lying parallel to each other and not in a very crumbled form. So they are a very crystalline material. So this crystalline material, when you really pull, and they give you that really high or they absorb that much amount of tensile force, and it only fails when these molecular chains really slip off each other, and that's where the crack happens in the textile itself. So this entire strain hardening area, that phase 2A or 2B or the last phase, which also Sachin shown in his presentation, during that phase, it is the tensile load going on to those glass fibers. Those crystalline molecular chains inside the fiber, they are being exercised with tensile forces, and those actually hold on to those very high tensile forces. And that is why they might be brittle on an edge. If you take a knife edge and put a glass fiber, it will just break. But that is along the cross section of the glass fiber. In the longitudinal section, it is basically these molecular chains who are actually taking all that load, and that is what happens at the fiber level. And then yes, once that happens at the fiber level, then as Sachin correctly said, there is then the coating, and then finally the matrix. So although concrete may be brittle, and glass as a material, as in the glass of water you drink in, that is amorphous glass. The glass you have in a fiber has got a very high crystalline content, which gives it that very high modulus. So that is why that is not just as brittle as a glass you drink water in. I don't know if that answers the question.
Yeah, I think that answers.
Yeah. So thank you, Mohit and Sachin. Just maybe there are a couple of questions about the matrix. So maybe you can discuss a bit about what is special about the matrix that is used for TRC. And there is also a question as to whether use of finer aggregates makes TRC more suitable for repair, strengthening applications or precast elements, and whether it is a limitation of TRC.
Yeah, Mohit, you go ahead.
So I'll just start with the limitation of TRC. See, one of the biggest limitations right now of TRC is that we do not have building norms in place to use them for any kind of structural application. We do not have them in this country. Even abroad, in Europe, in Germany, where some of this material actually started existing around 30 years back, even those places have now got, in certain specific conditions, with certain specific mortars, with certain specific textiles, they have got a kind of a code in place. But it is not a generic code where you say, okay, you take any textile and you take any mortar and you can do it. So I think codal challenges are there. On one side, so you cannot so that is one limitation of TRC. You cannot just put it anywhere in structural applications. You can use it as retrofits nevertheless, as in if you are repairing a bridge, you normally use some of these carbon fiber grids. You use them to strengthen bridges and stuff like that, but not directly into concrete. They are more so wrapping around of pillars, wrapping around of bridge structures. That is more with an epoxy matrix or an iso matrix in which you do it. The first question was about the concrete itself. I think Sachin, you're a better expert on concrete than I am. I'm more of the textile guy, so I will give that to you.
Yeah. In addition to what Mohit said, what we generally look for TRC is, what we are trying here is to optimize the material. So we are trying to have very thin material, not to build up a bulk of concrete, and then there is no difference between, there is no advantage or edge for TRC. So the whole concept is to reduce the minimum, optimize the material, have a thinnest section as possible, and use for those applications where you require a thin section, not for general application. Like I can't go and make a column itself with TRC or a beam itself with TRC. That's not possible, right? So this is our next level or next generation of thin wall sections or thin element sections, which is going to build up very fast in the future. But the application is limited to that. And that is one thing that we should realize before we tell with the TRC that we can use it for any applications. That is not possible. This is specifically for thin applications. Secondly, related with concrete metrics, we generally require very higher cement content in comparison to normal concrete. And that comes with mortar itself. If you mix a mortar, normal mortar also have a higher cement content in comparison to normal concrete. This mortar or this concrete for TRC should have higher penetration capacity. So it should have particles of smaller size, and the selection of the particle size basically depends upon the mesh opening that here you have, and the distance between, or the height difference between the layers, the gap between the layers that you have. So that is the parameter that defines what should be the maximum size of your aggregates. And then again, you should have proper bond between the textile, which is a smooth coating that we have most of the textile and the metrics. So we have done 60 MPa concrete. Mohit has done from 40, I think, to 100, 120.
120 we have gone up to.
Yeah. So we have done 60 and 104. So that will be the range that we look forward for TRC application, because that also gives an edge in compression. When you have flexure, you have a top zone of compression, and you have that compression less compressive capacity, then you have to increase again the section just to take the compressive load. Okay. So a higher compressive capacity also gives you an edge on your flexure behavior. So that's about metrics. Metrics basically consist of fine materials. We also add silica fume and fly ash. Silica fume basically to optimize the cement content, and fly ash to optimize the cement content, and silica fume for a proper bond. It gives a finer interface between the textile and concrete. So that is always optional, whether you go for that or not. That is basically dependent upon what you look for in the mix. I think I have
also just to the basics, Sachin, you would also agree to this. When people ask me this question often, can we make a whole building and pillars, and can we make bridge piers out of textile reinforced concrete? My answer to most of them is very simple. As in, what do you have in a bridge pier? Do you have more compression or you have more tension? If you got more compression, the material of choice is concrete. So go ahead and take a good grade of concrete first before you think about any textiles, putting any textiles in there. So coming down to those basics every time with every application, where does it make sense? Where does it give its value addition? And what is the value proposition if you're using textile reinforced concrete? These questions are elementary questions before you go to any kind of further discussion on whether and how and whether codes are there or no.
Yeah, well, that's really true. And in addition to that, I want to add one more thing, that we don't know what is possible with TRC right now. It's endless, because we have just started to explore different possibilities, and other countries have already started a decade ago, but we are also exploring on the same track line. So it is possible to have a lot of things, but we know what it is not possible. So you need a lot of research, you need a lot of execution in field, and you need a lot of initiation from the industry to actually channel through different possibilities of TRC at this stage.
Okay, thank you. Sir, would you like to add anything to that? Sir, you're muted.
Yeah, thank you. I hope everyone has had a good workshop. It's good to see 70+ participants at the end of the day. after a long day. So it's really heartening that so many people are interested. And I'm sure that all the speakers have done a great job in explaining how these two materials can be used. We have to start using them. Then we'll understand more and more. Certainly, there'll be a lot of skepticism whenever we have a new material, but neither of these two are really new materials. I think it's we have to use these as systems. It is the same concrete, it is the same reinforcement, it is just a new way of thinking. And I'm sure that we will have a lot of positive applications coming out. And as Mohit rightly said, the same material or same system cannot be used in all applications. So we have to understand where to use these effectively and get the best out of the material. Yeah, I don't know if there are any specific things that I need to talk about, but I'm very happy that this has come about. And hopefully the next time we'll be able to do a in-person workshop and have more discussions and interaction, which will certainly be very useful for everyone.
Definitely, sir. Just one more, a couple of more questions. One question is, do you recommend or prefer certain types of woven fabrics over others when making complex shapes with TRC? So is there any recommendation?
I know Mohit may be the best person to answer that.
You can have I mentioned lino fabrics, and you could have warp knitted fabrics. Warp knitted fabrics, basically they are slightly expensive, but delamination is less of a problem there, because you basically have got two threads kept one upon another. They are not ondulated, they're just kept one upon another and tied. It is just like when you take two steel rebars, you keep two steel rebars one upon another, and then you do the tying. So that is what is happening in a warp knitted structure. In a lino woven structure, you basically have, just like any other fabric, you have got the yarns going up and down. So if you have got 4 yarns, so you will have one going front, one back, one front. So you will have an ondulated structure. So this ondulated structure, it is used more often because it is cheaper. But ideally, we wouldn't wish to have an ondulated structure. We would wish to have, similar to the steel rebars, we would wish to have fibers which are just kept one upon another and just tied together. So for multiple applications where I would always suggest, especially where you want the fabric to come into being and really take those go through that phase of strain hardening, there I would really always prefer a warp knitted structure. The lino woven structure is for some low end applications where you also have a lot of draping requirements, where you have to really, if you have to make a bowl out of TRC, so then you have to really drape the whole thing upon it. So that is a place where we use lino woven structures. For both, keeping in mind that my individual components of the matrix, they should be able to impregnate my textile. That is a very essential thing. If they do not impregnate the textile, then I will just have 2 layers of concrete just coming out like 2 slices in a sandwich, and you will have all the masala inside the sandwich really fall on your on your desk. So you don't want that to happen. You don't want that textile to be a barrier. It has to be a reinforcement structure. So you have to have that kind of textile in there. I hope I answered that question.
So if I can add, I think when you want to stretch a textile, I think the lino weaving helps. Lino woven helps when you have to stretch and if you want to bend. And this we are seeing that could be possible with textile reinforced concrete, where you can have a element that you cast, and by the time it's completely hardened, you can give it some shape. So there, the lino woven textile might do better, at least in the joints. And when Mohit said, when you have like a dome or a shell, and you want to conform to a certain certain shape which is not flat, then maybe the lino woven, where there is a little bit of stretching. Now, also what we have seen is when we have decided where to use it and we are doing prefabrication, we can also look at 3D architectures. Just like in traditional reinforcement, you have the bars which are made into a cage, and then you fit the cage into the mold. So same thing can be done with the 3D architecture of textile. And this we've done a little bit in a lab, and that is very useful, because you then don't have to worry about where the textile is everything is in its place, and then you put it in and then pour the concrete or your mortar in. So eventually that, I think, would be the way that people will start using textiles in mass casting of precast elements, at least, just like we do with traditional reinforcement.
A statement which I'll just add, Professor Gettu, what I normally tell all architects around India and the world is textile drapes and concrete in its green state flows. So run your imaginations wild, and it can be achieved with textile reinforced concrete, thin wall elements especially. So I think that helps a lot of them to design their structures.
Maybe one more question from TRC. Does TRC always require a coating on surface or embedded coating? I guess it is meaning whether we always should use coated textiles.
Yeah, I think I'll just start about it and then Mohit can take over. Coating helps a lot in the handling of textiles. So the coated textiles are much easier to handle. They does not disintegrate upon handling. So in that context, coating is good. Second aspect is the efficiency. If you have a better coating, well executed coating, your efficiency goes up. You get more out of the given textile, given cross section of textile. So coating is actually good in those aspects. Now, where coating can be a problem is heat, temperature. When you have high temperature, like a melting temperature beyond the melting point of this coating material, then at high temperature, we have seen some cases where there is a slip on textile. So other than that, in most of the cases, practical application cases, coating helps, and coating is required when you do a large application of textiles. I think Mohit can also add with the practical applications.
From the practical thing, I always tell my team a very simple thing. You have to think of, since it's textiles, the reinforcement, you have to think of coating and non-coated fabrics in the following fashion. And that's very easy to visualize as well. You have got a white colored cotton shirt, which is ironed. And then you have got a white colored, fully starched, hard starched cotton shirt, which you have to iron. So both have its advantages and disadvantages. If you have got a fully starched cotton shirt, it will look very crisp on your body and it will stay in its place. While as one which is not starched, it will just drape around your body the way you want it. So there are advantages to both. There are disadvantages to both. In the practical world, again, when we are looking at structural, semi-structural members, or we're looking at flat panels, bigger domes, that is where we require the textile to be stable also in production. We do not want it to just kind of fold and bend like a curtain structure. We want it really to be there in position. That is where we normally go for coated fabrics. And if we want to really drape it around something, we have to kind of create a sphere, for example. Then we really want it to be flexible enough to be able to achieve the structure it is being formed into. So that is how we basically differentiate between the two. And yes, as Sachin also put it in some of his studies, the coated one, however, nevertheless, how you place it, it gives you a higher performance as compared to the non-coated one. That is always there, but it is again for what application you're using it.
Okay, so I think, thank you. We'll wind up. If there are no more questions, shall we wind up? Thank you, everybody. In this, it has been a great day with so many participants, and we've tried to bring in two different worlds of fiber reinforced concrete and textile reinforced concrete. We wanted to have talks from industry, academia, research, and we tried to blend in everything, including the testing. And I hope you all had a fruitful day. As I had mentioned earlier, we will be circulating a form where you please give us the detailed, complete postal details so that we can send the certificate as well as the ICI-TC document, which we have promised along with the registration. I would like to thank ICI for their support in this event and controls, especially Federica, Shailesh, Ganesh, for having supported throughout the organization, and the team at IIT Madras, Professor Gettu, for all his support, and all the speakers, Professor Gopal Ratnam, Dr. Mohit, I think Steffi, Sachin, all of them. Thank you very much from my side, and to the sponsors, of course, I should not forget mentioning. They were a great support, and thank you. If anybody wants to add, please unmute yourself.
Ganesh, would you like to say anything as a closure?
I think it is the first workshop I am seeing where there's a lot of blend is there and we are completing on time. I think many more to go. I think this is the start we have done. Let us take it to the next level in terms of really doing some applications. Yeah, that would help the industry. Yeah, thank you.
So
Thank you, Sunita. Amazing. Yeah.
Dr.
Yes,
Sunita, ma'am.
please.
I'm Dr. Vasudev from Toughness Institute of Science and Technology, Kerala. So hope you remember me, ma'am. Namaste and very warm good evening to Getu sir and all the speakers of the day. Really, from morning 9, it was totally a wonderful session, and I wish the same session or similar sessions would be there in IIT Palakkad and IIT Chennai in the normal mode. So that we can visit all these facilities over there. So this is our personal request, ma'am, and hopefully the 72 members who have joined over here will have the same thing to say to you, ma'am. So probably you may arrange such a session to us, ma'am. So we wish to do so. Thank you very much. And once again, I extend my thanks to Sunita ma'am as well as Getu sir for arranging such a session for us. Thank you, ma'am. Thank you very much. Thank you, ma'am.
Thank you. Good.
Thank you, everybody.
Thank you. Thank you.
Thank you. Then we will just take a picture, all of you, if you could switch on your videos.
Okay. How to do that in gallery? Yes. Somebody's walking around.
Yeah. Just one more.
Excuse me, my video is stopped. Please let me come in video.
RB Singh, sir. RB Singh, sir.
Sir, Singh, sir. Yes, sir.
Yeah.
Thank you. Yeah. Sir, would you like to say anything?
Yes, I would like to add that this was a most comprehensive program I could attend through webinar. And as an independent laboratory, it has given us insight to take a sincere step towards establishing facilities for FRC and TRC in whatever way we can start, because we are already into concrete and advanced structural testing. So for me, it is a very interesting workshop in both way, in knowledge as well as entrepreneurship. And I'm delighted to see here very senior old mentors and professors like Getu Sahab and my colleague Ganesh, who has been inspiring all along to venture into this critical field where tunneling is a major application area, and we have tunnel in every city, including in Agra, in our own city. There would be tunneling after 3-4 months. So certainly this workshop is going to be a major step in helping, and I think it is the most fruitful webinar of this year. We are concluding almost financial year in March. So with that, thank you very much, and thank you for allowing me to come on the screen.
Sir.
Sir, thank you for the sponsorship and for supporting us.
You're welcome, and we are ready to participate in a major way whenever there is an opportunity. Definitely. Just remember us. And it is just a contribution and giving back to the institutes from where we learn, and from that learning we are earning. So I'm just giving back Guru Dakshina. Nothing like that is sponsorship.
It's very kind of you, sir.
Very kind of.
Yeah, this we will continue this program in a bigger way as soon as things are better. I wish and hope that all of you are safe and healthy. signing off till the next meeting.
Okay. Thank you, Sunita. Well done. Everybody.
Thank you.
Bye-bye. Bye.
Thank you. Bye-bye.
Bye, Sachin. Bye, Stephanie. Hello. Sir.